Okay, so good morning to everyone. I hope that you had a nice evening yesterday, apart from the rain. And so this morning we are starting with a keynote session with our three speakers that you see here displayed, who will actually give us some key reflections on how we can actually use Earth observation to tackle challenges and human needs. So we will have these inspiring talks, and after which we will go in the thematic and technical sessions. So it's a pleasure for me to introduce our first speaker, Dennis Pamlin, who is the Executive Director and Senior Advisor at the Research Institute of Sweden, and founder of the 21st Century Frontiers, a platform to address the global challenges and turn them into boundless opportunities. He's previously been a policy advisor at the WWF, director for the Low Carbon Leaders for the UN, and today he's leading the Net Zero Compatible Innovation Initiative. So Dennis, the word is yours. Thank you.
To be here, and this is where we thrive, in data. That's what we need. So I'm going to share a few slides, and they will be shared with you, so don't be afraid that it will be quite quickly here. So if I share this. So what you see now is the heading: an expanded climate and innovation agenda, delivering on human needs beyond optimization of existing systems. And this requires a new generation of data. And when I was asked at the Paris meeting to lead this new work, the focus was, how do we provide for a future where 11 billion people can live flourishing lives? What is the new generation of data that is needed? And the background for this is obvious. You've all seen this. Between the Kyoto Protocol, the first really major agreement on climate, and the Paris Agreement, we basically saw no change. But that was not really the intent. The idea between Kyoto and Paris was to try improvement in existing systems, because the rich countries were supposed to reduce their emissions by 5%, but many of them created creative accounting and sort of tweak their old unsustainable systems to become a little bit less unsustainable. But we were not on the right track. This was not a path for the future. And this is a major challenge now for the data we provide. Because the last 30 years, the data was meant to optimize old systems. Now we need data to guide us for flourishing lives for everyone on the planet. This is a significant challenge for us. Because what we have created is what we sometimes call a carbon accounting tunnel vision. Much of the data is used so people can claim that they are carbon neutral or carbon positive or something. But it's not really looking at what solutions are being given to society. It's an accounting challenge. And if people are reducing emissions, they are reducing emissions without a long-term consideration. They optimize systems that are fundamentally unsustainable. You get slightly less pollution from a transport system, but that is not a transport system that can give us sustainable mobility for everyone. And also we tend to ignore the data is helping us to address climate, but it's not addressing the fact that we need to address biodiversity, equity, mental pollution, and other challenges. So that requires us to rethink what are the data sets that we are providing and how are they used. And what we have done then is try to make this as simple as possible, just to make people think that what we can do with data is addressing a static problem approach. That is when you look at existing sectors, you look at problems, and you try to improve that. You see transport and you say, how can we optimize that? You see energy production and you say, how can we shift that to slightly less carbon? What we are saying, that is not always bad, but it's not enough. We also need strategies that focus on how 8 billion today and 9 and 10 and maybe up to 11 billion people can live flourishing lives. And how do we find solutions for this? What are the solution providers? So instead of focusing on the problems and looking backwards, we need data that helps us look forward. What are the new solutions that are needed? And if there are two things that I want you to remember is that data, almost all and tools that exist today are based on the 90s. That is focusing on how we, the rich world, if I include all of us in the rich world now, we are the 10% that emit a lot. And then we try to tweak our systems. But that is not really the challenge. The challenge is not to reduce emissions. The question is how we can avoid emissions as most of the population on the planet is moving out of poverty. So that requires us to rethink. We shouldn't just track CO2 and where that is emitted. We need to see where are people and how are they moving out of poverty in a sustainable way, and how are we in the rich world live more flourishing lives while doing that in a resource efficient and carbon free way, instead of just trying to make fossil free versions of what we have. The other one is the innovations, and this is probably closer to your heart, but during the 90s and earlier, we only looked at slightly better cars. When I went to Kyoto in 97, people said we're going to use coal power for 200 years. There's not a future in the near future for solar or wind. It's easy to forget that only 30 years ago, the idea of the internet was a new thing. And the idea that we can have exponential lower prices on solar and smart solutions were non-existing. And things are moving faster now. So how are we making sure that the data we are providing is not locking us in yesterday's society? And this is just a slide and looking at some of the companies that did not exist at the time of when the climate discussions emerged in the 1992. Amazon, Oatly, BYD, Netflix, Trina Solar, Google. These are people that have changed how we eat, how we meet, how we find information. I'm not saying that these are only good solutions, but these are people that and companies that really have fundamentally changed things. And what are the new solutions that are now emerging for the next 20, 30 years? And that's where we need data to help those emerge that are really new smart solutions that provides us with healthy nutrition, exciting living, outdoor experiences, science and art. How do we live flourishing lives instead of looking backwards? Because what happens then is that IPCC is now changing their focus. They are looking how we can reframe from a problem to solution opportunity focus, and how we can leverage in human needs based on innovation as an entry point. This is Diana, who's leading the new special report on cities. So if you want to be part of the future and the next science, that is where you should focus, not how you optimize the old system. Because if we simplify that in images, we can call it a static problem approach for data. Then you look at the big pollutings, the buildings, transport, industry. And then you say, how can they reduce emissions? And what we get with that focus is the equivalent of fossil-free typewriters, if we started that 30 years ago. You look at the problems and then you're trying to make a fossil-free version. What we want you to start considering is, how can you have a dynamic solution approach to data? When your focus is on how do people get better lives, nutrition, health, spaces living, social development and personal growth. And then mobility and access and energy are only enablers for that. If we have, or fossil-free steel or something, if we have fossil-free steel building oil platforms, that is meaningless. But if we have smart fossil-free steel that can be used for public transport or offshore wind power, that is part of the solution. But much of the data now don't really show how is it contributing to the human well-being and global sustainability. So that filter is needed. And in addition to just this human needs, we also need to have a global perspective. Many people in the West seem to think that we are just going to improve our lives and make it slightly less carbon. But we need to see a future where everyone on the planet can live flourishing lives. And that requires us to rethink fundamentally in how we provide for those needs, from nutrition to what is really valuable. Is it to have a super yacht and a sports car, or is it to be out in the forest with your family? What are the kind of futures that data is providing us with? What are we emphasizing? What are we trying to encourage? So data needs to be put in that context. Because what we have now is really emission data and data that looks at the physical infrastructure. And that is, of course, especially if you look at Earth observatory data, these are the things that are simple to see. But we need a filter between that so we can see how are human needs being delivered on in a global sustainability perspective. So how can we use the current data and add on things like brain science and studies about human behavior and human preferences, so that data can transform into something really usable to guide our future. And that is really requires us then to divide the different data sets and understanding. Where is it being applied? Is it applied to human needs, or is it applied to systems that are maybe delivering on human needs and maybe not? And that is the real big questions we're facing now with data sets, and how we can group those, because data about mobility and energy and natural resources, of course, are not bad. We need them desperately, but they need to be linked and so we understand how they are delivering on the human needs. So I really want to emphasize it's not that the current data sets are bad, but we need a new way of framing them and linking them so they are usable and not just usable for optimization of existing systems. And that's where we have also provided some instruments that you can use. You can look at your current strategies and documents and scan them and see how much are you focusing on solutions and how much are you focused on human needs and how much are you focusing more on problems and just data in isolation. But you can also start thinking about what kind of cities are you supporting? Are you supporting the idea that the only thing that cities can do is just to reduce their emissions? Or are you providing data for cities so they can become solution providers? The way that Baoding, for instance, in China, has helped us bring down prices on renewable energy. What are your data helping the next generation of cities to become solution providers for? So, with that, I want to say that we have an exciting data future ahead of us. We need to expand the climate innovation agenda, looking at human needs and solution providers. We need to link our current data sets to human needs, and we need to use an 11 billion flourishing lives filter so we think about how resource efficient and smart the solutions needs to be. So with that, I stop. Thank you for inviting me.
Thank you, Dennis, for this inspiring talk, and I will ask if there are questions from the audience. In the meantime, I have a question. You've been talking about the difference between the static and the dynamic approach to data. So if we are optimizing our existing problems or if we are going towards, let's say, new solutions. Since here in the room we have a lot of nice minds that are working on our data, what would be your concrete suggestions for them in terms of going in this direction that you very well depicted?
I think what we have seen is really the way forward for most. This is, of course, very general. People are, many in the rooms are really brilliant and have their own path forward. But to create clusters that reach all the way to implementation. So you have some way of seeing the feedback systems, because it's easy to sit with you and look at the quality of the data and the amount of data without really understanding how it's ultimately going to be used. So the way you structure and tag that data can have fundamentally different impacts. So trying to create that kind of clusters. So you try that with a city or with a company or with a research organization that is focusing on delivering actual solutions on human needs. So you try to see that and say, how do I extend my new network? Because usually we have horizontal network with people doing the same thing. So we share tools and understanding, but what we see is really helpful is if people extend it vertically all the way, so you can see a person who's getting a better life through your data. So you have that track all the way down. That is what we have found is really helpful. Not all the time, but just test sometimes and say, where can this data set go? And I try to track it all the way to that person. And that you tend to also inspire innovation, because that makes it interesting to think, this is how my data actually ultimately is used and benefit people.
Thank you, Dennis. If there's no other question, I would thank Dennis again with a round of applause. Thank you. Thank you. So we will move now to the next speaker. It's a great pleasure for me to introduce Martyn Clark. He's the Urban Resilience Coordinator at GEO, the group of on Earth observation. He is an urban development specialist with 20 years experience in the public and private sector. He has worked with a range of development organizations as well as national, subnational and municipal governments. He has decades experience working on urban development programs in Africa and Asia, much of which has focused on developing low-cost, replicable tools and approaches to promoting sustainable urbanization. Today, he leads the GEO's engagement across the theme of urban resilience, and he will talk about how Earth observation can support urban resilience and sustainable urbanization from GEO's point of view. So welcome, Martyn, and the floor is yours. Thank you.
Thanks very much. Good morning, everybody. Hope you can hear me. And thanks for the wonderful introduction, and really appreciate Isa allowing us to speak today. I will hopefully build on some of the points Dennis has just made, but really from GEO's perspective, we want to sort of paint a bit of a picture of everything GEO is doing in support of kind of urban scale or urban resilience building. This is a relatively new engagement priority for the group on Earth observations, although the group has been around for it's just going into its third decade. Urban resilience is the most recently adopted engagement priority, and effectively what that means for me as the urban resilience coordinator is trying to better connect the needs of users, end users or anticipated end users, those working in cities, communities living in cities, connecting that group to I guess all of you, the community, the Earth observation community, the academics, institutions, individuals, research organizations that are doing all this wonderful stuff with EO. But to begin, urban resilience. So my entry point into the world of Earth observations, as been said, my background's urban planning, so I'm often thinking about the use of data, the use of Earth observations from the perspective of that technical officer, somebody sat in a city who's trying to take decisions that shape the future form, function of cities. Urban resilience, I suppose, is a term that has kind of grown in popularity over the last decade or so. To me, it's still kind of loaded with technical connotations. It's not necessary. It's reached common parlance within the kind of international policy arena, but not necessarily the person on the street. But I think really, as Dennis said, it's thinking about the concept as a somewhat dynamic phenomenon. So trying to build the capacity of the city systems, surely businesses, institutions, communities and individuals, to, as the definition here says, to adapt, grow, and no matter what chronic stresses and acute shocks they experience across a range of things. So I think we commonly think about climate resilience in the context of urban, but what kind of economic shocks and stresses do cities in aggregate face, as well as those households or businesses living in cities, as well as all of the kind of social and institutional aspects of resilience that that can do with some support. So it's really thinking about this concept of urban resilience in all of its kind of flavors, and the contribution that the data and the Earth observations in particular can make to supporting cities advance towards somewhere approaching resilience. It's really difficult to disentangle, I think, as I say, the concept of urban resilience with climate resilience. It's perhaps here that, in my experience, this is where cities are often thinking about the concept of resilience, or being encouraged to think about the concept of resilience. As we've already heard, I think there's a lot of progress has been made in the last 2 decades in terms of setting that international policy agenda for climate resilience, although that hasn't necessarily trickled down or been articulated in plans, strategies, actions at the local level. So there's still quite a long way to go in terms of, I think, all cities globally, working towards a net zero future, or a place where populations are less vulnerable or more resilient to a range of climate shocks. There's this, I suppose, I always think about this in terms of cities having this kind of dual pathway where they not only contribute hugely to greenhouse gas emissions and global warming, but that you have this concentration of vulnerability and vulnerability to a range of climate shocks in urban settings. So cities really have this dual role of being able to reduce society's contribution to climate change, but also depending on how they are planned, their form and function again, how they're able to respond or adapt, become more resilient to climate change. And noting that cities, as kind of complex, diverse environments, kind of lend themselves to place-based approaches, and by definition, the need for spatial information to help understand how different phenomena play out over space, but also over time. So I'm sure there are very many of you in the room that are already contributing to kind of solving some of the challenges related to urban resilience from the Earth observation perspective. Here's a kind of, I suppose, a very general mapping of the contribution that EO can make, whether it's looking at the national level to understand how the impact of urban policies, or the trends and dynamics in relation to urban growth, or if it's at a very much more granular level, understanding the impact that climate and other natural hazards have on particular locations or groups within a city, or the contribution that EO can make to ensuring infrastructure is planned to be resilient to all sorts of shocks, both in the very short term, informing things like early warning systems, or longer term strategic plans and planning that all go towards making urbanization more or less sustainable. The other point, I suppose, that we often forget, at least within the EO community, is that it's not just this top-down view of advances in satellite sensors and information coming from space, but that actually there's a real growth and opportunity to empower communities themselves to be able to work with, capture data, understand their own risk and vulnerability through a range of sort of low cost and in situ sensors. So GEO, as I say, resilient cities is kind of our newest engagement priority. That said, it's been the primary instrument, I think, through which GEO organizes itself is the work program. Some of you I know are featured within our work program, and there's a long history of initiatives that are thinking about these challenges at the urban scale. Some of them are shown here, and And really what we are looking, as we look towards the future of geo, if you like, it's quite timely to be invited to speak today, because just as of yesterday, we launched our post-2025 work program, which is really where in the following 2 to 3 years, we are currently looking for proposals to speak to a range of thematics, and urban is very central to the design of the current work program. But I think the important distinction from those of you who are familiar with Geo's work is this move away from just providing data and information towards more operational services, and specifically the co-design and integration of a range of actors across the Earth observation value chain, from those kind of policy data needs that are set out in international policies, providers working at the kind of upstream end, operating satellites, capturing data through in situ sensors, to everyone in the middle who's processing, archiving, and then exploiting data through analytics and various forms of data fusion. And I mean, most importantly, really, and I think a central theme of the conference for the next few days is end users, and ensuring that these Earth observations tools and services really respond to the needs of end users, or anticipated end users. So there's a real focus in our current work program, or a call for proposals for our new work program. We want to see co-design and integration across the whole of the Earth observation value chain, and really, again, thinking about Dennis's earlier comments, thinking where the end user or the kind of human-centered needs sit within all of this. Geo, just an example, really. So something, again, that is a little new for Geo. We have a couple of new initiatives that the Geo Secretariat here in Geneva are incubating. The service here that I'll describe is something called the Global Heat Resilience Service, and I know we'll hear from colleagues in the following session around some initiatives around understanding urban heat exposure. But this is really an attempt by the Secretariat to look backwards a little bit to what's within the Geo work program, the types of research and some operational activities that already touch on this nexus area, really, of climate change, urbanization, and public health. And building on that, to say we think there's a real opportunity here for the Earth observation community to provide the kind of insight, knowledge that cities need in order to understand the scale and nature of risks in relation to extreme heat, but also some of the actions and investments that cities should take to try and manage those risks. So as we've been discussing this concept, if you like, over the last 2 years with a whole range of organizations, the UN family of organizations, the World Meteorological Organization, IPCC, but specifically going out and talking to cities or organizations that represent cities, like some of the city networks, C40 Cities, Resilient Cities Network, is really trying to almost kind of carve out the niche that we think the heat resilience service could play in providing that sort of very granular insight through maps, through graphs and charts, so any city in the world can understand their particular heat profile, if you like, and then insight that helps them understand what to do about it. So this is relatively new. We're sort of in fundraising mode at the moment for this project, but we were very pleased to have ESA's support actually earlier this year, where, having kind of scoped out what a heat resilience project might look like with an urban lens, we were then invited to provide a challenge for a hackathon on space and global health here in Geneva, where we essentially had the chance to test out some ideas, work with something like 20 hackers from all over the world to take some of the user requirements that we'd been discussing with cities and turn those into something approaching a functional prototype of a decision support tool with maps, with charts that helped us really explore some of the opportunities and constraints for combining and integrating various data sources, producing heat risk models, but also testing out some of the kind of software solutions, open source frameworks that help you kind of build and share interactive web applications. It was a very rapid 2-day experience, but actually very helpful for starting to, as I say, test some ideas and really reflect on how you implement the needs of the user in an Earth observation powered service. So more on this to come. As I say, we're currently packaging this and trying to raise some funds in order to basically move to a point where we prototype and test further with a range of city counterparts. Again, aligned with this idea that in order for Earth observation data, tools and services to be responsive to user needs, you really need those people involved from the beginning in the design of these services, just to test your assumptions on what you think it is that they need and how some of these tools will help them guide urban resilience, more sustainable types of urbanization. I'll leave it there for now. Just to say, if any of you found anything I said today interesting at all, please reach out. We have a couple of initiatives or mechanisms, I would say, for ensuring those interested in doing Earth observations in the urban context can better connect with the users. The primary one is the Resilient Cities and Human Settlements Working Group, which I co-chair, and we're looking for members both on the user side, so cities and their representative organizations, but also folks from the Earth observation community who are interested in meeting sort of 3 or 4 times a year to discuss how we can design these Earth observation services to achieve some urban resilience. Thanks, everyone.
Thank you, Martyn. Thank you. So we do have time for a quick question. Is there someone that has a question in the audience? Okay, so I do have a quick question for you, Martyn. I mean, from your direct experience, you've been working with several fields of applications of Earth observation. You're also working on different services and toolkits. And you're also in connection with a set of users and practitioners. In your opinion, which are the fields that are a bit missing Earth observation applications? Which are those, let's say, topics that are still not covered or not covered enough that the scientific community should, let's say, somehow focus on, because it's anyways some kind of priority from the user community?
It's a very good question, and it's probably quite hard to generalize, but I think generally my feeling is, I mean, climate risk data and information is always a gap, particularly thinking about some of the cities I've supported in the Global South. And that isn't always the absence of information or Earth observation powered data tools. It's often the discoverability of some of these things, or the lack of ability for users to integrate some of the amazing data and tools that's already out there into the sort of systems, policies, and processes that they have at the city level. So I think as a community, we could be doing a lot more to ensure that these tools are discoverable and that they're easy to use and simple, and that it's easy to integrate into, as I say, existing planning processes. So I'll leave it there, and perhaps others might reflect on that a little further.
Thank you, Martyn, once more. Thank you. Let me remind you also that we will have the demo area in the afternoon where we will have actually one presentation specifically on the toolkit that Martyn has introduced by Dennis and Monica. So you're welcome to learn a bit more there. Okay, so now we pass to our last speaker. I have the pleasure to introduce Professor Nieuwenhuijsen, who is the Director of Urban Planning, Environment and Health at IS Global Barcelona, and the Climate, Air Pollution, Nature and Urban Health Research Program, always at ISG Global Barcelona. He is a world-leading expert in environmental exposure assessment, epidemiology and health impact assessment with a strong focus and interest on healthy urban living. He has edited 8 books and co-authored more than 600 papers. Since 2018, he is among the Clarivat 1% highly cited scientists in the world, and in 2021, he was ranked as the #1 scientist in urban health. He leads the biannual Urban Transition Conference, and he is editor-in-chief of Environment International. In 2020 and 2021, he was the president of the International Society of Environmental Epidemiology. Today, he will be speaking to us about the health impacts of urban and transport planning, the role of air pollution, green space, heat, and noise. Welcome, Mark, and thank you.
Thank you so much, and it's a great pleasure to be here. Just let me explain, I'm coming from a public health background, quite different there. I'm, I think, in a way, a user of data that's been produced, and I hope to show you a little bit. So at the moment, we're trying to estimate what is the current health burden related to living in cities, and also what are some changes we should make to make cities healthier. I focus here more on showing what is the current health burden for our cities, but I'm happy to talk some other time about some of the interventions that could take place. And this is the general framework we're working in. We clearly see a relationship between urban design, behavior of people, how they get around the city, how this leads to environmental exposures and to disease and premature mortality. So we think, you know, depending how you design a city, depends how people get around. So if you design a city for cars, you get people to go by car, leads to air pollution, heat island effect, stress, lack of physical activity, what leads to disease, and then premature mortality, just to give you an idea. We've got this new project called UBD Policy Project. It's funded by the EU, where we try to estimate the health burden of current practices in cities. I mean, there are a number of different aims and objectives you can see here. I won't go into detail. I just want to focus on some of the results. As you know, with this European projects, you always have work packages working on different aspects of the project. And this is kind of the scheme what we have. One of the important aspects I would like to show is that we, as part of the work, we're doing reviews, and I'll show you some reviews we recently did, and also organize workshops, bringing together different stakeholders. Because as what I said, I come from a public health background, but to be honest, this is only a very little piece of all the work that's going on. And we would like to reach out to other stakeholders, other people working in there, to work together to come up with data to do the work that we're doing, but also come up with interventions and studies to make in cities to make them healthier. The data set we're working with is at the moment a data set of 1,000 cities in Europe. Our work focuses much on Europe. This is a data set based on boundaries produced by the JRC. And we use this because then it's easier to work with various things here. Also, for a number of cities, we've got more in-depth work where we go into cities, what kind of policies are being implemented in cities or could be implemented in cities to actually make them healthier. As what I said, we use a multi-sectorial, multi-stakeholder approach. We believe that we need to work with others, and that's why if you're interested in our work, I encourage you to work with us and provide data, and etc. But we always, in our workshops, also we try to invite a lot of people from the cities. So some of our recent work that has been published in working with the 1,000 cities, for example, showed that we get 166 premature deaths in these 1,000 cities every year because the current air pollution levels are above the new WHO guidelines, the World Health Organization guidelines. A lot of this is due to PM2.5, fine particulate exposure, almost 110,000 premature deaths each year. And then also the rest is due to nitrogen dioxide exposure, in particular coming from traffic. If you could reduce all the air pollution in cities, go below the WHO guidelines, you could prevent almost 200,000 premature deaths each year in these 1,000 cities. Also, as part of the work, we did a ranking where we find the highest burden of mortality related to PM2.5 and NO2. And top of the listing for PM2.5 are a couple of Italian cities in the north of Italy, Brescia and Bergamo, for example, where it's because of the circumstances there and what's happening. But we also see other cities in Czech Republic and Poland where there is still a lot of coal burning going on, what causes the high air pollution levels to PM2.5. On the other side, if you look at NO2, you get different cities that are often cities that are dominated by traffic, like Madrid, Antwerp, and also Turin, for example, which you see where they have the highest mortality burden related to air pollution. We also look at green space. We estimated that 60% of the population in our cities don't live in an area with sufficient green space, and that we could prevent up to 43,000 deaths each year if we increase green space in our cities. Again, there's a ranking. If you see cities like Brussels and Copenhagen, there is not enough green space and you get a higher mortality. Now, perhaps for you, some of this is surprising in a way, but and also where you see the cities, but often what we see is in the city center where people live, there is not enough green space and maybe quite a lot of green space around the city. Also, a city like Copenhagen, it has a lot of blue space and not as much green space. Furthermore, in our work, we see that 60 million people are exposed to noise levels that are harmful to their health. Noise is often a problem in cities. People don't like noise. It's not good for their health. And a lot of it is traffic-related noise and also to some extent related to trains, etc. The health burden, or the mortality burden is not as clear because the evidence for that is not as strong. Here you can see some of the cities where people are annoyed by the noise, where the levels are too high. And typically, I mean, you're in Rome at the moment, it's top of the list, followed by Paris and also Madrid. And people often, notice this as well. Then the other aspects, what we see in cities is the urban heat island effect. You're all familiar with it. I mean, where the city center is warmer than surrounding areas. We estimated that in 100 cities out of our data set, 4% of summer mortality is due to these urban heat island effects. And that if we could increase tree cover in those cities from currently 15% to 30%, we could reduce the average temperature in the cities by 1.3 degrees. And we could reduce the 1/3 of the premature deaths attributable to this heat island effects. So, I mean, here the message is, yes, heat kills us, and also there are solutions to reduce this mortality burden by making our cities greener. Oops, my presentation is stuck. The latest study, what we did was, I think also perhaps one of the most interesting, where we, in our 1,000 cities, we ask ourselves, what type of cities do we have in Europe? What kind of configuration do they have? What is the urban design? How is this related to environmental exposures, such as the urban heat island effect and nitrogen dioxide exposure? How is this related to CO2 emissions? And how is this related then to our mortality? So we try to put these different aspects together to come up with, you know, what would be a healthier city, a city with lower CO2 emissions and better environmental quality. In our analysis, we came up with 4 types of cities that we labeled. I must say it's a data-driven approach, what we used. What we labeled as, on the left side, a kind of compact city, what tends to be having a higher population density, of course, and also be smaller in size. And then on the right side, we call it the green low density cities, which tend to be much larger, lower in population density. And it's kind of a continuum between these 4 different types of cities that we could distinguish. When we looked at those cities, I mean, in particular, what we saw that there was a difference in traffic density between the cities, where in the compact city, you get a much higher traffic density, about 3-fold higher per square kilometer compared to the low density green city. What is in a way surprising, because, you know, for compact cities, you would think it would be actually much easier to walk, to cycle, use public transport and using the car, but still, because of the density we see, because of the density of the city, I mean, we can see also more traffic around per square kilometer. The advantage, though, of the compact city was that the CO2 emissions were almost half of those per capita, half of those of the green low density cities. So that was a very important aspect, and that's why we always, you know, suggest that we should have compact cities to reduce CO2 exposure. Unfortunately, also what we found was that the nitrogen dioxide exposure and the urban heat island effects were much larger in the compact cities compared to the other types of cities, and that there was also much less green space available for people in the compact city. Unfortunately, also what we saw that the mortality rate was 10-20% higher in the compact city compared to the green low density city. And as you can see, you know, thinking about this, I mean, then you think, the compact city is good for sustainability, so for CO2, but not actually for living. Now, what we also say that going into this is that the compact city needs more work. We need to reduce air pollution there. We need to introduce more measures to reduce air pollution. We need to reduce traffic density. We need to increase green space by, you know, taking away the asphalt that we have for cars and putting in more green space, for example, for the solutions. So we still say, you know, it's better to have compact cities than the green low density cities. And this is, of course, important for future city development. I mean, we can change our current cities, but still a lot of the urban infrastructure is being built, and we should take this into account, we believe. If you're interested in some of our work and the actual estimates of the mortality burden, you can go to our website, isglobalranking.org, where we get a lot of the data what we put on. I would like to highlight some of the recent publications that we came out that may be interesting to you for this audience. This is a review that we did looking at the nexus of urban form, transport, environment, and health. Particularly focusing on large city studies, so studies of more than 100 cities, to see what is the relationship between urban form, transport, environmental exposure, environmental quality, climate emission, CO2 emissions, and health. And I think this review is quite informative. And also, we suggested a roadmap for further work. I mean, and this I think may also fit with your kind of interest to see what is actually needed to do to make the work more informative. Finally, I'm doing a lecture, the Lancet lecture. In October, you're all welcome to attend. It's both online and in London, around climate crisis, cities and health, where I come up also similar to here, discuss some of the burden of disease and mortality related to our current cities, but also come up with solutions, how we can actually improve our cities to make them much healthier and also, you know, address the climate crisis as a result as well. Finally, this is our consortium. We've got a number of people, and you're always welcome to attend our workshops if you're interested in. Please visit our website, ubdpolicy.eu, for any further information. Thank you so much. And if you have data that you think could be useful for our city work, please get in contact with me. We're always looking for data. All the environmental data that we have, we get them because of people we work with that were provided. Remember, we only have the health data that we have and that we can work with. So we're always looking for more data. Thank you so much.
Thank you, Mark, for this unique perspective on urban health. We do have time for one question. Yes, Thomas. No, there's a microphone that's coming to you.
Thank you. So this is Thomas Kemper from Joint Research Center. Thank you for the presentation, because it connects very well, I think, also to yesterday's discussions where we said we have to turn all the information and data that we are generating into policy relevant information. I think you gave very good examples of that today. Then my question is more to the ranking of cities and the data you are collected that is now focusing on Europe. Are there any plans to expand this also to a global level so that we get not only the view of Europe but of what's happening in other parts of the world?
Personally, we're not doing this at the moment, and this is partly because of the resources. As you know, that it's not so easy to get funding. If we would have further funding, we would like to extend to other parts of the world. I mean, at the moment, we have this Horizon project, UBD Policy, that funds our work. We're looking for further funding. But there are other groups working on this as well. I must say, I mean, for example, Susan Annenberg, I mean, I think of Washington University, I mean, George Washington University, they're working on more on a global view of cities, particularly around air pollution. If you look at the review that I just showed you, I mean, there are some other examples of large-scale studies that are working on this. Now, the problem, of course, is that from a health perspective, the data on cities are not always available. I mean, we only could do this work, and we only started this work a few years ago because in Europe they were collecting data on mortality data on city level through the Urban Audit project, and that makes it possible to this kind of work. I mean, what we're also hoping for is getting data on disease burden, diseases in the cities, but there is no large database available for the 1,000 cities, and that makes it difficult. I mean, I must say there is a lot of data need for this work, because also, for example, if you look at transport data, there is no database available on simple things like transport mode share or the number of trips in these 1,000 cities. What is always surprising to me, because it's such a large driver of what's happening. On the other side, also, if you look, for example, there's no database on social economic status by neighborhood in those cities. Social economic status is also an important driver of health and many other things, but that's not available yet. And in Europe, we still have quite a lot of data. If you go to the rest of the world, there are many places where there's a real data lack, and so that makes it a bit more difficult.
So thank you, Mark, once more. And I would thank also all the three speakers all together. So with a last round of applause, thank you. So, sorry for being a bit late. We're running a bit late, but I think with the fact that we have this statement from Mark that 4% of mortality can be linked to urban heat island effect is actually a very key message to the next session. So the next session is on urban heat dynamics and soil sealing assessments for resilient planning. So they will be chaired by Claudia Barancelli and Efren Feliu-Torres, that I invite to come here. And yeah, wish you a good continuation of today. Thank you.
Super quick change with no break. Yeah, thank you everybody. Thank you to actually the previous speakers, as Francesca was saying. We have been hearing several times the issue of monitoring urban heat and urban heat island effects as one of the most sought after applications. So we hope that this session will really give everybody a good opportunity to have a look at ongoing research. With me, Efren Feliu-Torres, who is a climate change adaptation manager at Tecnalia, will help to keep a very strong focus on the application side, on the user side. So just a couple of words on how we have organized the session. I know it's a little bit challenging, but we hope to keep all the presentations in a row. After each presentation, Efren will help us to focus on a couple of main messages, and then we will have a final discussion at the end. So with this, first of all, I invite the speakers to stick to their 10 minutes. I know that you have a lot to say, and we are all eager to hear you, but we want also to have some open discussion, so please stick to the time available. And now I would like to leave the floor to Efren, just to give us a couple of words of introduction on really how we can go from the 20 terabytes per day to that specific product, that specific application that each user needs, and how do we do this, combining satellite imagery with also other data sources. So please, Efren, the floor is yours.
Now, okay. Thank you very much. Well, the intention of this introductory pitch is frame a little bit the discussion that we hope is generated after the 6 presentations of this session. As Claudia was saying, I'm managing the Climate Change Adaptation Group at Tecnalia. Tecnalia is a research and technology organization, and we are a little bit in between academia, private sector, and public authorities. We are involved in a lot of applied research projects, and some of them will be mentioned in this introduction, but also delivering services for private entities or public authorities in the field of climate change adaptation and resilience. And I'm going to show some examples with a small narrative linking these examples, finishing with some insights, hoping that they can provide a framework for discussion after the rest of the presentations. Okay. We can make use of single products, to say it somehow. And for example, this is a service providing projections of heat waves and for different cities, and intending to have a sense of the order of magnitude of the problem, how will increase or what is the trend over time. Building on this, we have also developed single products as land surface temperature in order to understand, well, if a city has or will increase the problems related to heat stress, what is the spatial distribution and how can we understand the territorial pattern of that challenge. But building on these single products for analysis, for diagnosis, we can also combine with other sources and try to inform decision making with more sophisticated products, to say it somehow. The one in the center having the analysis of land surface temperature is combined with census and cadastre data in order to inform about vulnerability and not only the hazard distribution. The other image is related to green roof potential developed in the CURE project, which, as a matter of fact, was combined also with other applications of the same project, addressing the urban heat island and the temperature stress distribution. Building on that same type of analysis, combining different sources, we are currently working with the EarthClim model in the city of Bilbao with a high-resolution temperature map, which is also combined with green infrastructure in order to inform decisions about urban regeneration and green infrastructure deployment. In this case, and linking it to some of the discussions yesterday, this is not only a static analysis. In this case, we will force the model incorporating urban interventions in order to understand the potential effectiveness of those interventions, and also allowing micro-scale modeling of those interventions in order to optimize the design. So from single products to combined sources and more sophisticated services that can inform decision making. This is just an example of the workflow with different information sources or data sources, the simplified workflow, and also the functionalities or the final information provided, and the combination with other applications in the framework of the CURE project. This is an example scaling up this type of analysis. In this case, one of the 4 impact chains analyzed for the real estate sector in Spain is heat stress, and how is that influencing or impacting in energy consumption in the real estate sector. And this is an analysis done at a Spanish level, in which you can, for a company, Beltis, which is informing financial sector or real estate sector about the evolution or the trend of climate change impacts in the sector. Those are images of the workflow and some of the outputs generated. And it's important that in this case we are combining, as you can see in one of the images, different data sources, national, European data sources, and this type of analysis are potentially scalable to European scale, as in the example of the ESPON climate analysis that we also did. Okay, some insights. There are challenges, and we are all aware about the integration of Earth observation or European Copernicus data with local or private data, and also about the interoperability across Copernicus services or different European or global data sources. I think that we need or we can aim generated transferable and scalable workflows and applications which could combine those different data sources and allowing the private sector or local entities to integrate their own data within these workflows and applications for a more sophisticated or better informed decision making, which could allow scenarios analysis, which could allow effectiveness assessment with tools like artificial intelligence, etc. For having the combination of these different resolution qualities and complementary information. And one last idea about these authoritative data sources, which could allow benchmarking and comparability across Europe, which is important for certain policy decision making, but also providing enough granularity as to integrate that local data and make decisions at local level too. And that could be all from my side. We have the different presentations and Claudia will be introducing them.
Thank you so much, ESRIN, and thank you for these final reflection points and, in a way, challenges. So now we have 6 speakers that will try to address these challenges, and I'm really looking forward to hearing from them. The first speaker that I want to invite to the stage is Nectarios Chrysoulakis. I apologize in advance for how to pronounce all your names. Is Director of Research at the Foundation for Research and Technology Hellas, Fourth, and today he will present us the URBISphere project. So Nectarios, the floor is yours for the next.
Thank you very much. Thank you. Good morning, everyone. As the corresponding principal investigator of URBISphere, I give you an overview of this project, which is a big project dealing with the coupling of dynamic cities and climate and funding by the European Research Council, ESRIN. Okay, cannot change. Is this one? No? Okay. So the objective of this project is to understand and forecast and project feedbacks between climate change and drivers of urban transportation, and exploring how urbanization, urban human behavior and technology changes in cities impact climate change, and how impacts on climate change influence urban populations, their vulnerability and adaptive capacity. So our main objective is to capture the complexity of urban dynamics and to change the way we represent cities in climate models. Of course, we focus on urban form. That means urban morphology, urban surface cover, and urban surface fabric. That means material. And this is the beauty of satellites that can reveal the different patterns. However, as you know, the majority of the urban surface is vertical, so we need to have different sensors to have also an image of the vertical facades. But also we need to have information about urban function, because people are moving, have mobility, and dynamic population, and emit CO2, also pollutants and aerosols, and see, for example, how we can use satellites to have information about total emission of NOx from top bombing Paris. However, we need to capture the inter-urban and intra-urban variability, so we need to put sensors in different places in the cities. So we need an objective way to stratify our observations and objective way to define our domains for the modeling. And we focus on characteristics of urban form. It is the building area fraction, the volume of area fraction, the vegetation fraction, and parameters related to urban function like the population density and anthropogenic flux. We calculate the radial decays from the center of the city, the periphery, and this is an example for Berlin. We can have define 3 rings and divide the cities to inner city, the outer city, and the rural area, as you can see. So based on these rings and methodologies recently published in BAMS, and we place the different sensors in according to these rings, and to have also calculate how this the urban form in these different rings affects the phenology, to put phenocams, and we can visit the presentation 119, the poster session this afternoon, to see how the different rings affect the end of the season and start of the season and all the phenology of the areas. And we put sensors related to observing the urban form and function, observing the urban emissions, and observing urban exposure. For example, we put ceilometers for the boundary layer height, and Doppler wheel lidars. We see how we put the different sensors in the city of Berlin and the different transects for the 3D emissions of the wind, and sun trackers for the different components of the radiation, scintillometers calculate the sun speed flux within the city, and standard flux towers measuring the different heat fluxes. And also, we have hyperspectral measurements with hyperspectral cameras on drones or the tripod, and we have more than 5,000 spectra in more than 250 clusters of urban materials, and we have developed an URBISphere spectral library, and of course we can see the nadir view and also have the different facades. I invite you tomorrow in the presentation 176 will be given by Yannis Lajanakis to see more details on this spectral library. And how we use this to calculate emissivity. We've published the methodology almost 10 years ago, but now an updated version will be presented later in this session in presentation 141 by Gina Mitraka. And also how we have different types of land cover, the angular land cover, and to better estimate the emissivity and the temperature. Again, the methodology of land cover is published some years ago, but in the poster session, Gina Mitraka will explain again how we use it to estimate emissivity. And also, we calculate, interesting to capture the different scales. This is thermal infrared campaign, different cities. And for example, you see we use thermal cameras, drones, airborne campaigns, and satellites. Again, this scale change, which is important for the upscaling based on what we discussed yesterday, we'll present it again in the poster session by Gina Mitraka. And tomorrow, in the very last session, Maria Golemi, in the paper 182, will discuss the 3D effects of the different thermal components. Some examples. This is, you can see retrieval data from the ceilometers. In this session, the blue circle, you see the ceilometer upwind, and this is the boundary layer over the city of Berlin, the different circles. And with red, you see above the city, which is higher, and with yellow, downwind, and you see how the urban plume is formed downwind and how we can measure it with the different instruments that we have put in the city to put the intra-environment variability. And based on this change, we can estimate the feedback and that the city has the boundary layer and then on the regional climate. For the function, this is a good example from Heraklion. We have two flux towers. You can see the footprint. The first is in the central business district, the second one in the residential area. And here is, maybe again not so, if you see here the central business district, and you have the red curve. This is a typical emission, CO2 emissions, so two maxima, the morning, the afternoon maximum. So the red curve is from the center, is mainly driven by transportation, whereas the blue curve is from the residential area, and it is related to the emissions from buildings. That's why it's higher during the winter months, because we have some, but we need more energy for heating. So based on this, forgot to say that we have two flux towers labeled by ICOS. So we run 2 out of 7 European flux towers. And based on this idea, we have a new project starting nearly 2025. It is the evolution of Copernicus Land Monitoring Service. Will incorporate CO2 emissions in these products of Copernicus Land Monitoring Service. So back to URBISphere, we have modeling, combine models of human exposure and vulnerability with urban surface models, with urban atmospheric models. And this is the example again from Berlin. You see how the different circles and rings help us to define the boundaries. And this is a nice figure from our recent publication in BAMS. You see the different domains of the models at 10 kilometers, 1.5 kilometer pixel, 300 meters, and in the city, 100 by 100 meter. How it is modeled, the different large surface processes, and the boundary line dynamics, and the urban plume. And you see how an urban pixel is modeled and observed, and a rural pixel is modeled and observed. But we need all this instrumentation to evaluate the models, because the evaluation is much more important. Some examples for the evaluation. You see for the different rings with different colors, the net radiation, the sensitivity flux, and the latent heat flux. And for example, you see the middle, the sensitivity flux, that the peak is in the green curve, and the dots is earlier in the rural area, and then later in the afternoon in the ring B, and later in the ring A, as is expected. And another example, you see that the wind is from north-east to southwest, as you see the image, how the model predicts the height of the boundary layer, and how the model agrees with observations. And again, some observations from Torpomi to see the urban plume formed based on the capture of NO2. And also some examples for comparison with land surface temperature for MODIS, for example, and for each separate grid, you see how the model and the observations are close or not close. For example, you see discrepancies in the nighttime observations and nighttime modeling in the rings A and B. And based on this, we focus also on vulnerability and adapting capacity, and analyze heat stress in Berlin. We have the resources to organize a survey, a household survey. So more than 10,000 questionnaires have been sent to Berlin citizens at selective pillars, and we have received more than 600 responses. And based on this, you see in the above figure that use the urban structure types for the buildings, and you see how they are distributed within the 3 rings of Berlin we have defined. And then from the questionnaires, we have estimated the perceived heat from the responses of the citizens of Berlin, and you see how this is in line with thermal discomfort in this that we measure, and you see how this is distributed with the city of Berlin. And furthermore, we can have indication when the elderly people live, and you see from this image that most of them live in the B1 and B2 rings, but there are a percentage that lives in high-rise buildings in ring A, and this build may have, yes, I'm finishing, lower vulnerability and adaptive capacity. That means the exposure heat decreases as we're moving out from the center of the city, but the vulnerability and adaptive capacity depends on the aging of people, on the urban surface structure, and we need to have detailed data to capture the intra-urban variability. So now we're working on Bristol, Paris, and Berlin, expanding Iraq and Stuttgart and other European cities, but we have global collaborations, and so this study will be upscaling at global scale, and the main outcomes related to the deeper understanding of this economic dynamics and human response to climate, extreme, and urban transformation. And we are in the middle of the project, but we're working to develop dynamic archetypes that link the different neighborhoods with the vulnerability, form, and function, and reflect the changes in urban development, socioeconomic change, and climate change. And finally, our plan is to provide evaluated scenarios of vulnerability and adaptive capacity and emerging risk from neighborhood to city scale. Thank you very much. So you can find more information on our website or contact any one of the PIs that you can see in this slide. Thank you very much.
Well, contribution about differentiating form and function and that dynamic factor which is important, and how different sensors or type of instrumental equipment can provide additional information to Earth observation in order to be able to implement modeling tools and develop scenarios for decision making. Thanks a lot.
It is important, if I may, the comment, just to evaluate the model, because the modeling is parameterized. We're using Earth observation data, but it's important to have all this kind of information, and not only the two-dimensional, the three-dimensional, to see also the local atmosphere and to evaluate the forecast of the models. Thank you.
Thank you.
Thank you so much, Nectarios. And speaking about the physical environment, our next presentation is going to provide us a deep dive on how to measure surface albedo and emissivity. And it's my pleasure to invite to the stage Jonathan Leon Tavares, who is researcher at VITO, which is a well-known independent Flemish research organization. Jonathan, the floor is yours.
There is no pointer, huh? No? Okay. Well, as many of you may have noticed, over the past year, we have experienced a concerning trend where each month seems to be the hottest on record. And in line with this, the European Environmental Agency, in its risk assessment report, identified heat stress on population as a major risk that demands urgent action. Failing to do so will incur in catastrophic consequences by mid-century. Locally, several research funding agencies, like the Belgian Science Policy Office, via its Stereo program, have been calling for innovative projects that leverage remote sensing data to support sustainable city initiatives. Our response to that was the surface albedo and emissivity for Belgian cities project, SUAVE for short. I am Jonathan Leon Tavares, the coordinator of the SUAVE project, which is a collaboration between the CESBio laboratory in France and VITO in Belgium. And the overall aim of this project is to make use of remote sensing data to calibrate a radiative digital twin of a Belgian city. In this case, we have used Brussels as a use case, and we hope that this calibrated radiative digital twin will allow us to support heat stress mitigation strategies. Well, as you know, several strategies to mitigate heat in cities have been proposed. However, here I only want to focus on those that they are denominated grey infrastructure, which involve the replacement of impervious surfaces like roofs, pavement, to counter the conventional heating effect. And you might ask, why does that work? Well, let me try to summarize that in an oversimplified way using this cartoon, where you can identify two roofs with different surface relative properties. On the left, we have a roof with a high surface albedo, high surface emissivity, and on the right, you see a dark color roof with low surface albedo, low surface emissivity. And as you can see, the dark color roof reflects very few solar radiation because it has a low surface albedo. And the solar radiation that is not reflected back to the sky will be absorbed, reprocessed by the surface, and released in the form of heat. However, the dark color roof cannot release that heat efficiently because it has a low surface emissivity, and contributing to the buildup of the heat throughout the day, and this is why this person cannot sleep under a hot roof. On the other hand, in the light-colored roof, most of solar radiation is reflected back to the sky, and the few solar radiation that is absorbed by the surface is released efficiently because it has a high surface emissivity. So that is clear. And at this point, one urban planner might be interested in applying this approach and might ask us, do you have surface albedo and surface emissivity measurements for each roof in Brussels? And the straight answer is no. And it is not feasible to go and measure these radiative properties for each roof in a metropolis like Brussels. But here is where the remote sensing component plays a fundamental role in the SUAVE project, where we want to address this following question. How can we efficiently exploit currently available remote sensing data to support heat stress mitigation strategies? Our answer to that is that, first of all, we need to fully decouple the spatial information that is provided by the sensor from its instrumental and experimental configuration. How do we do that? By making use of a 3D state-of-the-art radiative transfer code that is DART. The second question that we want to address is that, as many of you know, there are statistical relations that allow you to estimate high spatial resolution surface albedo from coarser products. And we want to review those statistical relations to find out whether the accuracy of the high spatial resolution surface albedo that you estimate from those relations can actually meet the accuracy needed for the urban climate boundary models. And the third question is more a practical one, when we ask ourselves whether we can put together a large and comprehensible catalog of surface albedo and surface emissivity for most surfaces in Brussels, so that an urban planner can decide which neighborhood, which district is more in need for a heat pollution mitigation intervention. How do we do that? Well, here you can see the diagram flow of the SUAVE project, where at the core, at the center, lies the 3D radiative transfer model that is DART, is our workhorse. And you can see that one input is a geometric urban database. We had access to this geometric urban database from the Brussels Environment website, and we had to do some post-processing and gather information about the location and sizes of the trees. And here you can get a glimpse of our geometric urban database that we have put together for Brussels. Then we pass it on to DART to simulate the radiative transfer regime in the shortwave and in the longwave domain. And as you can see, here you can get a glimpse of the simulation. On the left, you see the RGB image composed from these spectral channels in the visible range. And on the right, you see the corresponding thermal infrared image at 10 micron. Well, then the next step is to compare the simulations with the observations. And on the top, you see that I'm comparing the DART simulation with Sentinel-2 bottom of atmosphere, atmospherically corrected image. And at first glance, you can see that the colors, they don't look the same. And this is completely expected, because in my simulation, I assumed that all the roofs in Brussels were the same. And this obviously is not true. But here is where it comes, the main core development of the SUAVE project, where we exploit experience gained in the Urban Fluxes project to design and implement an inversion algorithm that will allow us to retrieve the 3D optical and thermal properties of a scene, and this case is Brussels. And at this point, we say that we had a calibrated radiative digital twin of Brussels, and we will be able to generate byproducts like a time series of software reflectance, surface albedo, shortwave net radiation, longwave net radiation, and of course, some of these products will be validated. The generation of the byproducts and their corresponding validation is still ongoing, but today I would like to show you some preliminary results from our inversion algorithm. And here you can see the Sentinel-2 image that we are using for the inversion and the initial DART simulation. As I said before, I mean, they don't look similar. The colors are quite different. And we pass this data to our inversion algorithm. And you see that after 7 iterations, the algorithm converges and is able to find the optical properties that when we simulate remote sensing images with DART, these simulations are very close to the observed ones, allowing us to have access to the optical properties per land cover type. In this case, we only assume 4 land cover types. And from the analysis, we found that the algorithm converges after 6-7 iterations. And currently, we had an issue in the retrieval of the optical properties for the vegetation in the blue channels. We are looking into that. For the thermal infrared inversion, here you can see on the top left the aster map temperature, the observed one that we use in this version, and then next to it, the DART temperature map that is simulated with DART after retrieving the temperature properties that you can see per land cover type on the top and the corresponding surface emissivity maps. And we noticed that the median relative error between the simulated images after retrieving the temperature properties and the observed images is less than median relative error, less than 5%. Well, summarizing, within SUAVE, we have implemented an inversion algorithm that allows us to retrieve the 3D optical and temperature properties of the surfaces in a scene. In this case, the scene is Brussels. And at this point, we can say that we have a calibrated radiative digital twin of Brussels that we found that when we simulate remote sensing images and compare them with the actual observations, we find a median relative error of 5%. As mentioned before, we are going to generate byproducts and validate those. This is still ongoing. Nevertheless, we believe that SUAVE will answer novel and urgent questions of how to efficiently use remote sensing images to support heat stress mitigation strategies. And we hope that with the large and comprehensive catalog of surface albedo and surface emissivity for most surfaces in Brussels, that the urban planners can pick up this catalog and will help them to underpin policy to protect the people from the heat stress. Well, if you would like to know more, please visit our website that we have put together, or just drop us a message. And well, there it is, surface albedo and emissivity for Belgian cities, SUAVE project. And from the project name, you can identify a geographical component, Belgian cities. However, since our methodology, our approach is based on robust physics, it can be applied to any other city worldwide, provided that you have a geometric urban database.
Thank you, Jonathan. I would like to call the attention on the first part of your intervention, where you highlighted the importance of albedo for indoor thermal stress. Mm-hmm. And it is important to take into account that decision-making in urban planning and urban development should be informed not only about the outdoor thermal stress and the urban heat island phenomena in the city, but also, importantly, about the indoor thermal stress, in which albedo plays an important
role. Yeah, sure. Mm-hmm.
Thank you, Jonathan. Also from my side, now we have seen what we can do if we cannot measure exactly what we want, in this case, each single roof in a city. And the next presentation is following this direction. And Zina Mitraka will tell us about a larger scale exploitation of satellite data for the assessment of urban surface temperatures. So again, how satellite imagery can help us when we cannot measure every single bit of our cities.
Thank you very much. Thanks for the introduction. Fortunately, the rain is slowing down, so you can hear me as well. So hello from my side. My name is Zina Mitraka. I work for the Remote Sensing Lab of Forth in Crete. And this is a small project that we had for a Living Planet Fellowship called EO for UTEMP. How is this changing? Next. Thank you. Fortunately, we have quite a lot of introduction here on why temperature is important, so I don't have to stress it again. It's critical. Nectarios was also presenting applications of Earth-observed temperatures for the URBISphere project. Probably all of us in this room, including the users that we were listening to yesterday, know that satellites are excellent for measuring, for observing the land surface temperature, but yet, although we have quite a lot of products out there from satellite sensors, besides the trade-off between the temporal and the spatial resolution that's soon to be changed with the upcoming sensors, first from the French Space Agency with the Indian one, and then ESA and NASA are following, we have the challenges that the previous presentation was very nicely posing also of the three-dimensional urban surface and the different and the very much varying materials of the surface cover. So what this project did was delivering better algorithms specifically designed for the cities in order to get the more accurate, more detailed, and more frequent in time land surface temperatures, or how you will be listening and seeing me saying urban surface temperatures, using multi-temporal, multi-scale, multi-sensor satellite data, a methodology that was validated with both in situ measurements and evaluated with independent satellite products. In terms of data, besides the thermal infrared data that we have in high spatial resolution, meaning Landsat, Aster, EcoStress-like, which is in the order of 100-meter spatial resolution. Don't get fooled about this 30-meter Landsat product. The sensor itself is a 90-meter spatial resolution, and it's a downscaled product, the 30-meter one. And then we have more frequent measurements with lower resolution sensors like Sentinel-3 and MODIS, that they are in 1 kilometer spatial resolution, but yet, I dare to say, more valuable for urban climate studies because we have many acquisitions per day. Besides those, we need to know the exact properties of the surface, as this previous presentation was showing, so it's important to know both what it is on surface cover, the materials and their properties, in order to get better representation of the surface temperatures. For that, in this project, we use some hyperspectral data for the materials. You will be showing a presentation tomorrow also from my colleague Yannis, and also optical data in different spatial resolutions. Besides that, we needed information on the 3D representation of the cities, and for that, we use products like the example you see up there, that's the London on the top. There are data out there on the building heights and the location of the trees, and in some cases, the height of the trees as well. In any case, there are data and there are more coming, let's say, but still they are not very close to what the reality is in terms of modeling. As you see, for example, that we have with airborne LiDAR data, which is not the case for all the cities around the world. Besides that, we also used spectral library data, meaning measurements inside the lab or outside the lab in the full spectrum. We also need the visible shortwave, but especially thermal infrared, multispectral for the emissivity, and then evaluation data from the flux tower in Heraklion, as Nectarios was also showing. There is a radiometer up there measuring long wave emission from which we get surface temperature. The methodology is what I call from a static algorithm and a downscaling algorithm. The static algorithm is using all this kind of data that I was just explaining, hyperspectral, optical, and thermal, to, as accurate as possible, describe the surface cover and the morphology. Once we have that in very good or as good as possible in terms of accuracy, but also in terms of detail, spatial detail, for our cities, then we can combine that one with emissivity information from spectral libraries, and that we can use with thermal measurements that we get from satellites to retrieve surface temperature. Again, this static methodology, I call it like that because it's applicable to sensors like Aster, EcoStress, and Landsat, but cannot give us frequent or daily surface temperature retrievals, and temperature is a fast-changing variable. So that's why we combine then this one with downscaling approaches that we published in the past, and used lower spatial resolution optical again data to update for the surface properties, and atmospheric information to correct for the atmospheric effects to get frequent time series of urban surface temperatures. Although I'll be talking about temperatures, it was important for this study was to get a good representation of the surface cover and morphology. So that was possible in some cases using detailed data for the digital terrain and the digital surface, and then very high spatial resolution satellite data like world view, for example, to get the building footprints and the tree footprints, and combining those two, we could have building heights and tree heights in good representation in some cases, as I said, from LiDAR data, but in cases that we didn't have, like for Heraklion, for example, from other sources, Copernicus data, for example. And on the other hand, other types of satellite imagery, like Sentinel-2, for example, from which we derived indices, for example, as the NDVI, from which we could use to assess the dynamic change of the surface, which, for example, for cities, throughout the year, I would say, that's basically what it was changing for the case of Heraklion, or for example for London, also to assess changes in other classes like buildings, paved surfaces, and so on. You will be seeing products and results both from Heraklion and London, mostly from Heraklion because that's where we had also the validation data from the Flux Tower, from the radiometer, and that's how product look like. This is 1 meter spatial resolution coming from worldview data, and you see original classes that we got from the worldview, and then you will be seeing tomorrow more on how Yannis derived these nice material maps for classes of roofing materials and paved surfaces materials that are actually very distinct in their behavior in the thermal infrared, which in practice means we need to specifically correct for their emissivity in order to get good temperature, surface temperature estimations from satellite data. So tomorrow noon, Yannis will tell you more on those maps. And then to use the information on the urban surface morphology, we did that implicitly, let's say, in the emissivity. This is what we call the sky view factor, and these are products for London and Heraklion there. The sky view factor is basically the proportion of sky visible from the ground, and that was implicitly used in this emissivity retrieval methodology. We use spectral library information like the ones you see there, for example, for urban materials on top and for different soils on the bottom. And then first approach that we did already a couple of years ago, as Nectarios said, was to use representative emissivities for a whole class and assign it to this class, but then a step further would improve the emissivity correction, including the surface morphology for the angular effect, including the sky view factor, as you see on the second equation. for which the emission by all facets within the field of view was taken into account. Again, the reflection by all facets of emission from the surrounding facets, and that leads to the propagation of emitted and reflected radiation with multiple reflections within a complex 3D urban environment. I wanted you to see how this looked like. That's an example for an area in London. I don't see that playing over there, but that was supposed to show you now products of lower spatial resolution. That's 20-meter changes in those fractions. We originally got it in 1-meter spatial resolution, then aggregated to 20 meters, retrieved the changes for Sentinel-2, information to get it dynamic, and then included information on the sensor geometry. I'm not sure you can see the differences in those two, but depending on the sensor geometry, we might have a larger or a smaller proportion of the walls included in our field of view. Thermal infrared sensor field of view. So for every different acquisitions, we have to change again our representation of the urban surface to include the correct proportion of walls, which you see in this example in the aggregated fractions product. On the left-hand side is more wall fraction, and on the right-hand side much less, which has a great impact on our temperature retrievals. And that's just one example, because I haven't been showing actually any temperature maps of how one of the products looks like. That's a temperature map for the area in Heraklion. There is wall fraction included in this example there. That's for the 6th of May 2022 daytime in Heraklion, and that's how the algorithm performs compared to the high-level product of eco-stress that it's derived from a physically based, I would dare to say, temperature emissivity separation algorithm, which makes it possible because it's a multispectral thermal infrared sensor. But then when we don't have so frequent or so detailed thermal infrared measurements, we need to do the downscaling algorithm in order to get time series like the ones you see the evaluation for in the right-hand side plots, where you see the evaluation of downscaled Sentinel-3 products in 100-meter spatial resolutions versus in situ urban surface temperature from the radiometer on top of the flux tower. And every dot you see over there, it's for one acquisition of the satellite, because that's when we had the corresponding retrieval. The algorithm did perform good in some cases, worse in some others. That's the worst case here, let's say, with 3 degrees difference compared to the in situ, but that's again acceptable for what we have so far. But hopefully with the next sensors coming up, like TRISNA, LSTM, and SBG, algorithms like this will help in get very good, accurate, and frequent LSTD retrievals, urban surface temperature retrievals, for all cities around the world. I don't need to say again how critical this is for urban climatology studies. And to summarize, this project explore the use of multiple Earth observation satellite data, and not only for monitoring the urban surface temperature from space, using and focusing most on detailing the urban surface and the urban form, and including information on the thermal sensor geometry. Combined with a downscaling algorithm, allowed for frequent, detailed urban surface temperature retrievals, and the method was evaluated against in situ and higher level products, LST, for the year of 2020. Nick already mentioned that, so I won't take more time. There is a poster, which is the follow-up of this work. This is ongoing work on the posters, and then my colleague Maria tomorrow is presenting how 3D surface temperature modeling will help us out in acquiring not only temperature for the viewing angle of our satellite sensors, but also try to assess it in 3D as the previous presentation as well for DART. Thank you very much, and sorry if I took more time.
Thank you, Sina. You've mentioned new variables like the sky view factor, also highlighting the importance of time series, the dynamic analysis, and in the end, developing algorithms in order to be able to transfer this approach and develop the same type of analysis in other cities. Thank you very much.
Thank you.
Thank you so much. And yes, I feel the difficulty of compress everything in a 10 minutes presentation. Myself, I feel like I'm in a candy store with all these, not just final products, but also intermediate products. And actually, what you mentioned about the downscaling techniques to have longer time series, that's a super critical issue that I feel should be highlighted. So thank you very much. And now it's my pleasure to invite to the stage our next speaker, Ifigenia Keramitsoglu, who is a research director of the Earth Observation at National Observatory of Athens. And with Ifigenia, we will move back to the user perspective. And the title of the presentation is very much telling, From Space to Life Saved. So Ifigenia, the floor is yours.
Thank you so much. Thank you so much. Good morning. It is my pleasure to be here today and present an ongoing work that is a digital twin for heat-related mortality risk assessment in urban areas. This is the work that is being conducted in the framework of a European project called Carmine, which I'm going to present very, very briefly. And it is a team effort with different teams and different disciplines in order to achieve these results that I'm going to show you. Again, it is very preliminary. The project just started in February. And just to set the scene, this project has to do with climate-resilient development pathways in metropolitan regions. So we're talking about metropolitan areas, and it is called Carmine. The goal is to help the metropolitan communities become more climate resilient by co-producing, and this is a key word for the project, co-producing knowledge-based tools, strategies, and plans for enhanced adaptation and mitigation actions. When we are talking about the tools and the solutions, there is actually a variety of those. One of them, and very relevant to the fact that in this audience we also have representatives from city authorities, is the living labs. And the living labs are now being organized. The first ones are going to take place by the end of the year. And this is where we sit down with, together with the authorities from the metropolitan regions to co-design, to listen to them, to validate existing strategies and policies in order to find where are the gaps and how we could help with some other tools, one of which I'm going to present today is the digital twins, hence I have highlighted this. The work the project has 7 pilot cities, and if you would like to learn more, please visit the website or contact me after in the break. So I will be talking a little bit about digital twins. I had put this slide at the beginning, before I came here, but then yesterday I heard about the terminology so much that I'm sure that all of you know about digital twins. Still, because there might be people in the audience who are not familiar with this new terminology, I'll just try to explain in layman's terms what it is about. So imagine a real-world system or process, and of course, the digital twin is its dynamic computerized counterpart. So this is it. And it is a digital replica. It is not a static model. And what really makes the difference with what we know as models until now is the fact that it receives and processes data in real time, so it gets new data as it is being acquired by satellite sensors, by in situ sensors, and it allows it to mimic the behavior, the changes, and the conditions of the physical counterpart. So a digital twin is like having a smart virtual companion providing insights, predictions, and the ability to have meaningful what-if scenarios. So the idea is to have a what-if scenario for the metropolitan area, for the case that I'm going to present to you, and find out what the impact will be. Here is a figure that I found that is extremely interesting and very much highlights the motivation behind the work that I will present to you that has to do with heat mortality. So in this publication that was published this year in the Lancet Public Health, you see this figure that shows both the geographical distribution of the aging of the population, hence the increase in the vulnerability, and at the other side, the warming. So you see that not all regions in Europe have to be treated in the same way, because climate change effects on health has regional differences. So the adaptation policies should also be framed locally. So in order to evaluate this, we need different kinds of data. Satellite data is one part of this, and regarding warming, you know, Earth observation data can be a valuable tool to evaluate this, but at the same time, we need other kind of data like socioeconomic data and demographic data. And you see these distinct differences in this figure. Going to the digital twin, the objective of the digital twin that we are developing is to have a heat health risk model, digital twin, that will be a human mortality estimator. It is based on artificial intelligence, and this is another key component for the digital twins, apart from the feed of real-time data. So we are using AI to accurately predict the occurrence of heat-related mortality. The idea here is to have two outputs. One is the long-term prediction for heat mortality based on you know, the predictions of climate change and climate adaptation and different policies, how these are going to impact the mortality due to heat. But at the same time, we are developing the digital twin in such a way that will be able to provide data during the heat season, and that is to manage an upcoming heat wave so that it will be at least somehow that the city authorities will be more prepared for what is going to come the following days, the next days. Here is the framework of the technical implementation, again with simple terms. So we start at the top with our data, and this has to do with the past data. So we try to learn from the past. And we use data from climate models, also reanalysis data, Copernicus, C3S data, demography and socioeconomic data, and these are our X's for the AI model. And then we have the Y, that is the mortality. We get this historical data, we use a percentage of those to train the model, and the rest to validate the model. Once we have the model somehow built, or at least a first version of the model, then we have the components that do this real-time feeding that I was referring to. So one of these components is the weather forecast. And this, of course, will give the output for for number 2, that is during the heat season management. Also, we will also get the climate models from a partner that has this expertise, and this is the Academy of Athens, and they're going to give us downscale data in order to run these scenarios. Again, Copernicus demography, socioeconomic, different policies, all these will eventually go in the model. But at the other side, you will also see other activities that I mentioned before. That is, for example, what will be the outcome from the living lab, and what will be the nature-based solutions that the stakeholders would like to test using the digital twin. This ultimately will lead to some potential differences in the policies, how these policies are going to impact the mortality in the long term. If we talk about the geographic expansion, we start with Athens metropolitan area, then we will move to Prague, where we will also include the air quality component. Then we go to Bucharest, and hopefully by that time we will be able to scale up to other cities, because transferability is a key element in the work that we are doing. Very briefly, how we want to build the DT heat. Again, I cannot stress more that this is work under construction. These are only the very first, not even results, I would say the first approach. And I'm going to be very fast because I realize that I'm running out of time. Okay, so we started with the mortality data. We followed with the distributed lag nonlinear model. We calculated the relative risk. The x-axis there shows the mean temperature, the daily mean temperature. From that, we estimated the deaths that are attributable to heat. And we saw some correlations between the number of deaths and different environmental factors. From that, we built the first version of deep learning neural network. That is the prediction of attributable deaths due to heat. We have already built the live component for the real-time feed with the weather forecast, so we see what happened the previous days, and we have the prediction for the next days. So with the model that you have seen, we are able to predict. Again, I stress this is preliminary results. This might change, but I just wanted to share with you the way that we are thinking in building that. And this is some of our predictions on top of historical ones. We have submitted a proposal to the second innovation challenge of Destination Earth, and we are happy to say that DT Heat Plus, because DT Heat is what I have shown until now, DT Heat Plus was this enhanced version of the digital twin, got the award for the most promising proposal. And I'm very happy to say that we are starting a collaboration with Destination Earth in order to actually build DT Heat on Destination Earth. And this could be, for example, a mock-up of how we would imagine the distribution of ambulances in the city based on the temperature distribution and the impact it's going to have on mortality. With this, I would like to finish. This is the team of different experts working on the topic. Carmine is the project, and if you would like to contact me, you can scan the QR code and find out about social media, emails, and contact details. Thank you so much for your attention.
Thanks, Iphigenia. Importantly, highlighting the vulnerability factors and the local factors. So we have to combine with that local data in order to be able to provide information for that decision making. Also, differentiating between the long-term planning in the city and the early warning system or the emergency response, which is also crucial, taking into account that we are able to assess effectiveness of interventions in order to reduce impacts and risk. Thank you very much.
Thank you.
Thank you also from my side. And we are running a little bit late. I am conscious of the fact that we are in between you and the coffee. So we will try to keep the time for the next two presentations, which will bring us to, of course, a connected but slightly different topic about soil sealing. So it's with pleasure that I invite to the stage Christophe Sagnier, who is a Senior Business Development Advisor at GAF, and who will present an harmonized pan-European time series for monitoring soil sealing. Christophe, the floor is yours.
Thank you very much. Good morning to you all. I'll try to make it quick. Yeah, we've got the 10 minutes. So my presentation is about the project that was conducted with colleagues from the European Environment Agency and the DG Regio and other colleagues from the European Topic Center. So it's really to produce a harmonized pan-European time series for monitoring soil sealing. And the main idea is that for European Union policies to be efficiently planned, there's a very strong need for a pan-continental, harmonized, multi-temporal, and highly detailed indicator on soil sealing. And what is more important, actually, is not so much the extent of soil sealing, although this is also an important factor, but it's actually how the sealed surfaces actually evolve through time. And there is actually a Copernicus land monitoring service that has been offering a data set on imperviousness, which is related to soil sealing, every 3 years since 2006. And it's really one of the main sort of data set that is being used as an input to this analysis. However, since 2018, the input for the production of this data set was switched from a mixed bag of data sources, I mean mainly Landsat, spots, the IRS data, to now almost exclusively Sentinel-2. And that actually caused quite a break in the time series in terms of change of spatial resolution from what was from 20 to 30 meters to now 10 meters. And so the change also means that you can't compare, the 2018 update to previous reference year. And the whole idea of this study is trying to develop a procedure which actually makes it possible to harmonize the whole time series. And just to illustrate that, if we look at these sort of example of the data set, I mean, the data set covers the whole of Europe. It's freely available on the landcopernicus.eu website. And but if you look at some of the details, it covers almost 6 million square kilometers across the whole of Europe. You see the different data set. There is on A, you see the data set from 2015, and then the update from 2018. And you see already there is considerably more sealed surfaces which are not sort of attributable to just a new built-up area, and they actually represent more sort of omission from the previous layers due to the improved resolution from Sentinel-2. And then there is another data set that is available, which is the Korean land cover. I mean, most of you probably knows the Korean land cover, but there is a new product called CLC Plus Backbone, which is a land cover data set at 10-meter resolution covering the whole of Europe. And there is an artificial class, and if you actually extract this artificial class, you see there's even more sealed surface which are being detected. And so that's just sort of poses a question on the characterization on one hand of the actual total area of sealed areas and also the change between 2015 and 18. So what we had, what we wanted to do is actually do a detailed analysis of these different data sets to see what were the pros and cons of using one of them and what was actually the magnitude of change to be expected. And to do that, we had actually a sample reference data set, which was developed as part of the Copernicus land monitoring validation exercise that actually was completed then, but is a new contract now started. And that was based on a stratified systematic sample based on the LUCAS. I mean, LUCAS is a survey that takes place between, well, it now varies, but it was 3 years, but now it's maybe going back to different. But in any case, it's based on a 2x2 kilometer grid across Europe, EU member states. And we use the LUCAS grid not just to use the data from LUCAS, but as a base for collecting sort of interpreted data from satellite imagery. And you see, so example of this primary sample unit, and with a 5x5 sort of kilometer, 5x5 grid within the primary sample unit of 1 hectare, and each of these points was actually visually interpreted based on high resolution imagery to characterize sort of sealed surfaces. So in total, we had 25,000 of those primary sample units across the whole of Europe, and we use this data as a reference. And the reason for having this number of primary sample units is to be able to characterize or to provide sort of data for at least the larger sort of grouping of countries across Europe. So just to give you an idea, I mean, there's a lot of figures there, I won't go through all of them, but just to give you an idea is that if you take the impervious degree sort of layer from the Copernicus Land Monitoring Service, on average, I mean, from 2026 to 2015, we've got just above sort of 80,000 square kilometers which are detected as sealed surface across Europe. When we move to 2018, there's a jump to nearly 110,000. However, and there's different counts depending on which, because sometimes there's clouds and so on, so we don't include all of the sample units in there, but in a sense, this is what we get. And then when we take the validation data and use some kind of a very simple direct estimation procedure, we basically see that in fact we expect the sealed areas across Europe to be more of the order of 160,000. So there is really an underestimation of before 2018 of nearly half of the area. So that's already is a bit of a problem. And we see the difference, is nearly sort of 70,000 square kilometers and just under 50,000 after 2018, which is still a lot. However, when we compare with the Copernicus land cover plus backbone sealed class, the difference is only 7,000, and in this case, the backbone product is slightly overestimating the area with 175,000. So that's just for the status area. If we look at the change, then we've got the, on the top, we've got the actual change data set, which gives us the a figure of about sort of just above between 2,000 and 3,000 square kilometers sort of expansion of sealed areas across Europe between 2006 and 2015. And suddenly, in between 15 and 18, there is a jump of 6,000 square kilometers. And if we look at the confidence interval, the difference with the upper band of the confidence intervals, we are quite a way out for the first time period. we're quite close between 2012 and 2015 and completely out for 15-18. So that's why we developed this harmonization approach where we saw that it seemed that the backbone data was quite a good basis to estimate sort of sealed areas, and we backtrack from that using the change layer or modified version of the change layer from 2015 and 2018 to account for this change in resolution. And I'll just, and that was, we used sort of calibration areas using the validation data set that we had, and each of these calibration areas is basically a combination of production units and the sort of environmental zones. Okay. And to reprocess the change layer from 2015 to 18, we used a discriminating function, which in this case was very simple. It was just a sort of a distance layer with the notion that new sealed areas tend to occur within the vicinity of existing sealed areas, and if it's sort of outside a certain distance, which can vary according to the local conditions, it's likely to be more of an omission from the previous time period. And you see an illustration on your right there, where you see some of the candidate sort of sealed areas versus the one that we consider to be more omission from the previous period. And when we do the some sort of validation matrix of this approach, we see that there is a much better results. I mean, again, I will not go into all the details, but you see, all the numbers in green there are much sort of closer to the reference data, and the harmonized impervious change data set is much closer to the reference data than the original sort of impervious data set, particularly if we exclude the areas which are outside the so-called sealed mask, so where with values greater than 0, then the difference is actually quite staggering. And we use different sort of metrics to do that, and again, that we can, I mean, for those interested, we can discuss that at a later stage. Now, if we look at the first graph that I was showing in terms of area, we see that now we are much closer. I mean, we are slightly still over it, in this case, no longer underestimating, slightly overestimating, but which we've got much more sort of consistent values if you look at the bottom line as compared to the original line above.
If you can,
yeah,
please.
I'll just complete, and we see that this is also the case when we look at the sort of spatially with a few differences, but in any case, 12 of the 22 times we are much closer with the harmonized data set. And if we look at a change, again, we are there sort of quite a major improvement, because we are within more or less for all 3 out of 4 period within the 95 confidence intervals of the reference data. So I'll just jump to the conclusion. Again, we have some differences spatially. Just to say that this data set provided much more sort of temporally and consistent time series. We've reduced the level of omission, and the level of commission errors slightly increased but remain low, and they kind of balance out with the omission, which means that's why the areas are much closer to reality. And you can apply this to the approach to other data sets to ensure you've got this sort of temporally consistent data. And I'll just also say that we've also got some recommendation for future production, putting a lot more emphasis on actually characterizing change rather than status, and with expected accuracy with balanced sort of emission and commission error requirement. And all of this is actually from a paper which is published, and you can actually find the link in there to actually getting access to the data itself, which is freely downloadable. With that, I thank you.
Thank you, Christophe. Well, the importance of differentiating the extent and the trend, to say it somehow, and analyzing the evolution with higher resolution, as you were saying, but importantly addressing that calibration and harmonization in order to understand over and under estimation. Thanks a lot.
Thank you so much, and thank you also for pointing out, maybe still in a slightly too technical way for our end users, but very interesting from my side, the difference between different data products and how important this is to actually build trust, because of course a final user will be facing the choice of using one or another data product on the same topic, what to use, what's best for the specific application. So in terms of communication, I see the challenge, and I think it's actually needed, though, again, to build trust also in the user community. So thank you again. And with this, we are moving to our last speaker for this morning. It's my pleasure to invite to the stage Walter De Simon from Planetech Italia, who will tell us about the ULYSSES project, which is an ESA project. So I'm happy to close the morning with this. The floor is yours.
Thank you for the introduction. Good morning, everyone. I'm Walter De Simone, as I said, from Planetech Italia. I'm here to present the project Soil Sealing Assessment and Monitoring of the Mediterranean Coastal Area, also called the ULYSSES project. The ULYSSES project is an ESA initiative under the EU Science for Society MED program, with a phase one running from 2020 to 2022, and a phase two running from 2023 to 2024, including a possible extension in 2024. The main product of this project is the soil sealing degree map, and focusing on the Mediterranean basin with a 20-kilometer coastal strip. Country covered in the phase two include Italy, France, Spain, and Greece. The project partners are Planetech Italia as a prime, ISPRA, and CLS. Oh, skip. A brief introduction about the coastal region. These coastal regions are vital to Europe's economy, housing 40% of the UA population and generating 40% of the US gross domestic product. However, they face significant pressures from human activities and climate change, resulting in habitat loss, pollution, and coastal erosion. Effective management in this zone is crucial for balancing the development with the preservation of healthy ecosystems and the related ecosystem services like water retention, local climate regulation, soil habitats, and biodiversity of soil. The Mediterranean coast span to 22 countries with about 46,000 kilometers of coastline and a population around 500 million people. It's a critical area for climate change impact. It's one of the main climate change hotspots, and due to the water scarcity, dense economic activities in the coastal areas, and agricultural reliance. The region is also crucial for global shipping, with 1/3 of the world merchant shipping passing through annually. Sorry. Soil sealings, a definition about soil sealing. Soil sealing refers to the permanent covering of soil with impermeable materials, causing the loss of soil and its ecosystem services. As you can see in the bounding box on the right, globally, 17 hectares of the soil are sealed every minute due to expanding infrastructure. And in Italy, soil loss reached over 21 hectares per day in 2022, in the highest in the 11 years. Soil sealing exacerbates climate change impacts by reducing vegetated areas, increasing heat islands, fragmenting habitats, and elevating energy consumption. The ULYSSES project provides vital data for policymakers and researchers to address these challenges and improve coastal resilience. The phase 2, exploiting the large volume of the EU data made available by Copernicus, we use Sentinel-2. In 2004, the product will be extended to Italy, France, Spain, and Greece, as I said. The maps offer the principal product is the soil sealing map with the imperviousness degree, sealed surface percentage per pixel. And these maps offer details of the imperviousness degree, providing a long-time series data from 2018 to 2024 with the spatial resolution of 10 meters. In the phase 2, as I said, we have an extension at the country level and only for the time series. For the Mediterranean basin, we have a layer for the year 2023 and the year 2022. And a full coverage of the country, Greece, Italy, France, and Spain, with from the 2018 to 2024. The product of the ULYSSES project include a GeoTIFF raster with color table and associated metadata in XML file. They aims for over 90% overall accuracy with both producer and user accuracy target set at 85%. The ULYSSES project provides multiple layer data and is comparable with other imperviousness layer data, like imperviousness density from Copernicus and the global human settlement layer. And the implementation, the project uses Kubernetes architecture to manage its data processing. A master node manages the cluster while worker nodes run applications. Processing pipeline are organized in pods, which are a collection of containers, fundamentally. Here we can see an example of a screenshot of the geoportal dedicated to the product for the exploitation of the product. Here we can explore the data from the country point of view or a regional point of view and explore all the year analyzed. And to access to this geoportal, we can visit the project website. For more information, you can contact the team of ULYSSES or visit the same website or the social media. For conclusion, ongoing and upcoming demonstrations include a dedicated meeting in Athens on September 19, 2024, and an event at Ecomondo in Rimini, Ecomondo Conference, in November 2024. And thank you for the attention.
Thank you, Simone. Addressing specifically the coastal area with the high population density in the Mediterranean, it is important, and the perspective of understanding ecosystem services and the link with climate change impacts, among others, with urban heat island and temperature is, I understand, an important contribution in the framework of the session. Thank you very much.
Thank you.
So conscious of time, but we still have our speakers here with us. So I'm looking at the audience. If there are burning questions, comments, reflections that you would like to share with all of us before we join the coffee break, I think we still have time for a couple of those. Coffee need is too strong. I know we have one in the front.
Thanks to all the presenters, and it's not so much a question, but maybe a comment and something to consider for the next sessions, because also the purpose of the conference is to understand how these solutions can be scaled up so that they are used more. So maybe also in the further discussions that we'll have for the speakers, it would be interesting for them to reflect on the scalability potential, or what are the limitations or the conditions for this to reach more. Because what I observed, and yesterday I posed some questions to you as audience, and actually today I did find some answers on especially soil sealing and the cooling, measuring the cooling from vegetation. And I would need to understand more, but my question is again, is there a potential for this to be used by others and tailored to their needs? And this is basically the nut we have to crack. And yeah, so maybe it's just an invitation to the next presentation to have this thinking in mind and reflect on it. But thank you very much for the insights, and it was extremely interesting. Yeah.
Thank you so much. And if there are no further questions, I think many speakers actually also have a poster in the poster area, and of course there will be around to answer your maybe specific questions. I thank you all once again. Thank you for bearing with us, and I think now we can break for coffee, and Francesca has some communications.
Yes, we reconvene at 12:10 since we've gone a bit longer. Okay, have a nice coffee. Thank you. Everyone, can you start taking your seat so we don't go too late with time? Please take a seat so we can reconvene. Otherwise, we'll be late for lunch, huh? You better run. Okay, I think you can start taking the word.
Good afternoon, everyone. Is everybody back in the room? Can you hear me? Hello. Yes. Yes, it's all there. Yes, yes, perfect. No problem. Okay, I think we can make a start now, unless you want to be late for lunch. I think I'll make a start now. Welcome you all to session number 2 on urban air quality, mobility, safety management, and monitoring. And it's going to be a really packed presentation today. We have 6 people presenting. To introduce myself, I'm Kavita Muthu. I am co-chairing the session along with Olivier.
Yes.
So, yeah.
So I'm Olivier Sanchez. I'm head of the emission and modeling team in AirParif. So AirParif is an independent regional association for air quality monitoring in Île-de-France region, which is the Paris region. And AirParif is accredited by the French Ministry of Environment, and it's funded by the state, local authorities, and the economic partners. So in my department, as we deal with emission data, modeling at different scales, from regional to local scales, the department has been developing strong collaborations with research institutes for a long time. And in the framework of our mission, we provide an operational link between research institutes, decision makers, and the public. With regard to Earth observation, we have been using So with regard to Earth observation, we have been using those for a long time. We use data from the Copernicus monitoring service as boundary conditions or as models for our own ensemble forecasting system. We use meteorological data from NCEP that use as initial data JDAS system, the Global Data Assimilation System. For emissions, we use agri-forecast data based on crop field forecasting system from the Copernicus Global Land Service. We use Tree Forest Atlas from GRC for biogenic emission calculations. We use MODIS data as vegetation fraction. I would talk right now on one specific tool that is really important for our monitoring mission. This is the emission inventory, which is a key tool for public policies. It not only feeds models, but are used to inform public and decision makers about the quantities of pollutants that are emitted in the atmosphere. They are used to test scenarios for reducing pollutant emissions. They participate in the assessment and monitoring of regional and local regulatory plans, the Atmosphere Protection Plan, or territorial climate, air, energy plans. That is the reason that we coordinate one specific project, which is the SENSA project, which is funded by the Agency for Environment and Energy Management for France. The SENSA project aims to build an operational integrated system for monitoring NOx emissions using satellite imagery of tropospheric NO2 columns from TROPOMI. This operational system will be based on the high resolution emission inventory that we're currently building regularly. The Copernicus TROPOMI data, and it will rely on our regional modeling system and for sure on in situ data. It will enable AirParif to monitor NOx emissions by major sector in near real time on that fine temporal resolution. We hope for quarterly or monthly, or even monthly resolution. This unique data will make it possible for us to update the regional emission inventory in near real time and to assess the impact of public policies on NOx emissions. So this is the general background of our mission and why we are currently here in this conference.
Excellent. Thank you, sir. Thank you so much, Olivier. Very quickly introducing myself. As I said, I'm Kavita Muthu. I work in the ESA Business Application Space Solutions department, so mostly looking at what are the data we have and how that can be applied to the market sectors. And my particular focus is on smart cities applications. So we have a very good initiative called Space for Smart Cities Task Force, where we are working with the cities to understand what are the data needs and then how the companies can address their challenges. So we have worked in more than 10 countries, and we have more than 100 studies and projects running through, particularly on the urban development. And we have invested more than 15 million on this type of activities. So that's a very brief introduction. I'm very conscious about lunchtime as well, so I think I will now ask all the presenters to have their presentation ready as well. We have 6 presentations, 10 minutes each, And at about 7 minutes, I will try and show 3 minutes left for each of the speakers so they know they don't have much time or they will have to rush. I need to keep this, unfortunately. It's not a good idea to have something before lunchtime, so I'll try and minimize the gap between you and lunch. So to start with, I would like to invite Simonetta to present about TRIPS.
Okay. ESA 5G for LART bus program is a demonstration project to integrate advanced technologies like machine learning, deep learning, and UAV monitoring to address key challenges in urban safety. The project is developed as a consortium built from Data Reply, Center Reply, and NovaRecon. We, as Data Reply, trained and deployed machine learning and deep learning model and created the web app interface. So today I will deep dive in these features. Everything is done thanks to the support of our main end user, which is the city of Turin, which helped us thanks to its many offices like the Traffic Management Office, Turin Municipal Police, Road Maintenance, and City Cartography offices. They all provided us valuable data, and they provided us also the support to validate the features of TRIPS. Nowadays, TRIPS is in its pilot phase, and it will be ending in the beginning of November 2024. Okay, so TRIPS can be seen as a three-module platform. The first module is the pavement status assessment module, the one that helps the city to assess the road markings quality every 2 months in order to perform a preventive and predictive road maintenance using VHR satellite images, 50 centimeters resolution. The second module is the car accident risk forecasting module, so the one that provides a forecasting, a prediction for the next 5 days of the probability of car accidents for every area in the city center and also in the suburbs. The third module is the drone-based accident surveillance module, the one that is able to collect real-time accident images and, thanks to 5G technologies, transfer them to help prompt emergency response and comprehensive post-accident analysis. This third module, as we are currently in the pilot phase, cannot be shown due to confidentiality issues, but we will now step to explain how the first and the second modules have been worked. So the first module is the one that aimed to evaluate the road markings quality every 2 months. So we started by training a network trying to use as many patches, as many images as possible, so 50,000 images to extract the most meaningful features for the street using a supervised road segmentation task. Then we labeled ourselves 4,000 patches to detect objects on the street, with the idea in mind that road markings can be seen if the road is visible and not covered by obstacles like vehicles or vegetation. But through shadows, indeed, sometimes we can see through shadows. So we also trained a shadow detector to exploit the possibility to correct shadows on the streets, and we have done it using a neighborhood histogram matching technique only on the street portion of the image. Using these shadow-corrected images, we trained a visible road segmentation model. So, as I've already said, the idea is to extract only visible portions of streets where we can actually see the asphalt step. So, as an output mask, we can see that vehicles are like holes in the mask. Then, after that, we are actually able to see the visible portion of the road. We can perform and we can assess the road markings quality. And we labeled ourselves considering the idea of markings visibility. So if the marking is missing, if the markings is present but not clearly visible, or clearly visible. At this point, we tried two different approaches that can have its narrow limitations. But now we are working with the Turing offices to understand which approach is better and it is possible to adapt to their needs. The second module instead is the module that addresses the probability of car crashes. And with the Turin Municipal Police, we understood that the main reasons of car crashes are high speed and reckless driving. So we used 5 macro features like street feature, accident history, traffic data, temporal data, and weather data to train a forecasting machine learning model. Even if the dataset was highly unbalanced, 98% versus 2% of positive samples. But we were able, using some techniques, to reach the 95% of accuracy. So let's now take a look at our platform, which starts with a login page. And our platform is entirely built on AWS platform, so it's a cloud application. We start by seeing the map of Turin with color-coded streets, green, yellow, red, and blue. And we are able to inspect the last acquisition, the last image acquired, in order to help correct the classification of the model and to understand if the blue parts, which are the unclassified parts, the parts of the street that for the latest acquisition the model was not able to correctly address, we can actually improve the classification by correcting it, like an active learning approach. Then the second module, it's the car accident forecasting risk module. So we will select the day that we want to analyze and the time slot that we are interested in. And we see that also the map has only 3 colors in this case. And we can inspect each area with their features like minimum lanes and the width of the street. So by now, we are still ending this project by trying to validating markings classification and trying to understand if there is any correlation between markings quality and accident risk. And also we need to label more images because to address this specific task, 4,000 images were really not enough. And in our next future, we are working on developing additional features in the framework of feasibility is a project to river monitoring. So we are going to map river banks erosion and monitor urban flood risk. And with the idea in mind to build a robust smart city platform. And because of that, we are always open to work with additional end users and to understand how we can adapt our solution to different cities in Italy and in Europe. So thanks for your attention, and You can
Perfect. You get more brownie points for keeping it to 10 minutes. Excellent. So can we have Robin on stage for the next presentation?
Hi everyone, my name's Robin Workman. I work for Transport Research Laboratory in UK, and I'm going to talk about measuring unpaved road condition from satellite imagery. So just to define the problem to start with, 58% of the population in low-income countries live in rural areas, and 66% of those don't have access to all-season roads. And we found that 53% of roads in Africa are unpaved. So that's important to understand. Even though this research is based on rural areas, there's lots of unpaved roads in urban areas as well, so the technology is certainly applicable to that. So we know that rural transport is a key development factor in economic growth and poverty reduction, but we also know we're not maintaining the roads to enable that growth and improvement in livelihoods. So seems to be okay. So to understand the problem a little bit more, we consulted engineers in 35 different countries. We found that 77% don't carry out surveys, condition surveys of the roads of specified frequency. 65% rely on visual, subjective surveys only, and most don't do their surveys at a consistent time of year. So we're looking at really an assessment of good, fair, poor type assessment of the roads, which is really important in terms of understanding and planning the maintenance of your roads. So this graph here, you can see the dotted line is if you had no maintenance at all, and it's actually much more expensive than maintaining roads on a regular basis. So we've done this research for a few years now. It started off in Africa under a couple of different donor projects, and that was done using manual assessment of the roads. And then we moved on to use machine learning and apply that. This is a self-funded project. To apply machine learning to make it more efficient. And then we got good results from that, but it was expensive. So the high resolution imagery we're using as Pleiades was expensive. So we tried to trial it on lower resolution, see if we could save costs. And that's what led on to the ESA project now. So you can see here the resolutions in blue and the costs in orange. And there's a sort of a sweet spot in the middle there where you actually get a big reduction in cost, and the resolution it doesn't go down too much. So we want to try and work on that. And so the three resolutions we used in this research were basically Pleiades at 3.3 meters, then Satellogic Super and Vision 1 at 0.87 meters. The process we used was to firstly understand what the Roads Authority needs in terms of their road condition assessments. So define their requirements, how often they needed, what type of data they needed, and then to acquire the imagery, and create tiles and label tiles, and I'll go into that in a little bit more in a moment. And then we had to ground truth an area for training of the machine learning. In this case, we used Madagascar and Malawi as our trial countries. We used a relatively small area in those countries, and that applied to the different types of roads, different maintenance regimes in each country. And then we used the machine learning models you can see for the classical models we used in this case. We did try CNNs as well. One of the outputs of this project was a plugin for QGIS that allows you to create the tiles for machine learning training. So based on the center line of the road, we were able to identify areas and then cut out those areas, and that leads to the tiles which are input into the machine learning model. And we had between 20 and 30,000 tiles for each country. And you can see the different types of surfaces there. So it's basically trying to distinguish between a good condition road and a fair and a poor condition road based on the texture of the surface. In terms of the results, the accuracies for Madagascar were quite good for the high resolution. As we expected, they drop off for the medium and low resolution. So it's really a case of whether that's good enough for the local roads authority to assess their condition, and that depends on lots of different factors. For Malawi, the results were lower overall, but actually a smaller difference between the resolutions, which was encouraging. We also did a binary analysis. So in Madagascar, they pave some of their more vulnerable areas using cobblestone, but they don't have a record of those surfaces. So we try to compare, to try to predict which areas were cobblestone and which areas were unsurfaced. And you can see we got, as you can expect, but seeing the different surface types, quite a high accuracy for those at all resolutions, really. However, because the sample size for the cobblestones was quite small, there was a lower accuracy in terms of the recall metric for cobblestones. And this is the overall results. You can see the accuracy there in blue, and then a few more details of the other accuracies. So a key factor in this was looking at the cost and benefits and which resolutions were most appropriate. So we developed an index for this where we looked at the resolution and the accuracy we found and tried to make some predictions there. So if you just take the resolution against cost, then actually the high resolution is potentially more cost effective. But if you look at the accuracy, you can find that the lower resolutions, because they get a reasonable accuracy but it's much lower cost, then they do show to be more cost effective. Although there's a lot of variables in this, and because we haven't scaled it to a full country study, then there's a lot of predictions and estimates included in that. So thinking about the ways forwards, so we're going to publish a paper on this and continue to refine the models under our own steam and explore and define what use cases there are for this technology in different countries. We're talking to African Development Bank about scaling up and doing a trial country at a whole country level or even a state level, and then our aim is to develop a commercial product or a service for this. We're planning on, we have a road asset management system software that we have, and we're planning on incorporating this as a module into that as well. So we are committed to this. Our company, Transport Research Laboratory, we developed we invented the zebra crossing more than 70 years ago, and that's been pretty successful worldwide. So we're hoping we can replicate that success with this. Thank you.
Thank you so much. Again, on the dot, so we're doing really well on time. So from the urban safety management, we now jump on to the urban air quality. So I would like to call on Davide to present, please.
Thank you. Good morning, everyone. I'm Davide De Santis from Tor Vergata University of Rome, and we'll talk about the primary project. But before, let me introduce the primary team, which include... okay, sorry. Which include many entities, Tor Vergata University of Rome, of course, L'Aquila University, 2 institutes of CNR, and CERCO, and the Italian Space Agency, who actually supported this project. Primary stands for PRISMA, for monitoring air quality, and indeed, the main scientific goal of the project is to explore the use of PRISMA data, which is an hyperspectral mission from the Italian Space Agency, and to provide qualitative and quantitative information about atmospheric particulate matter and in particular the speciation of the particulate matter. Very briefly, the roadmap of the project included the generation of statistically significant atmospheric profile, taking data from the CAMS atmospheric monitoring service, and to generate PRISMA data simulated, in particular using the FlexOD post-processing tool and the Liberating radiative transfer model. Then we use this simulated data set to be the training data set of AI-based module, in particular neural network, that then we apply to real satellite data. And we were able to provide aerosol product based from the level 1 of the PRISMA hyperspectral data. And one very important aspect of this project was the test and validation that we were able to perform with ground and aerial measurements for our product. General idea for the data set generation, we consider the global atmospheric composition monitoring service, the global atmospheric composition data set from CAMS, which give us the component that you can see on the left-hand side of the slide. And with this data, we can give this data to the input to FlexOD tool. And this tool give us optical properties and atmospheric profiles, which are the input for the radiative transfer model, which is Libratran. We properly set the parameter to give us the PRISMA-like radiances, and with this, we were able to build a Python end-to-end generation simulated chain that we use to generate our data set. But first of all, an important aspect of the project was also to compare the data that we use from the CAMS atmospheric composition forecast data set, and we compare with the Spartan network, which actually include instruments around the globe, which are able to provide speciated information on the PM2.5 in different species, which are actually the same that we consider in our project. And we detect that there is a bit of an overestimation on the organic matter. And in the framework of our project, we were able to provide a correction factor in order to obtain then a distribution that was more aligned with in-situ measurement. And together with the PI of this data set in CAMS, we recently published a paper on this. So if you are interested on this additional validation CAMS dataset, I invite you to scan the QR code and you can find the paper online. With this configuration, we produce our dataset considering up to 150 sites, considering main cities in Italy and in Europe. And we extracted data for the entire 2022 from CAMS, in particular 3 days per month. And considering different geometries of acquisition and surface albedo as input, from our chain, we produce more than 50,000 examples that consist in our training data set. With this training data set, we then used to train a neural network that we were properly designed, considering as input actually 26 compressed component, so principal component from the original hyperspectral vector, which consists of 240 bands. And to compress this information, to optimize the performance of our algorithm, we use both linear principal component analysis and nonlinear principal component analysis through, in this case, an autoencoder. And for the sake of time, I will skip this part that we are publishing a paper on this. And together with this 26 input, we had very important information from Lancover that we were able to obtain, considering K-means unsupervised classification, exploit the HLS dataset, and then we provide our own classification starting from the PRISMA level 1 data. And together with land cover and the 26 component, we add ancillary information like latitude and geometries of acquisition. And in output, as you can see, we can provide particulate matter as total column aerosol and different species, and 4 aerosol of thickness at 4 different wavelengths. This is a result, an example of our results of our project, in particular for the aerosol thickness of 5 and 15 nanometer. And for the date that is 15th of October 2022, that we will consider in this presentation to show you an example of our validation, which actually is one of the core part of the project through, in particular, 2 field campaigns, one in Rome in 2022 and one in Milan in 2023, combined with different ground-based measurements and also other aerial measurements that we will see in a moment. And basically, on the left-hand side of the slide, you can see the result in terms of total column particular matter in gram per square meter. And on the right-hand side, the overpass of PRISMA given by the this sailometer from ULYSSES. And we, with a technique that was recently published in a paper, we were able to compare the vertical resolved particulate matter estimated from the ground-based measurement with what we obtained from our neural network. And we see that there is a bit of overestimation in the total particulate matter, but and we ask why. And actually, looking at in the speciation, there is a very interesting part that is the fact that considering the integration of, for example, on the left-hand side, we have the black carbon component that's very important for health correlation, of course. And we see that the measure provided from the algorithm and from the in situ values are aligned. It's well quantified, and this happened also for the other species, except for the dust component, where there is an overestimation, but it's also only for dust, and we already are working to fix it. And a very important aspect also to note is the different spatial feature and the distribution of value between the black carbon, where the higher concentration are over the city center as we can expect it, and on the other side we can see how the dust is more distributed in the rural areas. A very important point that I would like to underline is an additional field campaign for the validation, where we use a drone and we design our own equipment to be on board of an UAV and to measure different quantities and to have the possibility to also obtain quantitative information on particulate matter. As for example, in this case, we can see black carbon vertical profile, starting from early in the morning on the left, where you can see stratification and different concentration of the black carbon distributed also in between fossil fuels contribution and biomass burning. And you can see also higher concentration due to rush hour in the morning to go to work, to school. And we, in this case, we are close to the highway. And at the same time, in time, you see during the morning that then the stratification going to, we lose the stratification. There is, as we expected, a more homogeneous profiles, and this was a very interesting preliminary result from this campaign. Last but not least, we were able to set up a collocation and matchup tool to have the possibility to map data from passes from PRISMA and other satellites in a perspective of data fusion for our algorithm with our EO mission, and to store our product with in-situ measurement for the purpose of validation. A few take-up messages to recap. We generate an end-to-end PRISMA-like chain to obtain our data set, and we perform in-situ measurement to validate the output of our neural network product. The results are aligned with ground measurements, except for dust, but we are working on it and we are fixing it, this problem. And considering an uncertainty up to 5% of PRISMA measurement, the propagation of error in PRISMA in primary product is about 3%. And very fast, the next step will be the refinement of the algorithm, continue with the drones and the extended validation, data fusion with other missions, in particular considering polar emitters, and for example, use other spectral data as, for example, the data provided by HAMAP. And with this, I conclude and thank you for your attention.
Thank you so much, David. Just 1 minute over, I think. That's fine. We are halfway through, so I would like to now call on Bas to present about the CityAir, again, air quality.
Okay, good afternoon, everybody. Thank you for giving me the opportunity to give a presentation about the project CityAir. It's an ESA project from a rather small consortium. It's me, Bas Meiling, from the Dutch Meteorological Institute, together with my colleagues from NILU in Norway, in Oslo, and my colleagues from the Spanish company Lobelia. So, it's all about using tropomy data for better application for monitoring urban air quality, and we are shifting from PM, from the previous talk, now to NO2, nitrogen dioxide, because this is the thing which we can measure with tropomy so well. So the point is in urban air quality that the best way to monitor it would probably be through reference instruments, but the instruments have as a advantage that they are very accurate, but as a disadvantage that they're very expensive, both in buying them and maintaining them. And this is why you have all these alternative ways of measuring urban air quality. For instance, you have many initiatives lately about measuring air quality with low-cost sensors. So this would afford a more dense network, but at the cost of a higher inaccuracy. And then also you have the satellite possibility of measuring it. If you look at tropomy on Sentinel-5P, it's a polar orbiting satellite, so it overpasses only once a day, so you're missing basically the daily cycle of air quality. But it measures globally, so you have information everywhere. And you have, of course, modeling systems like CAMS, which is providing you a rather coarse idea of the air quality, current air quality in Europe with a 10-kilometer resolution. And you have also specified urban air quality models who could fill in the gaps theoretically. But as I see it, all these kinds of instruments for monitoring are complementary, so they all have their advantages and disadvantages. So the thing is how to combine them best to get the best results. But first focusing on the tropomy instruments. What you see here is a single overpass of tropomy on the left-hand side over the city of Madrid. That's the black outline. And maybe you can recall from the earlier talk by Mark this morning, Madrid is ranking 1 in urban air pollution related deaths considering NO2. So this is why it's so interesting to study it. But also you see, if you look at the retrievals, the observations of the instrument, you see that we are far away from what we actually want. That's on the right-hand side. You want to have ideally like hourly fields of NO2 within the cities with a high spatial resolution. And there are two problems, of course, with the satellite information, is that if the measurements are too coarse, typically about 5 by 5 kilometers, and we lack information about the exact height distribution of the air pollution. So we have to translate it to surface concentrations. So this is something we cannot do without the use of a model. And preferably, we want to have a model which is versatile, which we can apply from city to city. So we're not stuck to only one city and do a very good job over there, but we want to have like a kind of algorithm which we can copy to whatever city we're interested in. So in this attempt, I want to present you here a short overview of the Retina algorithm, which was actually built around the dispersion model of AirMod, which is from the EPA, the Environmental Protection Agency of the US. It's open source. But the thing is, if you build such a detailed urban air quality model, you need very detailed urban emissions. And this is information which you most of the time lack for all the cities you want to investigate. But fortunately, we can use proxies because we have a good idea of where those emissions are. And in most of the cities, especially in Europe, it's traffic related, for which we can use like the road network and the traffic volume as an emission proxy. And it's residential related for cooking, for instance, or heating. And for this, we can use population density as a good proxy for it. Okay, and if we calibrate this kind of, so the idea is by using these proxies, we still do not know how it translates 1 unit of proxy data to a certain amount of emissions. So Retina solves this problem by tuning the emission factors such that the observations best match the actual simulations. And we can do this either by ground observations with the reference network, for instance, or a low-cost network initiative, or from the space observations. And this is to show you that we are doing quite a good job in reproducing the space observations. You can see at the right-hand figures where under different conditions, you see different overpasses, again over Madrid, with different wind direction and different buildup of the plume. The urban air quality model, Retina, is quite good at reproducing the columns we are observing from space. So that gives us confidence that we are able to doing the opposite way around, using the mismatch between the simulation and observation from space to adjust the emission factors to improve the surface concentration which the model is simulating. So what you see here again, Madrid, it's a monthly average based on corrections made by Tropomi. Of course, you see the strong pollution gradients close to traffic arteries, the highways. You also see the green spot or the blue spot here, actually, the low concentration which are found in the local city park. So we are able to capture all these dynamics, and we can do this on an hourly level, which you can see on the right-hand side, where you can see the time series as it is compared to a reference network. And here you can see in a black line the real observations, and in the red line the observations as they are predicted by the observations of the satellite. But the best, as you can see here as well, the best results are actually obtained if you also have ground truth available. In this case, a network of 23 measurement stations who can also give you an idea of what the local air pollution is. Okay, and I told you that this is like a versatile system. So as an example, I give you applications on the different conditions for different cities. So for Warsaw also we are deriving these kinds of hourly maps based on daily updated satellite observations. For Sofia, the thing we did is that we used the local reference network, but we added a campaign of an NGO who sampled monthly averaged NO2 concentrations with Pamlin diffusion tubes. And we can use these measurements also to improve the validity of these kinds of maps. But this is all, this is like a short overview of the added value of satellite data, because they add value, but there are some limitations. So the real quality of this kind of work, I think, is in using the complementary of both space and both ground, if it's available, of course. Because the problem with Tropomi is that it misses the diurnal cycle. So as it only overpasses once a day, we cannot tell you exactly what the emissions are during the morning or the afternoon. But What I hope to show you is that it's perfect for cities with very limited ground truth, which are many cities in not only Europe but also in the global south. But this is not the only thing, because this is all science. It's pretty useless if people are not using it. So this is why we teamed up with Lobelia, and they are very good in making graphical user interfaces on top of these applications. It's called Lobelia Explore, and what I want to show you here is an animation of an application in Madrid, where we did a monthly reanalysis of a 5-year period based on tropomi information, and derived this street-to-street information of air pollution. And this is a demo which plays around with all the features which are currently implemented. So you can switch from color bars to get like a different idea, or you can browse through the different months to see the temporal evolution of air pollution. You can also compare 2 different periods with each other. So in this case, you see the lockdown period in Madrid in February 2020 with the year before, and play around and see where all the differences were. Of course, you can zoom in, you can click on a map, and you get like the time record of these monthly averages for a certain point, but also for a user-defined selected area. And this is all calculated on the fly based on the data set we pre-calculated. So, and this is the option where you can look at differences between 2 months. So you have all these kinds of tools to play around with and to get a better insight in what's really happening on a local scale, based on observations, both from space and from produced by the local authorities. It's a combination of both. And the last slide, before I finish my talk, is what we have to do right now in the CityAir project is generating a longer time series, as I already showed you for Madrid, but also for other cities we are showcasing, and in our case it's Rotterdam and Warsaw. At the same time, we are updating our code that we have like a more seamless implementation possible for other cities as well. So we want to be as independent as possible for local data sets. So we want to use open data, satellite-derived information, which is globally available, and move forward towards an open source code and build a community around it so people can contribute to it and see how they can implement it for their own application. And finally, we are preparing it for the long-awaited Sentinel-4 mission, which gives you similar data as Tropomi now, but only on an hourly basis. So this will better capture the diurnal cycle, and we have seen that the product will improve for. So I have to round up. More information, please talk to me, write to me, or talk to the people from Lobelia, because they're also present here at this meeting. And yeah. I hope to speak to you, to talk more about this in private. Okay, thank you.
Perfect. Thank you very much. I think that's 2 minutes overrun. Let's see what the other presenter has to do. Thank you. We'll have the question and answers at the end of all the presentation. So I will now call on Esther. And talking about air quality as well.
Okay. Hello, I'm Esther Pantaleo from the physics department of the University of Bari. And today I will talk about spatio-temporal imputation and bias correction of Sentinel-3 scene for intra-urban air quality assessment using deep learning. Okay, so this is the outline of my talk. I will first state the problem, then I will show some preliminary observation,
and I will go into the main topic, which is AOD correction and gap filling at intra-urban scale. And finally, I will show results and conclusions. So this is the problem. We have we are working on the NASA JPL's multi-angle imager by aerosol, or MAIA, investigation, which represents the first time that NASA has partnered with epidemiologists and health organizations on a satellite mission. And the aim is understand how different types of particulate air pollution affect human health. So, for example, adverse birth outcomes, cardiovascular and respiratory diseases, or premature deaths. The MAIA instrument will make radiometric and polarimetric measurements, and its aim will be to characterize the sizes, composition, and quantities of particulate matter in air pollution. This work is in collaboration with Agenzia Spaziale Italiana. Our research is part of a project called APAYA, funded by Agenzia Spaziale Italiana. APAYA is an acronym for assessment, a nice acronym for assessment of PM exposure at the intra-urban scale in preparation of the MAIA mission, and involves partners from the University of Bari, l'Istituto sull'Inquinamento Atmosferico, the University of Naples, and ARPA. For this work, I want to acknowledge the fundamental contribution of Roberto Cili, who's sitting here, and I want to thank all the collaborators as well. So the problem is the following. We want to evaluate health risks associated with the PM in urban areas. So there is need for, in order to evaluate those risks, we need to have a precise and high-resolution mapping of PM concentrations within a city. However, PM ground monitoring stations are sparse, we know. So our question is, can we use satellite AOD and machine learning or deep learning models to perform AOD correction and gap filling at our scale, which is intra-urban scale? Future questions will be how to use this predictor, AOD, as a predictor of ground level PM. We firstly made some observations. So we wanted to understand the quality of available AOD products. And in order to do this, we compare them with daily average measurements of Aeronet provided by the Aeronet network. And as data, we use the data from the Italia Peninsula. And the reference period is 2019-2022. As AOD products, we use the Sentinel-3 AOD, MODIS MAIA AOD, MERRA2 AOD, and CAMS AOD. The last two are reanalysis, we all know, data. As ground truth, we use the AOD from Aeronet station at 440 nanometers. All this data were, we considered the daily averages because our purpose was to estimate daily AOD levels. Okay, so we downloaded Sentinel-3 scene data and performed a change of coordinates from curvilinear to Mercator, cylindrical Mercator. All other data we downloaded with GE and performed upscaling to reach the 300 meters resolution of Sentinel-3 scene. So this is a plot of each AOD product in the y-axis versus the ground truth AOD, which is Aeronet. We can see that MODIS and we show the Pearson correlation, RM, the root mean squared error, and the expected error on the side. So we can see that MODIS Maya KOD proves to be the state-of-the-art in satellite AOD reconstruction, while Sentinel-3 SIN correlates less. We see that the correlation coefficient for the top plot on the left is 0.47, while for MODIS, the correlation coefficient is 0.76. And also the Sentinel-3 shows, SIN shows a bias towards overestimation of AOD. Of course, in the plot, the number of points is different because we have different availability of data. So there are many data for, there's more data for the reanalysis measurements. Now then we moved towards the main problem, which is AOD correction and gap filling on an intra-urban scale. Again, our aim was to create a data set of daily averages of AOD at intra-urban scale, and we used a pixel-based approach. So, we used both linear and nonlinear regression. Our input features are Sentinel-3 SIN, MODIS MAYAC, MERA2, and CAMS AOD. And as auxiliary data, we used MODIS LST, the DEM, ERA5, some ERA5 weather analysis variables, latitude, longitude, the PBLH from MERA2, and the day of the year. So we developed two models. One that we call the ensemble model for AOD correction. This model has, is a regression of all the AOD factors plus auxiliary data. While for data imputation, that we also call gap filling of missing information, we use the same model without the high resolution AODs, which are MODIS and Sentinel-3 SIN. MODIS MAYAC, Sentinel-3 SIN. The auxiliary data, we performed the regression against IronNet AOD, which is the ground truth. These are the results. We performed, we used as validation strategies both a leave 1 year out cross-validation that we call LOYO, and a leave 1 station out cross-validation that we call LOSO. We compared also both linear and nonlinear models, so an ordinary linear regression and random forest. Here we can see that for the LOYO validation, the linear model and the random forest have similar performances. They have a Pearson correlation around 88. The random forest has a slightly lower performance. While when we switch to leave 1 out station cross-validation, the linear model outperforms the random forest model by 10%. And if we look at feature importance, we see that the most important factors are MODIS first, AOD, and the reanalysis AOD, so MERA2 and CAMS, while other coefficients, other features are less relevant, and we can say that S3 SIN's contribution is minimal. Finally, these are the results for year 2022, so prediction for 2022 using all preceding years. On the left, we have the results of the ensemble model, on the right of the gap filling model. Performances for the ensemble model are, we have a coefficient of correlation of 87%. For gap filling, performances are lower, 74%, although they also include points where we have clouds, so difficult measurements. In conclusion, our findings demonstrate that there is room for further improvement of AOD products by imputing missing AOD values and by further calibrating AOD using regression models fed with available AOD estimates and auxiliary data. Probably Sentinel-SYN3 is not a ready product right now for these purposes. We didn't show many details, but we also tested deep learning models that we wanted to present, although, however, we were not successful in using these deep learning path sharpening techniques, and the best model is the linear model fed with AOD after reanalysis. So that's everything. Thanks, everyone.
Thank you so much. You get the brownie point as well. You made it on time. Thank you. Okay, so we call the last presenter, Soren, to talk about air quality, but more on the mental health, which is a topic which I really like. Thank you.
Yeah, thank you very much. Very happy to present here today. We'll be very quick so that we all can go for lunch. But might be a good idea to stay and to wait because you might learn something about your own risk to become depressive. And that's quite important information, I think. Well, we'll see. It all depends on the control variables as I will describe. And yeah, I will give you a quick introduction to the environmental project, and then we look at some results from this project, Earth observation for mental health. We are working with cohort data, and I will show some results with the UK Biobank. Environmental is a quite big EU project. We have 10 million euros for 24 partners. It runs until 2027, and we investigate how some of these environmental challenges, especially climate change, urbanization, and psychosocial stress caused by the COVID-19 pandemic will affect brain health during the lifespan, and goal is also to develop interventions aimed at prevention and early interventions. So we have to identify adverse urban environmental signatures, and then the goal is to develop a predictive model for the environmental impact on brain and mental health by relating symptoms from cohort data with the environmental measurements. So for that, well, the whole project is led by Charité Berlin. So there are quite different groups active, and remote sensing is only present in 2 groups. One that's me from Frascati University Jena, and one from the Free University Berlin for the climate data. So we don't generate own products, we use available products, and quite a lot. So we have tree cover, the Tandem X Copernicus DM with various different layers, also terrain aspect, slope, elevation, ruggedness and roughness. We use lots of World Settlement Footprint 3D data. World Settlement Footprint 3D data is a very good evaluated and validated product. And we have building area, building volume variance, and standard deviations. And very important is that we calculate this for different diameters. So we look into the neighborhood of where people are living. Makes no sense to really pinpoint the information from remote sensing for the patient position. We need to have the environment. So the neighborhood is very important. Where are these people living? So we look into different neighborhood diameters, 300, 500 meters, 1,000, 3,000, 5,000 meters. And if we do this countrywide, you generate a quite big data set because we have lots of different dimensions in our environmental data layers that come from these different products. And then we also look into water bodies and nighttime lights, sun energy, especially interesting for Norway, for example. And we also include spectral information, spectral bands for the analysis. And of course, tree cover, NDVI is included for greenness. So today I'm also only show you some of the results that we have here, especially for building volume in 2 kilometer diameter and building volume in cubic meter per area. And we also look a bit into NDVI, but yeah, we have already done other analysis with the blue data, but where we don't have really time here to show all this. UK Biobank is a very big data set. We have 500,000 participants, all geolocated, spread over UK. But well, the plot is a bit misleading. There's a bit overplotted. Most of them are actually in London and in the surroundings of London. So that's maybe also a spatial bias that we have in this data set, but UK Biobank is one of the best cohorts that we have available. So we started with UK. And we have brain, heart, body, MR imaging, genetics, wide range of health records, activity monitoring, biomarkers, etc. This is a huge data set with lots of dimensions. And the main problem with working with this kind of data is that we are not allowed to see where all the participants really live. So we don't have the exact position. Yeah, we provide our data to UK Biobank, our environmental layers, and they send us the attribute join back, and we get a huge CSV file with 500,000 patients, but we don't have the exact position for these patients. So we cannot do spatial interpolation, for example, and we cannot do spatial visualization. But yeah, we are very much depending on these cohort data. So NACO and commitment for other countries are on the queue, but we start with the UK Biobank. Well, these are the variables that are related to depression, anxiety, and substance abuse. So we looked into these variables first, and then we defined some control variables where we look more into detail where the correlation comes from. Well, this is all from this zonal attribution or the attribute join with UK Biobank data and our environmental data. And then we go into the analysis. This is, for example, here one of these typical plots that we are doing, depression diagnosis versus build-up volume. So we have build-up volume here in 2 kilometers, and we use quantile binning. So every bin here stands for 500 participants, and you have the depression score. So these are diagnosed depressions. And you see we are here at 40% going down to 30 or 35% in high build-up volumes. Why is the depression going down here? Usually it goes up when you go into high build-ups. It's going down here because we look at a specific control variable. So we look into the data for women, and we look into the deprived persons. This is a very high deprivation index. It's an index of multiple deprivation from UK that we're using. And you can see that for this subgroup of women, they are very much deprived. They live in very deprived areas. Socioeconomic situation is very bad. And the depression rate is getting lower when we go in the high build-up regions here with 5 million cubic meters per 2,000 meter diameter. So the full picture is quite different. If you look here at the different urban structure types that we have, that's just for orientation. We are here in the region detached houses and high density block development, but the business district is around 10 to 50 million cubic meters, so that's quite out of this figure here. If you look at the full picture, the situation is much more complex, because what we have seen was the yellow line, and the yellow line shows for the deprived women that the depression goes down. But if you are undeprived, the depression goes up if you live in the central business district or highly impervious area. And if you live in the countryside and you are very undeprived as a woman, then you have a lower depression percentage value. So that's very interesting to look into these IMD values. They come together with UK Biobank depression or the UK Biobank data set, and it makes the picture much more complex because you then don't have one trend. It splits up in various different percentages. We know from the literature that men have a much lower risk for depression, and that's also pictured here. We have much lower depression values here in the range of 15 to 20% below what women have to face. So highly deprived women have a highest depression rate in rural regions. The percent depression decreases with build-up, but undeprived women have lowest depression rate in rural regions. So if we look into NDVI data, we see a similar trend, but just inverted. Higher NDVI values, lower depression rate, and you can do this for the same control variables here. So for the deprivation control data, we can see that the undeprived women have a very low depression rate in the high NDVI value ranges. Same with men, a bit different, and the variability is not as high as with women. But we know from the literature that women have a much higher risk for depression than men, and it's also a bit pictured here. So if you look into address time, it's a very interesting control variable, because originally we thought when we look into address time, we can also see that environmental variables have a stronger impact when address time is higher, because people stay in this region for a longer time. They should be affected more from environmental conditions. But that's actually not true. People that stay very long at one place and have a very high address time. Here the yellow line, they have very low, comparably very low depression rate. And that's probably because they are much better integrated in their social system, and they are also elder people. So it's quite complex to look at these data sets and to find out whether the environment has really an impact here. And if we look at the people that have just moved recently to a place, that's the blue line, they have very low address time, and they have very high risk for depression. And that's quite also what we know from the literature, that moving to a different place is extremely stressful. So same for men, basically, a bit different in the level where we start at. And so women with a high address time have the lowest depression rate in rural regions, but depression increases with build-up. Yeah, we also looked into other variables already, and you can see that, for example, cholesterol values are lower in the central urban areas than in rural regions, likely because diet is different, people may be more doing sports, very difficult to estimate where this comes from, but we can clearly see that cholesterol values, blood values are different in suburban areas compared to urban and high-density urban areas. Daily alcohol use is very interesting. It seems to have a nonlinear function. We come from high values in the suburbs to lower values in the row build-up regions, and then towards the central business district, it increases again. Alcohol seems to be not linear distributed when we go into the high built-up regions. So similar, we have an increase for senior psychiatrists for anxiety and also for 6 alcohol daily, extreme alcohol consumption, etc. So in summary, to bring this to an end, we have lots of correlations, but it's very difficult to explain what the impact of environment is on these factors that we see in the cohort data. So correlation is not causality, and it's a huge debate what the influence of these environmental factors really is, and we have to really look into the control variables to find out how much information comes or how much impact comes from the Earth observation data in our products. Higher address time, index of deprivation, and another problem is even when we start with 500,000 patients, with these control variables, very quickly we run into underpowered systems because we are only dealing with 10,000 patients then finally, or 5,000 even. Because with the control variables, you're looking only at a small subportion of your full cohort data set. So can we explain the big three with spatial EO data? Probably yes, but not fully. Yeah? It's a bit unclear how good we will be. We cannot evaluate our results later, but of course we can, with our multidimensional data set up a machine learning system that will approximate for every pixel in your K the risk to become a depression. That's possible. The question is, how good will this information be? And we have no additional data set to evaluate that because the cohort data comes without georeferencing. And if we would have georeferencing information from the cohort data, then we could split it into an evaluation and training data set, and we could really evaluate the accuracy of this product. But so far, that's not possible because of just legal reasons that we cannot use the exact position of the participants. So that's it. Thank you.
Okay, thank you everyone. I think I would like to call upon all the presenters to the stage now, please, to have all the question and answers from the audience and ourselves as well. We won't keep you too long for lunch, so I would really like the audience to stay back and have your questions, please. So we've seen 6 in total, 2 looking at the urban management and monitoring, 3 looking at air quality, and the last one looking at mental health. I think they're all really important topics. I still remember when I started looking at air quality data, I was downloading with real excitement onto the stage. On the stage. Yeah. They need to see. And remember, 1 pixel was covering the whole of the city, so it's really improved a lot. Now we can look at the street levels. So, excellent, thank you. Can we have the microphones as well, please, here?
A second air quality presentation. So that was really interesting, but I didn't quite figure out. So you have the high resolution emission, and then you relate this to the satellite observations of the concentrations. So for the high resolution concentrations, how do you take into account the dispersion and advection, like the meteorological factors? How is that accounted? So it's a learned model, I guess. Huh?
Does this work? Yeah. Thank you for your question. So, yeah, how do we do this? So I basically build up a dispersion model based on this proxy data. I assume some proxy, some emission factors, and from this I'm reconstructing the satellite observations. And the mismatch between satellite observations and the simulations tells me how to adjust better emission factors, which give better results from space, and hopefully also better results if you run it for surface concentrations. And it turns out that it does. So if you correct from the space observations, you get better ground surface concentrations. So this is the short answer. Maybe I can give you a more elaborate answer afterwards. Thanks.
So I have almost the same question. Did you succeed in separating between different activity sectors about the emissions, or you just correct the overall emissions?
No, for what I do now is I separate between transport emissions using the road network and assumed traffic volumes, and residential emissions using the population as a proxy, as those in an urban environment, at least in Europe, are the predominant emission sectors.
Any other questions from the audience? Okay, I'll start the question as well, and then I think I'll go with TRL in terms of the cost of the data sets. I know I saw a nice graph between the cost and the efficiency of it. Would you give a bit more insight? Because I think that's a really important information we need to have.
Yeah, so we made a few assumptions with costs, and some of the original work we did with Pleiad's imagery, we had a 50% discount because Airbus were our partners, and they indicated that for a large data set, which would be, the example we gave was Tanzania, where we did our last res, they would give up to 50% discount. So there's quite a big variation there, but the cost, I think the headline cost is around €30 for the highest resolution. Then we go down to the Vision 1, which is, I think, €6 or €7. So quite a big difference, but not such a big difference in the resolution. So that's why we were coming with better cost effectiveness for the lower resolution in the end.
Thank you. I have another question as well for Soren. In terms of the depression rate and the air quality. I know you're looking at the women's are more depressed compared to men, but did you also take into account the age factor?
Age as a factor of the patients is so far not directly included, but the address time is totally correlated with age, because address time between 30 and 80 years means that people have been living there for their whole life, and they are at least 50 to 80 years old. So it's already included in the address time analysis. And it's also one of the problems that we cannot differentiate some effects because they are so directly linked, like age and address time, for example.
Perfect. Olivier?
So I have a question for Robin. I really like also the link with the cost of the data. But I was wondering that your tool is addressed for local authorities or state authorities. How do you manage to make the tool operational for the people in place?
Okay. Yeah, thanks. That's a great question, because one of the things we considered all through was the capacity building that would be necessary. So I think on the process I showed that they could have an option of doing, if they have a reasonably high capacity, they could do quite a lot of the work themselves, perhaps with the use of the help of a local provider, like there's one in Nairobi called RCMRD, Resources of Mapping for Development, which could certainly do a lot of that for them. But they also have the option to have someone come in and do a lot of the work for them, like we would. So the capacity is reasonably low in these countries, so there would be some capacity development that it would need to be done. So we've thought about that as well, and it's an important area to consider to make this sustainable in the long term.
Okay, so I have almost the same question for Simonetta. As in the project, the city of Torino is included in the project. So finally, the tools are not so simple to interpret when we saw the maps. So how do you manage also the link between the city in order they can have to become relevant for use of the data?
We are working with the city of Turin also in other projects. So we are trying really to understand their needs, and their needs, like the road markings assessment module, cannot be handled with a 10-meter resolution, for example. So it's like we need the city to evaluate the cost of a 2-month temporal resolution image acquisition of Pleiad Neo or World View, in order to understand if actually it helps them to allocate their budget for the road maintenance. So we we are speaking to them and we are trying to understand if we can decrease the resolution and to address their needs. But in this specific case for the road markings, we cannot do it as with 1 meter or 20 meter. We are not able to actually see the markings on the street. But for the next projects, for example, the river monitoring ones, we are trying to use open source data, like SER data from Sentinel-1.
And I have a question for Bas. In terms of, I know there were a lot of data sets in terms of the data collected and the source of the data and interoperability. So I think that's one of the challenges I think all the people who spoke today will be having. So I would like to have some insight from you on the data interoperability.
Sorry, about the data
yes, from different sources and integrating.
Okay, so yeah, so ideally what you want to have is being completely independent on the local availability of data. So what I try to do is make as much as I can use of open data sets, which, for instance, for the emission proxies, I'm using the Global Human Settlement Database, which is satellite derived and it's available for the whole globe. OpenStreetMaps, which is all available, also open data for the road network. What I'm still looking for a good solution for a traffic volume. So this is really a parameter which is really important for local air quality. But there are, as far as I know, but please correct me and tell to me if you know an open data set for traffic volume, which I can use, because now I depend on local counting exercises or a little bit of outdated EU products like Open Transport Maps, but this is from 2016. And as far as the meteorological is concerned, this is not open because I'm using ECMWF data, but the idea is to swap this to open meteorological data as well in the future. But yeah, I think it will be a good philosophy to continue building these tools upon open data, so it is for the whole community and for all the cities there to be used without any problem. Somebody else to add something to this? Well.
Esther, in terms of from data to the modeling side of things, so the data modeling, the air quality modeling you were doing, how difficult or easy was it in terms of, how long did it take for you to come up with all the input parameters, modeling, and then validating? I know it's a very daunting task as well, using machine learning. So if you could have some insight into it. I think that's for the audience. It's more like everybody wants to use machine learning, everybody wants to use AI, but it's really understanding where to use it and how to use it and when to use it.
Yeah, first of all, I want to say that the tasks were split across people, and I was not in charge of the pre-processing, but I know the pre-processing was the hardest part. So it required specific competencies, and it took a lot of time because we had to harmonize the data with respect to the resolution and so in time and in space. Regarding AI, I can say that in the end, the best model was the linear model, which is pretty fast to run, so we were happy with that. And so that was easy to manage. Yeah.
Thank you. Any questions from the audience? Not inspired you yet to ask questions, or is it because we are close to lunchtime? I think we need one for Davide as well, I think.
Yes, just a small question for Davide. I really appreciate how you manage the different scale treatment, but you show also that models are biased, and especially when you are dealing with chemical composition of aerosols. So my question is, you need some in situ data. For example, in Paris, we have two aerosol mass spectrometer in order to measure the different components of the aerosols. So, but they are quite really expensive to set up. What would be the main process to compare with that type of data? What would be the best to do to validate, in fact, the outputs of your system?
Okay, thank you for your question. Good question. Is basically only about the validation, not to consider, for example, additional data for fine-tuning the training, let's say. Yeah. Yeah, indeed, that was an important part that we consider in the project. The point, actually, at the moment, is the availability of the real data that we have for the prediction. That we have not so much data due to the availability of this hyperspectral mission that at the moment is more like a precursor, but we to have a very, let's say, a higher comprehensive validation. Firstly, we need to obtain more predictions, more output from our algorithm. And of course, will be the occasion to exploit in situ measurement and the instruments that we have in the team. But also, we also would like to extend as possible the network. Also, we will check in Paris, of course. Yeah, maybe the first point is to increase the amount of data that we can process with the tasking and hoping that we can, tasking new acquisition from current operative mission, extending to MAP, for example, looking for other new upcoming hyperspectral mission that I note that recently they increased, at least upcoming. We are waiting. And then yeah, we will find, of course, let's say the key point will be to combine with in situ measurement, of course, with some assumption, because always there is a point to compare point measurements with spatial distributed measurements. There will be also in this presentation, for the sake of time, I didn't mention, but there is also, we consider to different scale, of course, of our results, because actually below the kilometer spatial resolution is difficult to find product to compare. And yeah, there are many points, but basically the availability of hyperspectral high resolution data at the moment is our, we are looking especially for this, and then we'll do, of course, this validation.
Thank you very much, and thank you, audience, for really being patient. I think it's a very interesting discussion. They'll also be available during lunchtime, so you can carry on the discussion from now on. Thank you.
Thank you all, and thank you, Kavita and Olivier. This is a difficult task to be before lunch. So, quick reminder, in the afternoon here in the big hall, we will have 2 sessions. The first one is on urban energy, and the second one is on green infrastructures. And in parallel, you will have the 2 demo areas, which will happen in James Cook. So building 1, close to the canteen on the 1st floor. So at the same time, the first one and the second one. Last but not least, this evening at 6 p.m. we have the poster sessions in the tent. I've seen that you have already done some conversation. So since we are late, we will reconvene at 2:40, so 10 minutes later. So I wish you all a nice lunch, and the canteen is in building 1.
I can hold.
I need to.
Okay.
Cioè noi stiamo in 4 apposta per stare a prevedere.
Io ci metto. l'ha chiusi. Okay. So thank you everyone for joining us in this first session after the lunch break called Urban Energy Landscapes and Efficiency Mapping. We will have a session format where we have an opening, then we have short presentations of 10 minutes, followed directly by a Q&A. Again, in time management aspects, if there's no question, we will continue directly with the next presentation. So if all speakers could come to the front, that would be fantastic. So our opening today is done by Martyn, who is the head of digital services at the Regional Sustainability Agency of the French Auvergne-Rhône-Alpes region. It's called AURA-EE. So we're looking forward to hear the perspective of a practitioner also in urban energy landscapes. Thank you, Mathieu.
Thank you very much. I'm glad to be here and to be part of this first conference, URBIS. So I'm just going to give a very quick, I'm going to put a timer, a very quick overview of what we do as a regional agency and how it could be useful for you, either practitioners or Earth observation companies, actors. And so here we start, just a very quick overview. Auvergne-Rhône-Alpes is one of the main French regions in terms of inhabitants, finance, and so on. So the regional government is helped by actors such as our agency. So we are funded mostly by public funds, but we also have some independent autonomous projects at the side. We are working directly with the cities, so we are very used to working with them, understanding their needs, and trying to fulfill them by providing data, services, applications, and so on. We are trying to work in very diverse field of expertise, such as energy production, energy consumption, but also retrofitting for buildings, air pollution, and so on. So one key point of our agency activity is the fact that we are trying also to connect with other regional agencies. So that's why I think it's quite nice that we are here today, because there are a lot of other regional agencies all over Europe. And there is a network called FEDAREN, which is just a network of all the regional agencies and local agencies that could help you access to the cities, because they have the knowledge, they have the contacts. So this is a very quick overview of our agency. One of the tasks that we are trying to do is to provide services to the territories to help them in their transition. That goes from territorial intelligence, so trying to analyze what's happening there and using then data, of course. So satellite data is a good source of information. But we are also providing support and trying to build projects involving the territories to innovate and to create new opportunities to work together. And a very concrete example I'm going to use is the observatory activity that we are doing. So the goal of the agency in this kind of topic is just to gather a lot of data regarding energy and environment transition, and to help the cities using those indicators to build their plans to invest, to decide the subsidies they are going to put into effort. So as I mentioned on the slide, yet we are using very few satellite data for this kind of work, and that's why I'm here today. It's to understand what we could use to help the cities of our region. So if I go very quickly, when we have the data, then we are trying to go further. So that's why we built some applications that are using the data, but providing like simulation tools or action plan tools that help the city go further and analyze the data and use them. And that brings me to the very end of my presentation, is the fact that when we are considering Earth observation in our regional agency. We are going to proceed the same way we proceed usually, promoting open source and open data tools, but also involving territories as soon as possible in the process of building the tool, designing the tool, to make sure that they can tackle the issue that they are trying to address. We have, of course, some topic that we would like to discuss, like energy, renewable energy production potentials, natural risk, and climate adaptation. And a very small concern that we have about Earth observation, maybe I think most of the presentation I've already seen have addressed these few concerns. The fact that, of course, Earth observation is very resource consuming in terms of human skill resources, but also for money. And that's why the main issue we have today regarding these kind of topics is the sustainability of the tools, of the service, of the data that you are building. The fact that the tools and database that you can build are sometimes very punctual and built once, and they cannot be updated easily. So for the territories who are trying to work on the long term, it's very hard to base their efforts, their methodology on this kind of data, because they don't know if it will be up to date when they need to update their own plan of actions. So that was really quick. I don't want us to be more late than we could be. So I'm happy to be present with you today, and I'm glad that we have very interesting topics to discuss this afternoon. Thank you.
Okay, thank you. Our next speaker is Alessandra Feliciotti from Mind Earth, talking on pioneering urban energy efficiency, the ESRB AI project.
Hello, hi, thank you very much for having me here to present this activity. The BAI project is an ongoing project funded by the European Space Agency through the development and verification of urban analytics Expro Plus. The project started just in January and is going to conclude at the end of June 2025. So today, I really would like to give you an overview of the current progress of the activity. I myself am an urban planner, urban designer by training, so my goal here is to really understand what are the potential of this type of activity and solution for, let's say, future application in urban planning domain. Before starting, I would like to introduce a little bit Mind Earth. Mind Earth is a small Swiss-Italian company that operates in the area of location intelligence and remote sensing. We specialize in working with 3 types of data: Earth observation data, location-based GNSS mobility data, and at the same time, in situ data that we collect through a proprietary system that we developed throughout the years. Before diving into the project, I would like to somehow set the stage a little bit to understand why we think that this is really a key topic to address right now. If we look at the European building stock, what we see is that at the moment, buildings are a really important consumer of energy. They represent around 40% of all energy consumed, and they are responsible for the emission of 36% of GHG gas. If we focus a bit more on how the European building stock looks like, we can see that around 40% of all buildings across Europe, with local variation across different countries, we can see that around 40% of all buildings were built before 1970s, which is the decade where the very first, let's say, laws or regulation about building insulation were starting to come out. So at this moment, around 75% of all buildings are considered as energetically inefficient. And the renovation rate that focuses on energy-driven renovation each year averages to around 1% of the full building stock. And if we think that, okay, fine, and the average life of a building is around 80, 100 years, so let's wait and then build back better, this is really not a good strategy, because it has been estimated that between 85 and 95% of all buildings that currently exist will also exist in 2050. Europe is very aware of this situation, and we all know that through the Green Deal, We have very ambitious target as a European community to decarbonize our city and make them more energy efficient. It has been set as an objective for 2030, so really around the corner, that around all the 49% of buildings should be powered by renewable resources, that we should aim to double the renovation rate from the current 1% to 2% yearly. There are rules that will make sure that all new buildings will be built at zero emission standards, so from now on. And there is a requirement going forward that countries have to adopt in different ways based on local needs to reduce primary energy consumption by around 16%. And around 55% of this should be achieved by renovation of the worst performing buildings. All of these objectives are really ambitious, and one of the main ways that we now have we use to understand building energy efficiency is through so-called energy performance certificates. These certificates are produced by certified auditors. They are valid for about 10 years since their emission, and then they are required every time a new building is realized or for rentals or renovation activities as well as sales. They not only provide a ranking, which we might be familiar with because we also see it in appliances and all sorts of objects. And for buildings, this ranking from A to G is based on factors such as insulation, heating system, characteristics of the window, lights, and so forth. In addition to a ranking, EPC also provides some sort of synthetic recommendation on how the performance of the building could be improved. In the image that we see on the bars on the right, we can see the distribution of EPC classes across Europe. Not only we can see that a vast majority of buildings are in classes that are below E, but also that we see that this is has very strong variation across countries. An objective that has been recently updated to the Energy Performance Building Directive says that by 2030, we should aim to have every building at least upgraded to F class and to E class by 2033. So the challenge is really big. When we talk about data, which is a very important aspect here, so how do we know if a building is efficient or not? We can see that in Europe, the framework is very spread. There are some countries that have accessible EPC information, other countries that do not have centralized repositories. Countries like Italy have them, but they are region by region. And also they're not comparable because each country has their own way of measuring energy efficiency and classifying buildings. So we can see cases like Belgium where we even have 3 different types of EPCs in a single country. In this big context, the Building Energy Efficiency Estimation with AI project aims to create a data set that is, at the moment, is scaled at the level of individual cities to assess building energy performance and retrofitting potential, joining together Earth observation data, geometric morphological information, and in situ optical and street level data. This is done by implementing a multimodal AI-based system that allows to estimate the building energy efficiency for residential building in 3 main groups: AB, efficient, BC, so intermediate level, and EFG, so the least efficient buildings. But in addition to that, we felt that just EPC rating alone was not really sufficient to provide enough information. So we also wanted to create some sort of building passport, so enriching the information of each building to also include characteristics such as materials or presence of solar panels that we could derive from top-level or street-level imagery, so that we could generate some summary information on what is the best renovation strategy. We are not doing this alone. We have been doing thorough consultation with our stakeholders across 3 different countries. We're working in Copenhagen with KAB, the largest social housing provider in the country. We are working in Austria through the work of Renovate AT, which is our partner and has kept contacts with Obenauf, a company that represents essentially developers, small developers, and the municipalities of Klagenfurt and Vienna. And in Italy, we're taking a more business-oriented approach by interacting with Mobiliare.it, that is the larger real estate information provider in the country. We have worked with 4 main types of data for this. I'm going to go in detail for each of those. For what concerns street-level imagery, we have developed an app that allows to commission street-level mission to people that can use their smartphone to collect information on individual building. This is a bit of outlook of this app that has been customized for the specific need of this project, so people can just book a mission on a building, take a picture, this is uploaded, and we can then analyze it. We are applying a similar principle to analyze street-level thermal imagery, which we collect with, in the same way, but with smartphones that are equipped with a FLIR One Edge Pro thermal sensor that allow us to understand thermal defects on the facade. We are also using top-view multispectral imagery. We have just been granted by ESA through the third-party mission access to Pleiades Neo and WorldView 3 data, so we can use very high-resolution imagery for the areas of interest, but also to test different options that might be already available through municipalities. We are also using orthophotos, which are typically collected on a yearly basis for most cities around Europe. In addition to that, we relied on either authoritative data sets or OpenStreetMap data to build a sort of morphological profile of each individual building, taking into account things like area, height, volume, and other information that can help us understand a bit better how the building works. And of course, in each country, we access EPC data to use as a validation, but also to extract additional information on the building itself, which are typically contained in this data. We can see the example of Copenhagen, where this data is openly accessible through the Spare Energy portal, and it's nicely associated with the street-level imagery, which we could use for some tests. The system is based in 2 main areas. We have a baseline system where we essentially apply a cat-boost classifier to basically link street-level imagery and top view with year of construction and morphological features to estimate building energy performance in these 3 classes. And then an advanced system that builds on the baseline one, but also generates some targeted or specialized models that extract specific features from the facade. Here we can see some of the first results for the city of Copenhagen. This is the baseline model, so it's the model that is agnostic to the feature of building, but simply takes the street level and top view imagery and associates additional information on year of construction and the morphology. And we can see that the results are quite good. On the bottom right, you can see the result for a state-of-the-art work on the same data set for Copenhagen that was only dividing it into binary classification between high and low. And we can see that the performance is substantially improved. And finally, we are developing additional specialized or models. We have currently worked on the roof shape model, where we are able to identify 4 different types of roof shapes. The roof material model that is divided into 8 main classes, and the photovoltaic panel model that allows to identify whether a building has or doesn't have photovoltaic panels. For the next steps, we are now in the process of starting the field campaigns in Turin, Milan, and Vienna to gather RGB imagery, and in all the cities plus Copenhagen, we initiate a thermal campaign for the collection of thermal imagery. From these, we will implement more models for architectural style assessment, facade material, and number of stories, and additional models that we have devised with our stakeholder. Whereas for the top view, let's say, component, we will integrate land surface temperature and albedo data derived from Landsat 8 and 9, and integrate additional information on solar energy potential derived from very high resolution DSM. And again, trying to test the quality of the 2 types of data set for orthophoto or very high resolution imagery. So thank you very much for your time.
Thank you very much, Alessandra. Do we have a question in the audience? Yes. I don't know if we can. Thank you. A micro will come to you. The man in the back. Thank you.
Hi, my name is David. I'm from iStack Space. Both you and the previous presenter have talked about the use of public data sets.
Mm-hmm.
And I understand why that's a huge driver for choosing the data. However, I'm wondering whether there is any, well, the public data sets sometimes have limitations, and especially in thermal data sets, typically they only are at one time in day, during the day. So I'm wondering whether there is any space for commercial data sets, like the one that we'll be able to provide and some other people here in the audience.
So the reason why we are testing both very high resolution imagery and orthophotos is to understand what is the, let's say, what are the trade-offs between the two. On one hand, we know that, of course, there are important advantages in using very high resolution data for their multispectral profile, but at the same time, we know that a lot of municipalities really, I'm not saying like, but need to justify some investment in terms of data collection, for example, with orthophoto campaigns. So we want to test both options to see what are the trade-offs of both. One important aspect is actually updating the information, because some layers that are out there, they have the problem that we only have a single snapshot in time. So in some countries, we see, for example, with the case of orthophotos, that they are updated yearly. So we can, make a product that is always updated. In the end, I think it's really a trade-off between what is the added value of commercial data for municipalities that are adopting it, or for people that are buying this type of product. But of course, for example, in the case of thermal, by using freely available data, we can get up to a certain point. So we have been looking into collaboration with drone operators to understand what the type of data could be used, or also to understand other types of sources that could be used instead. But yes, I mean, this would be ideal. So we would also like to test it in the context of the project, so that would be nice.
All right, thank you.
Yeah.
Thank you very much. Thank you, Alessandra.
Yes, thank you.
We are going to welcome Anna-Catherine Mess-Marconcini, who is going to talk about Solar DE.
Okay, actually I have to say the project got renamed during the phase of the submission of the abstract and today. So it's actually not called Solar DE anymore, it's called EO Solar. But yeah, thank you for having me and presenting the work. Let me go back 2 years in time. ESA actually initiated quite an ambitious project called the Green Transition Demonstrator for Austria, GTIF, and DLR was part there in the urban spaces. Here we wanted to, or we were supposed to derive information about green roofs and also about solar panels on roofs. And not only the actual status, but also the potential for installing them, retrofitting the buildings. We were provided with a lot of data from Austria, and the way I'm presenting this now, the methodology that we used for EOSolar has actually been developed in the GTIF project. So we had the DSM, the DTM, OpenStreetMap data, because Austria didn't have any building outline data for the whole country. And we also were provided with aerial imagery, RGB and the near infrared. And the first part that we implemented was actually for mapping the existing rooftop PV panels. We collected training data that was not only for Germany, but we extended the training data also to Austria. We had the very high resolution imagery, aerial imagery, and we trained a neural network to classify buildings, either if they have a solar panel
or a roof, a green roof or not. It's like an image classification. It's not an object detection approach, it's an image classification. So we have every single building and we decided, okay, is there a PV panel on top or not? Then the second part was actually deriving information about the potential, and here we used the digital surface model with a resolution of 1 meter that was provided from the Austrian Federal Office of Meteorology and Surveying, and we used OpenStreetMap data. Just go at once. We masked the buildings and derived information about the slope and the aspect of the single roof parts. And we used this information to actually calculate the yearly solar radiation for each roof. And into this whole process, of course, not only the roof was included, but also the 50 meters around every building to also include information about vegetation that is possibly shadowing the roofs. So, and then afterwards we excluded parts of the roof that had a degree of over 45 degree and were facing north. And at the end, we derived a product for the whole country, which was quite elaborate to generate. For each building, we derived a value of solar radiation that is possible to retrieve with standard PV panels that are currently available on the market. Just have a look in the detail to Innsbruck. So we assumed we have a performance ratio of 68% and an efficiency of 19% for a PV panel that is available. And then this whole product was actually shown to the Federal Minister of Economics and Climate Protection in Germany during opening of the research wind park of DLR. And he was saying, yeah, that's nice that you did it for Austria, but can you actually do this for Germany? As we are, DLR is under the umbrella of the federal ministry, we of course had to say yes. And within 2 weeks, we had a new project, which was quite ambitious as well. So here, just to give you a background, the situation at that time was we actually did have solar catasters throughout Germany, but every state or even municipality or district is doing their own. So you have quite a variety of different quality. You cannot compare the products, the area coverage is different, you have different information content and so on. And at the end, the policymakers and decision makers can compare one to the other. And we also have I try to translate it. I don't know if it's the correct term, the market master data register, where everyone that is installing a PV panel on their roof and wants to feed the energy into the network needs to register. But they're publicly available. The data is only for buildings that collect more than 30 kilowatt peak. So the private house owners, they are not actually. You can't get the data from this register. And of course, we thought, okay, we will somehow create a German-wide cadastre for solar energy. Which is comparable, up to date with the information that we can, or with the data that we can collect here based on the digital surface model and airborne imagery. And just to give you an overview of what data we actually got for Germany, you can see this is quite heterogeneous. This is just an image for the auto photos, but the data collection goes back to 2016. And also for the surface model,
We actually were provided with the data from the German Federal Agency of Cartography and Geodesy. They are collecting the data from the single states, but their catalog was not up to date. So we actually searched on the geoportals for each state to download all current data sets available. And here, I don't want to bore you with how we downloaded the data, but it was crazy. Let's say every state has their own system to provide the data, and I think if you see Germany, you can assume this will be also for the whole of Europe similar. So at the end, we had a quite up-to-date data set, but also here to give you an example, we were provided with a BKG with the data on the left. If you see what is available for Bavaria, you can see already that there's quite a difference in the data quality that has been provided. And we used this data to actually calculate the solar radiation for Germany and provide the PV potential. And I want to show you now just a few examples from the different cities. So you have Berlin, we have Dresden, we have Frankfurt, Munich, and also Stuttgart, but we did it for the whole country. So these are just nice to show examples. And then, of course, you want to combine this data with data on the actual status. So you want to know, okay, we have this potential, and we calculated this for all the buildings, all the 20 million buildings, but you want to know, okay, which buildings, which buildings actually can be retrofitted with the solar panels, and which buildings already have PV panels. And here, I said before, we developed a methodology for Austria. However, the Marktstammdatenregister, the register, is more up to date than the aerial imagery. So we decided to skip this part of mapping all the roofs with PV panels and used the information provided by the register, and combined this with our potential. So in the middle, you can see we calculated actually the share of installed net output in the total potential that we calculated, and we saw also, or we provided also a data set of the proportion of buildings with PV on the right. And this is quite an interesting image where you can see that somehow East and West Germany, there's still quite a big difference. However, if you look in the middle, you see the installed net energy is quite similar. So you can assume parts of, for example, Bavaria or Lower Saxony, a lot of small buildings, a lot of private homeowners already have PV panels installed, while in the eastern part of our country, more bigger buildings like agricultural buildings have been used to install the PV panels, and maybe also the financial possibilities in this part of the country are not there. So just to sum up, the product has been published, had been handed over to our minister in Berlin in June at the International Aerospace exhibition, and you can also access the data on the EU Solar at dlr.de. So, and with that, I want to thank you.
Thank you, Anne-Katrin. We have time for one question. There's a question.
Mm-hmm. Yes.
Yeah, thank you very much. Very exciting talk. I was wondering, we were also dealing with sun energy, and we found it very challenging, really, to calculate sun energy in mountainous regions. And you showed the sun energy analysis in Austria. So I was wondering, have you also taking into account slope and aspect angles of the terrain, slope, terrain,
yeah.
To calculate this, because then you need all these different angle calculations for your neighborhood, which is really very time consuming and calculation expensive to do that. And so, because then it will be very precise, but that's the question, yeah.
Yes, yes, definitely. I mean, that's why we used the DSM and not the 3D building models that are available for Germany, for example. Yes, because we actually wanted to include this information. And just to give you an information, I mean, it took us 4 months on 10 to 20 processing units to actually come up with this product. It was quite elaborate. Yeah.
Okay, thank you very much, Anne-Catherine. No, but I'm sure Anne-Catherine is available for more questions. Next up, we have Matteo Manieri from Telespazio Belgium talking about how space-based solutions can support urban energy decarbonization.
I'm not that tall. Thank you. Thank you so much. Thank you all for being here, listening to me. Good afternoon. I'm Matteo Manieri. I'm responsible for open innovation. I'm here today to cover for Filippo Iodice, who's my colleague that was supposed to give this presentation, but sadly he can't be here. So the topic for today is how space-based solutions can support urban energy decarbonization. Before we start, looking at there you go. Before we start looking at how we can really support decarbonization, it's important to clear up what decarbonization really is, what it stands for. And there's 3 main concepts I want to discuss. The first is compensation. I'm sure you guys know this. So this is where you're reducing the emissions of an activity by compensating polluting activities with reducing activities elsewhere. So in other words, I'm burning something here and planting 6 trees in Brazil, and I say it's okay and it's done. This is not really a real solution going forward, because essentially you're not reducing necessarily the emissions of, what you're doing. On the other hand, we have sequestration. So here we're reducing the amount of greenhouse gases in the atmosphere by actively removing gases from the atmosphere, like a vacuum cleaner, right? But then for CO2. Here we see that the technology just isn't ready yet today to be used on a large scale. So that's why today we talk about decarbonization, where we're reducing the amount of greenhouse gases in the atmosphere by reducing the amount of pollution emitted. In other words, we're reducing the scope 1, 2, and 3 of our own activities. How do I get, why am I here talking about decarbonization? What is the background? The background is a project that we did for ESA. It was part of the Business Applications and Space Solutions program, and it was an enabling study to understand the opportunities for space upstream and downstream sectors in support of decarbonization, where specifically we looked at how space can enable decarbonization in the food production industry and in the buildings industry. How did we do this? We did this by talking to experts, a lot of them, company representatives, technology experts, support experts, field experts. We talked to a bunch of people throughout a workshop and questionnaires and interviews that we conducted, in our process. What we saw when looking at the needs of these people is that there's one clear visible need, right? So a lot of people that we talked to within the buildings industry, construction workers, they said, I need to focus on renewable energy for singular buildings. For this building, how do I make sure that it's renewable, that I'm using green energy? However, when working on this project a little bit further, we realized that this is not, this is also a need, but there's 2 other hidden needs that are also equally as important. The first is that the focus should be on energy usage within urban context. So not the singular house here, not the singular house there, but an urban neighborhood, an urban context. The other is that there's a lack of integrated and continuous data, and we've heard this, throughout the entire day. We have space data, which definitely isn't continuous, and, trying to merge in situ data and space data is like, putting apples and pears together sometimes. So we looked further at what the role of these space technologies can be in support for decarbonization. And here there's another concept that I want to clear up, which is direct detection for decarbonization and indirect detection for decarbonization. When we're talking about direct detection, we're using the sensor of the satellite to measure CO2 directly. We'll say, okay, I'm measuring CO2. I'm counting how much CO2 is in this area, in this pixel. When we're looking at indirect detection, we're measuring other parameters and deducing the emissions from the parameters that we measured. To give you a very stupid, simple example, we're measuring the traffic flow, and based on the traffic flow, we know what the emissions are. And this is what we call indirect detection. Through this bus program, we looked at various satellite technologies, from imagers to GNSS to SATCOM, looked at what their application can be, how mature and effective they are. And based on that, we tried to decide what the added value of space can be and what we can do. Mainly, we saw that for space data, actually there's four main things that we saw. First, climate change is a global problem, and we need a global solution. Generally, satellites tend to be global. I mean, they circle the Earth, right? Then we have that the space sector must help feed the demand for data. We hear it everywhere, you know, municipalities say, oh, I need data for this, this, and that. The space sector must help them achieve this data. That's where the added value lies. On the other hand, we have that space sector must integrate this data in economic and environmental context and not use them as singular data points on its own. Lastly, space can provide a sort of homogeneous reporting from a super parties and technical point of view, because the way a satellite measures something there, it'll be very similar or equal to the way a satellite measures something somewhere else. When looking specifically at urban environments, we see that there's a lot we can do. I mean, we've heard it, you know, the entire day and yesterday, and we'll hear it tomorrow again. There's, you know, from heat islands, solar radiation, surface runoff, land usage, air quality, emissions. The state of the art is good. It's good, but we're not quite there yet, because what we see is that there's some limits. The first, you hear it everywhere, you hear it always, spatial resolution. It's too coarse. Second, revisit time. Too little, we need it more often. Lastly, as I said before, data integration. Data oftentimes is not mergeable. It's difficult to put the two things together. So, as part of our work in this bus, we looked at how we can solve these issues. There you go. The solution we came up with is the decarbonization twin support. So here we're trying to combine data in a digital twin-style platform for an all-in-one emissions monitoring and mitigation tool for urban areas. Again, not the single house, urban areas. So what the image also tries to show, we go from a big pixel, big satellite data, in situ level, you know, BIM data, and a reporting data level. We merge it to get a size which is just right for us. Fundamentally, this means combining three main things. Data from BIM, so detailed local building data for urban districts, such as, for example, energy consumption, building emissions, thermal dispersion mapping. Satellite data, where, you know, we look at emission monitoring at a regional level, so from air column measurements to thermal dispersion, solar radiation energy cadastre, as my colleague before me said, urban green monitoring, and lastly, we look at integration. Here we want to integrate the BIM data and the satellite data in a digital twin-style platform, which will act as an aggregator of these data types. With GIS, we can simulate and visualize the effects, and lastly, we can identify energy usage and emissions in real time via 3D district models, leading, hopefully, if everything goes right, to a result that allows satellite-enabled urban decarbonization through the identification of high CO2 emission areas, the optimization of energy consumption, a comprehensive overview of district emissions and energy consumption, and a decarbonization plan of attack for urban areas. Looking more, you know, at the nitty-gritty, you know, the details, we have back-end technology where we're integrating BIM data, satellite data, and reported data. So scope 1, 2, 3, that's reported. We select the data, so which satellite is important for us, which one is not. We extract, load, and transform. So not extract, transform, load, but we load it first, because digital twin. Then we apply it on a geo design, which is different than a geo platform, because we don't want the users to directly interact with the platform. We do that ourselves, because we want to also do something we call project design, where we identify the good practices that can be implemented to reduce the emissions. And then we have a bunch of results which I, you know, touched upon 3 seconds ago. Of course, this product is not on its own in a, you know, in a void. It's part of a long-term space-enabled decarbonization roadmap, where at the start we say, okay, we got to use the data we already have today, which is the digital twin. But on the long term, we want to reduce the threshold, improve direct measurements, and have real-time GHG measurements. But I mean, I'm guessing that's what all of you here dream about, so I don't have to say that twice. But really, the key takeaways I want to give to you and I want to bring home is that we got to shift from satellite data usage for monitoring energy and emissions for singular buildings to improving urban resilience by reducing energy demand in a whole urban context. Thank you so much.
Thank you, Matteo. Do we have Any question in the audience after this nice presentation? I have one regarding the analysis you are doing on the carbon emissions, direct or indirect. I was wondering if you could do some historical analysis of what happened maybe on the territory to show some trends that are maybe not identified yet, but that have created some irreversibility in the territory organization?
Absolutely, and that's an extremely good point, because at the end of the day, one of the other, if you will, added benefits from satellite data is that we have historical data, for years and years. I mean, that's what in the first day we heard is one of the benefits of the Sentinel program, is that it's continuous data, that goes through. Personally, within the urban context, it's difficult for me to really give an example, but within agriculture, there is things you can do. You can look at the way a farmer is cultivating its land, and you have the data for years previous to today, and based on that data you can say, okay, look, because he did this 20 years ago, today you should actually be doing that to reduce less, or to emit less, sorry. So absolutely, it's a good question. It's where satellite data is definitely an added value compared to in-situ data.
Okay, thank you very much. I don't know if there is another question from the audience. Okay, thank you very much.
Thank you.
We are welcoming Elke Kretschmar. We will talk about the benefits of a multi-scale approach for solar potential analysis. Thank you very much.
Thank you. I'm Elke Kretschmar. I'm an Earth observation expert and project manager at IABG. Zoom in. So I would like to take you into the field of solar analysis and zoom in through the different levels we might address. This I will do with the help of some IABG projects we had been working on, and the Global Development Assistant clean energy experiences we are making at present, in order to introduce Earth observation into the world of the international financial institutions. If we decide if we think of Earth observation, using Earth observation information, it's also always a question of scale. So what type of granularity we are addressing, what is the purpose if a user is asking for solutions, and who is the user, for what purpose, what maybe also not expressed issues he wants to have the solution. And last but not least, is he able to provide some money for data, for example, and for on-site visits, for example, which brings us to the question of which data are we able to use and what can we expect with this data. I want to start with the global information layer. So we all know the Solar Atlas, I suppose. It's based on a very valuable data set, based on a series of data sets based on low resolution and medium resolution climate-related data on long-term and most recent analysis. What I would like to highlight in this case is some downstream reports published by SMAP recent years, called the global, addressing the global photovoltaic potential by country. So what are they doing? They are converting the possible usable sun into the feasible and economically relevant areas, so close to people, not on protected areas. And with this, they come up, they generated a list of the different countries, what they already using and what might they be using in future. So this is the global scale. If we go to national level, so we just saw it most recently from Anne-Catherine. So there are two different options to create these data sets. So it's, let's say, rich in open data solution. So if we have open data available, which we have for quite a few countries, even then it's difficult to get the data. So we have this bottom-up approach, which is very precise in general, and we have the common, let's say, common practice solution going from top down, well, trying to get benefit from the data we can have free of charge, just to describe the prerequisites in certain countries. So we are talking to global players, we are talking to World Bank, for example, so they are working in different countries from one day to another, so it's already interesting to them to see, to get an idea on the limitations on ground, especially also linked to clouds. So this was just an example summing up all the cloudy data sets of the recent years, just to identify these locations where there are clouds all the time, for example, high probability of clouds in front of mountains, for example. Same data enriched with data from the user, with energy infrastructure, for example, with some hotspots the users already addressing. Can already regionalize on a smaller extent and help supporting the decision on where to go for very high resolution commercial data, which costs the user something. Especially relevant in countries like Armenia, where we have very restricted access to public data, or in fast-growing cities where it's not really clear what the edge of the size of the city is. Talking about cities, we had all the data on the table, and they started to think of this. We started to discuss about floating solar. So they said, well, you can tell us the different water levels of the lakes. This is interesting. So then what we just heard, the tip of the iceberg, sometimes it's going much further. Once we have a region, we have a sub-segment or sub-region of a city identified where there might be solar rooftop analysis draft requested. If we are outside of Europe, we have less prominent cities, so often there is poor situation of archive data available. If it comes to stereo data, there's almost nothing. And if we have archived stereo data which is 3 years old, it's far too old. What we see here, so it's sort of a pragmatic approach, which some of you might not like to hear, but we have this city of Niamey, for example, in Niger. So here, let's pretend there is a certain budget available for data acquisition. We have the situation, it's close to the equator, it's dry, we have similar building heights, we have flat rooftops, and they would want to have solar potential analysis because everyone has it. So in this case, we sort of, well, you just need the square meters of the rooftops. You need the type of building structure, you need to know where are obstacles, and that's it. So we did solar potential rough estimation using just one image and covering the entire city instead of half of the city, which wouldn't have made sense, and doing the classic way, using stereo imagery, tree stereo in best case, and combining this, reflecting the building heights, the mutual shading, and which we did then for Armenia again. We are going back to Yerevan, getting a glimpse on different segments on the rooftops and obstacles again. Still knowing we are talking about very, very high resolution 1 data, so it is coarse, it's just a subset. We have OpenStreetMap data, we have OpenGIS data. We all know it's very valuable, but it has its limits. Combine this with machine learning AI approaches, and well, I don't want to go into detail that here. This is the center segment in Yerevan, so deriving the elevation model and rough information on the solar radiance situation on the rooftops, still keeping in mind we are talking to economists. We are talking on those who want to fund projects in a certain country, in a certain region, in a city in this case with 1 million inhabitants, to understand the dimensions in this city. What is the situation? What is the construction of of the different building types there, and to define focus areas. So they are aware of the limitations, and this is also always, well, from our point of view, it's always a challenge or important to make them aware or to be open, say, about the limitations. So they said, well, if it comes to planning, if it comes to implementation, we go there, we have a drone, we do it more detailed in the end. And this is also something we do in Germany as well for some users here. So it is, the implementation is again another thing. So you think of energy balance, we had this static limitations, rooftop loads, which can be done, okay, pretty lost. Well, this is then policies as well is linked to a lot of extra things, which can be just clarified on ground. Which brings me to the concluding slide. You remember the questions. So, of course, scale is something, well, depending on what we understand of national and regional, it's a bit overlapping. It is important, or our experience from our collaborations is, the coarser it is, the more it is about understanding, the less commitment is given. The more we go into detail, the more the need, the higher the need of analysis, of a precise analysis is given. And what is also interesting, in between, in the regional context, there are quite a lot of workarounds around going for detailed analysis. This also, well, brings us to the different range of data we might be using. And when it comes to the data, we consider, of course, or the results we expect, or the user expects. So, of course, the more in detail we are, the more precise we are, but we have a small footprint. And if we go into larger areas, of course, we then can have the chance to compare different things. So, roughly speaking, for every level, for every resolution, there are user groups which have their needs. And with this, I would like to close and say, well, it's not always rooftop. So there are many solutions, many questions still open. Thank you.
Thank you, Elke. Are there questions in the room? Okay, then I have a question. So you mentioned that especially on the local level, there are a lot of workarounds also concerning data availability. We have heard already that computationally it's sometimes challenging to do certain types of analysis. Have you encountered, let's say, situations where somebody had a wish for what they wanted and then realizing that they could go in less detail and so on and so forth, and what type of data or information were people willing to, let's say, let go of during the work on the ground?
So since when we are outside of Germany or Europe, we are talking to international financial institutions or people rather trying to understand the rough picture and doing good, however. So it is rather that they try to go back to statistics, to recent studies, to what was there already. So sort of a certain shyness in order to enter a certain new environment of data and new solutions which they might not be able to understand themselves in the beginning. So that is why this is also the aim of this GDA project, to showcase, to make them discuss with us, to come up with ideas. So it's a lot of statistics, a lot of we compare with another city and all that stuff.
Okay, thank you very much. Are there more questions in the room? Yep, there's one.
Hi. So the potential and the use of photovoltaic technologies probably will not change very much over the scale of time than one municipality or a region can use. I was wondering if you believe there may be a change in the last slide that you showed, where the types of data for different purposes you would prefer, if there was something more changing over time. I'm thinking about temperatures, but of course something else.
Well, we are not in this context. We are not addressing the what's after the comma. So what I know, what I trust in, for example, the global data set, the global solar atlas, it's also updated on a regular basis. So in this case, of course, these climate change or models, even though it's not measured or most recent measurements and also assumption maybe for future are considered. The examples I'm here addressing, apart from the very last thing, is to get a draft picture. We are talking about an environment where there is not much data, where they're happy about the OpenStreetMap data and everything that comes with AI. So it's, I think maybe some other of the session members can answer this a bit more precisely. So it's not the focus. I guess, well, of course, this is the granularity and the granularity of the data which feeds into these global data sets or the regional modelings is, of course, getting higher. The repetition rate of the satellites of the data which comes in.
So then you're basically saying that for these type of applications, there is still a gap between what may be possibly obtainable and what is needed because the technology or the application or the downstream industry is not yet there, right?
For the application or the examples I showed here, roughly speaking, the fact that they ask today and have the result in 2 days or in 5 days without paying much is most important.
All right.
To be honest.
Mm-hmm. All right, thank you.
Well, it's just one layer of many also hazard layers and all that stuff, which then gets combined.
Thanks.
Okay, thank you very much, Elke Kretschmer. Our next speaker is Beatrice Baresi, speaking about space for energy efficiency in smart cities.
Hello, hi, good afternoon everyone, and thank you for inviting me to this session. I work for ESA, for a program which helps European industries in developing solutions which use any kind of space assets together with other technologies to address the needs of people, but having always in mind the environment, so our planet, but also in a way which is economically sustainable for this company. So we want that companies grow economically using space-based information. Okay, so let's start by stating the obvious, which is that cities right now are facing a lot of challenges. And it's not, only for this session to address all of them. I think for the sake of the session today, I will just focus on the impact of climate change and the demand of clean energy, which are the ones that affect mostly the energy efficiency. But of course, there are so many more challenges. The good news is that space, in a large sense, together with other technologies that we heard already a lot of examples about it, can help addressing these challenges. And I'm talking with facts in the sense that we have an history in the program, but you have heard also a lot of examples yesterday and this morning as well of solutions that use space and other technologies to help the cities in addressing these challenges. And I will give examples in my presentation of solutions that have been developed for addressing green cities, urban infrastructure, clean energy, decarbonization process, and so on and so forth. These solutions are very different in terms of topics that they are going to address, but they have a common fil rouge, which is the fact that they use existing technologies, and they also are user-driven. So the cities, the urban developers are always in the middle of the solutions. So let's start with the first solution that I'm going to present to you, which again I would like to emphasize, it's an operational service that in this case has been developed for the city of Essen and the city of Bremen. These two cities are very important because they represent the rural region, and I mean there are a lot of people here coming from that from Germany, and it's a very specific region. It's also very important for the economy of the country. And the platform that has been developed for these two cities has two specific functionalities. On one side, it helps the city in managing the vegetation, the urban green areas. And on the other side, it allows to manage the urban heat phenomenon. So when it comes to management of the urban green areas, which affect a lot the consumption of energy of a city, this solution allows the city practitioners to have an overview of what is the status of the vegetation, to know, for instance, what is the vitality of a tree, to know, for instance, if that particular area needs to be monitored or to receive more water. The other service that is going to be provided by this platform is about urban heat. There was a whole session this morning about urban heat, so how crucial, how important is this phenomenon for our cities. In this sense, with this platform, a city can look at the effect of urban heat in a neighborhood, and what is really important, it can also see through the years, by using a trend analysis, how the situation has been changing. And this is very important, for instance, because as a city, you want to know if, for instance, the presence of a park has had a cooler effect in that neighborhood, or, for instance, if there was no effect at all on a specific area. So having the possibility of comparing data in the course of the years has been also considered very, very helpful. And this solution is based considering high resolution, medium resolution Earth observation data, combined also with OpenStreet information. The next solution is really addressing the issue of heat, urban heat island. And I brought to your attention today because if we talk about energy efficiency and consumption of CO2, I mean, urban heat, it's estimated they will be responsible of almost 60% of CO2 emission. So they are very crucial because they are part of a kind of vicious circular. On one side, urban heat are a consequence of climate change, but on the other side, their mitigation will increase the climate change. So it's really important to address them. This solution, Heatscape Revolve, it's about seeing what is the effect of planting, for instance, new tree on the urban heat islands. And what they have seen is that when it has been used, in this case a pilot has been done in Hungary, the efficiency of energy for a building has been of 3%. And there was also an improvement in terms of outdoor comfort conditions. As we know, I mean, if the temperature is too high, this is not good for us. Also, the economic value of a neighborhood decreases. So having this solution that allows to manage the urban heat islands is very beneficial. Still talking about efficiency of a building in an energy point of view, I want to present to you this solution, which is called ThermCert, which is focusing on the urban area, but it's very peculiar because it has been developed for an energy operator, in this case, E.ON. And here, the challenge, the need of the operator was very specific because every single energy operator has the obligation of putting in place measures for households that suffer of the so-called fuel poverty, which means households that have very low income, so they cannot pay the bills because they don't have enough incomes. In that specific situation, energy operators are asked to put in place measures to make sure that these people can pay the bill and still live and buy food. But the first question for energy operators like E.ON is to know where these people live. So this picture, which was basically created by using thermal images, it's to understand what is the energy consumption of a specific region. Then this platform ingests also data coming from, for instance, the income of the neighborhood, how many people live in that area, and so on. Once that the energy operator has all this information, then can address and put in place these ad hoc measures. Talking about efficiency of a city, when it comes to energy production, I thought it was also important to consider the transport, the mobility element, because so far we focused on the energy consumption of the building, on the urban green management, but if we want to make our city clean, we have also to think about the emissions and the energies which is due to traffic consumption. Of course, ideally, we would like to switch completely to the electrical vehicles, not only as a private, but also as a city. We want that all the bus fleet, all the vehicles are electrical. Everyone says yes, everyone is always enthusiastic about electrical vehicles, but then the big question is how much I'm going to earn, or how much I'm going to save if I switch to an electrical vehicle. Answer to this question is not easy because each of us use, let's say, a car with different behavior. So Human Switch, this solution, tries to answer to this question. Human Switch, which is a solution that has been developed by a UK company, which has been already largely adopted in cities, basically consider the pattern, the behavior of a driver, and tells you how much you are going to earn if you switch to an electrical vehicle based on your pattern of how much you drive your car, how many kilometers. And it uses satellite navigation to understand what is the condition of the traffic. The other component of the solution is live, which is really to say, okay, once that you have adopted the electrical vehicle, what is the best setup to adopt it, to embed the vehicle in the infrastructure? Affordable Map, it's a digital twin solution where basically you have an overall picture of the Benelux area, knowing what is, for instance, the roof orientation, how the pavement is done, and so on. And this information is very valuable for city developers or for city planners that need to decide, for instance, where to install a big photovoltaic park. So I will finish soon, but usually I put this slide at the beginning to tell you how, let's say, vast are the number of applications that space-based solution can unlock. But in this case, I thought to put it at the end, because I hope that by now, at least you get a glimpse of how many applications can be implemented using space data. So here you really see only a few names, and the slide I realize is very dense, but it's just to trigger your imagination to think about how many, let's say, challenges space can help us to address. I just want to conclude by mentioning Space for Green Future Accelerator, because we cannot, think about a session about decarbonization without mentioning this. This is an initiative that has been triggered by ESA, but actually is an initiative that sees a various number of partners coming from different domains. So ESA has partnered together with, for instance, the Covenant of Mayors for representing the cities, but we have also partners from the different transport sector, we have policymakers and so on. And we are all together to support the green transition. We realize that if we really want to make and to reach these very challenging objectives that we have in front of us, we have to work all together. So that's, let's say, if you want to know more about it, please get in touch with me. I will be happy to tell you. And yeah, I will be also afterwards at a demo session, so if you have any more questions, please come to me. Thanks a lot.
Thank you very much, Beatrice. I don't know if there is any question in the public. Okay, I have one for you. I was wondering, you presented a lot of solutions, and I was wondering if you have any idea how we could, how the solutions you propose for cities and real estate developers and so on, how it could help social acceptability of the projects, either for building retrofitting. I don't know if you have any idea how it could help the citizens to accept the projects of the city or maybe be involved into it.
So every single project has always what we call a pilot phase, where it's really required that the companies work with what we call the user, the future customer, in facilitating this process. So instead of pushing at the end of it, let's say only after the technological development is completed, we always make them part of the designing process since the beginning. So they are part of the requirement definition, but also of the system deployment and eventually of the pilot. And we have seen that this modus operandi helps also the acceptability from the user perspective.
Okay, thank you very much. I agree. I think it's very great to have such people involved as soon as possible in the process. Thank you very much.
Thanks a lot. Thank you.
And I think we are welcoming back Anne-Catherine, who will speak about mapping the energy transition, EO4Energy. Is it the right name now?
Yeah, that's the right name.
Okay, global survey of wind turbines and coal power plants. Thank you.
So, thanks again for the introduction. You might be wondering, okay, what's that topic now? We're talking about urban, and here I come with wind turbines and coal power plants. But as we have heard yesterday, also already the numbers, over 75% of the energy in the world is consumed by cities, and also more than 60% of the greenhouse gas emissions are produced in cities and urban areas. So, and to say, only 2% of the Earth's surface are actually covered by cities. So this is a great topic, and we somehow have to talk about changing the energy system, and it's actually already changing. It's becoming decentralized, it's becoming digitalized, and it's becoming decarbonized. And here the wind turbines and also the photovoltaics play a really major role in changing that. They are distributed and they are decentralized, and they provide the power more on or closer to the point of use. However, we have varying availability of wind and also of sunshine, which makes it difficult to estimate the output and the fluctuation over time. And here it's crucial to have databases where those infrastructure is located to derive high-quality energy feed-in forecasts. So it's actually quite important. And we initiated the EO4Energy project together with ESA, where we used Sentinel-1 and 2 time series data and Sentinel-5 data together with deep neural networks to actually derive wind turbine locations and also coal power plants. Wind turbine locations, because there is a remarkable gap in the existing databases, which I will show you later on. And for the coal power plants, it's obvious. I mean, they are producing the highest amount of CO emissions, and they are still the energy source #1 in the world. So what have we actually used to derive this data? We are using temporal statistics from Sentinel-1 and Sentinel-2 between 2022 and 23. Here we derive the key temporal statistics, for example, the mean, the maximum, the minimum, from the backscattering of Sentinel-1, as well as the Kano element, which is the sum of V and VH, and also the 4 Sentinel-2 bands that are available on the 10-meter resolution with their normalized different indices. We have defined 50 test sites globally. They are distributed over all continents and within all climate regions to cover really the availability of or the look of all the wind turbines that are available. And here, just to give you an example, I've said that before, the databases currently give you the location of a whole wind park. They don't give you a single wind turbine. This is what you can see on the left side. We have then gathered the reference points in the test sites, which you can see in the middle, and just an example for you to see how this is looking like on the right. And as I said before, the limitations of those available databases is the access. So usually they are commercial databases, so you don't have access to it. They don't cover the whole globe. And they are not consistent everywhere. And here's just an example from one of the test sites in Mexico. Actually quite impressive in terms of mean wind speed. We have quite a high potential, and also there a lot of wind turbines are already have been built. So you see the different data sets. And this is what it looks like for 3 of the test sites. So we have gathered over 25,000 reference points in all those 50 test sites. And then for the CP, we have actually used a database, also manually correcting the points. These are distributed globally, so we didn't define test sites here because we wanted to include all the available data. And we have additionally collected 3,000 points from other classes. Most importantly, other power plants, but also forests, industrial areas, grasslands, and so on. And just to give you an example of one of the CPP or coal power plant sites in Germany, it's actually in Saxony, Boxberg, just for the data. So you can see, just to give you an idea, a coal power plant usually has the coal storage. It's close to water for cooling. It has the cooling towers, the cooling facilities, and of course many other parts. And just some examples of the training data that we collected. So different types of power plants, industrial areas, but also forests and so on. And then this is actually what we have implemented, and here the approach is similar for both wind turbines and coal power plants. So we collected the data. We pre-processed all the Sentinel data on the Google Earth Engine. Here we already have a process from the World Settlement Footprint implemented, so we are actually using this data also here. And then we trained an AI model. This time it's an object detection approach on our GPU cluster that we have at DLR. So just to show you some examples, here we have the test sites in California, Mojave. It's very interesting because it's already there since quite some time, and you have quite a variety of wind turbines in this location. So small ones, and of course they're growing over time. And they are now actually being replaced, like a lot of small wind turbines are now actually replaced by one big one. So this is quite an interesting test site. On the top you see the reference data, and on the bottom you see our classification results. We also have Chile, quite interesting. We have Australia, Romania, China.
So we were able to achieve a F1 score of over 0.9. So the model is quite robust. Just to show you some examples of the CPP detection here. Of course, we classified correctly. We actually also classified sites that were not in the reference data. So this was our goal, to find additional ones that are missing in the database. However, we still have some difficulties with other power plants. So we are tackling this. And yeah, we have power plants that haven't been detected. But this is, I guess, a normal process, and we could reach an F1 score of 0.8, which is quite good for this difficult class. And at the moment, we're actually rolling out the whole process to India. I'm almost done. Which is quite an interesting country for both types of energy sources. So it's on the 4th place after the United States, after China, and after Germany for wind power capacity. So as you see on the right image, you have quite a lot of wind speed on the western and southern coast of India. But we also have a lot of coal power plants, and they are still building coal power plants in India. And if we want the transition, we somehow have to stop them. So this is quite an interesting country for us to tackle at the moment. So, and with this, I'm already done. Thank you.
Thank you. So we do have time for one last question. If there's a question. If not, I'm sure Anne-Catherine is around for the coffee break that happens now. We reconvene in this room at 4:45, so 4:45, with the next session. So thank you very much again for all of our speakers, and have a great coffee break.
Can I remind everyone to take a seat here or in the demo area, depending on what you want to follow? Thank you. Okay, everybody. So we are starting with 15 minutes of delay. Just organizational aspect for who of you was not in the demo area before. The demo area has been moved from James Cook to Magellan, which is just close to James Cook. So in case you're interested in that demo area part 2, you have to go to Magellan. So it's a pleasure for me to welcome you to the session 4 of today, the last one in Big Hall, that we will be talking about urban green infrastructure from vegetation characterization to strategic resilience planning. Let me say that I think that there's no doubt that green infrastructure is a main topic for cities. We've been hearing it since yesterday with the keynotes, but also this morning. I remember Mark saying that coming from the recent results of his team of research, if we were able to augment to the 30% of tree cover, the reduction in temperature would be more or less of 1.3 degrees, which is incredible. Even thinking of the 1/3 of premature death that could actually be prevented. So it's really a hot topic for cities, a big challenge, and it's a pleasure for me to co-chair this session with Markus Anilo, which has the direct experience. Markus, to you.
Yes, my direct experience is that I live in Tallinn, and Tallinn was a green capital 2023, which is last year. And there was a lot of discussions and events related with green infrastructure. That maybe the most popular and ideas or projects were like building, not building, but having bog fields, which are like natural areas where city didn't cut any grass. And of course, we started negotiating that we should have like green corridors, which allows animals to cross the city safely through the green area, and it's similar to forests or fields with high vegetation. So I think I had a little bit, I read those descriptions about the presentations, and I think there is a lot of information that is directly related what we did last year.
Yes, so we will, as usual, have 10 minutes per speaker, followed by roughly 5 minutes of questions. I ask all the speakers to keep their time. We will remind you when you have roughly 1 minute left. So we keep the time, and then we go to the poster session and the aperitivo. So it's a pleasure for me to introduce the first speaker of today, Pierre Sicard, that I invite on stage, who is presenting on behalf of his colleague Fatimatou Koulibaly, who is not able to be here. And he will be presenting urban vegetation characterization from multispectral and very high resolution satellite imagery. Thank you, Pierre. The floor is yours.
It's not working. See, it's working. So thank you, Francesca. So yes, my colleague cannot be there, and I will give the talk for her, and I hope I can answer to your question if need be. So, so we need a tree inventory, full tree inventory in both public and private lands in order to quantify and to avoid a large underestimation of the for the quantification of the air pollution removal capacity by urban trees. So for that, we have developed a satellite-based approach in order to detect, classify, and map urban trees, individual urban trees at city scale in 2 front-runner cities, in Aix-en-Provence in south of France and Florence in Tuscany region in Italy. So for that, we have selected very high resolution imagery with a high spatial resolution between 30 and 50 centimeters in order to detect small trees during growing season with a cloud-free sky condition lower than 2% of clouds. We have selected also 8 spectral bands with 1 panchromatic band and 8 multispectral bands with a very low view angle to limit the distortion of urban features like buildings, etc. So for that, we have selected a Pleiad of world-view imagery in June 2020, and for also tree stereoscopy in order to estimate the urban tree aids. So for the green cover detection, we used a stepwise masking system using threshold and DVI lower or higher than 0.40 in Aix-en-Provence, for instance. We try with different intervals in order to classify as vegetated or not vegetated areas. So it was possible to map the green cover at city scale. Then for the tree canopy segmentation, we used the watershed algorithms with different window size in order to extract spectral and textural features for each object. So then we use the aralic features in order for the textural attributes for tree canopy. And for that, we use all spectral bands, but at the end, with different ACP, it was possible to use only 4 bands, visible bands, to extract the textural attributes. Finally, so we need a training model. So for that, so we use the municipal tree inventory. I mean the public trees managed by the municipality. From this inventory, we extract the dominant tree species, for instance, 22 in Aix-en-Provence and 21 in Firenze, representing more than 90% of the total number of public trees. From this inventory, we extract training samples by joining worldview imagery and public trees inventory. And we used 70% of samples as training and 30% for validation. At the end, we extract and we calculate 16 texture-based features for each training samples. So by extrapolating, so we are able to detect individual trees at a city scale and to have a full inventory in public and private lands. For instance, in Aix-en-Provence, the most common tree species are Pinus, Celtis australis, and Platanus species. In Aix-en-Provence, the green cover is reaching 40% of the total area. So for the tree height estimation, so we use the segmentation by the seed region growing, grouping pixel with a similarity, and for each peak is associated to the maximum point of the tree. After that, we use the digital surface model, digital terrain model in order to estimate the canopy height model. So it's possible to map at city scale all individual trees with an estimation of the tree height and the mapping of tree species at the city scale. This is very important for the quantification of the removal capacity by urban trees. Tree species, plant species is the most important parameters for such estimation. So at the end, more than 80% of detected and classified trees are in private lands. So this is why it's very important to avoid an underestimation of the removal capacity to include public and private trees. In Aix-en-Provence and Florence, we have detected 22 and 20 dominant plant species and grassland at city scale, with an accuracy for classification over 80%. For the tree height, the accuracy is about less than 1 meter of accuracy. And the lower trees are detected in residential yards, and while higher trees are detected in public area. Thank you for your attention.
Thank you very much. I have one question. It maybe sounds that I'm like the mayor of Tallinn, but I'm not. If we would need to compare, because what we are doing in Tallinn, but we are collecting the same kind of information from the ground, from the pictures, from the cloud points. Which one could be more effective is maybe not the right way to say, but which uses maybe less resources or is more effective in that sense? I mean, should we maybe this, how much time did it take to analyze the whole city?
Okay, so you mean comparison between ground observation? Because first, ground observation, you cannot obtain observation in private area because it's forbidden to go in the garden. So you don't have. So for that, you miss 80% of information. Second one, I have estimated the time in order to record, for instance, in Aix-en-Provence, we have 200,000 trees. And in Firenze, 250,000 trees. So it's very time consuming. You can imagine to get the tree species, to get information about the tree health. So it's more or less 1 year. And this algorithm, if you have the imagery available, stereoscopy or not, you need maybe 2-3 days.
Okay, thank you. Do we have another questions?
Okay, no.
Don't be shy, it's the afternoon. So in the meantime, I have one. So you were saying that in private land it's not possible to, let's say, collect information on the ground. But which data have you been using for training or for comparing the results of your algorithm in terms of classifier? Have you been using the public trees?
So we use the municipal tree inventory. Each municipality has an inventory of public trees. I mean managed by the municipality. So we use this inventory as a training data set. But for instance, if you have exotic tree species, you cannot detect in a private garden because at least you need 30, 50 trees for the training. So if you don't have, I don't know, but jacaranda, it's a not common species here. Jacaranda is a subtropical species. You cannot recognize at city scale because you don't have enough trees in the municipal tree inventory.
I have another question. While doing this, you said you are using the tree inventory from the municipality, so the municipality is involved in the process, or is it simply giving the data and that's it?
Alors, in my case, both municipalities, but also Vilnius in Lithuania, Valencia in Spain, Bucharest in Romania, are involved. So now we can use these algorithms to extrapolate and to replicate our activities.
Okay. Someone else has questions? So since you've been so brief, I'm going to ask you one more question. Also, because this point was raised yesterday, that industries sometimes have difficulty in connecting with cities. How did you manage to approach municipalities and have them working with you?
European project.
European project.
Yes. LIFE and Horizon project.
So it was a research project?
Yes.
Okay. Thank you very much.
Thank you.
Thank you very much. I asked to show up in stage Joan von Steve with the topic Navigation Urban Landscape, Unveiling Green and Blue Infrastructure through Strategic Mapping.
Thank you. Good afternoon. What I will present is the outcome of a collaborative work. Raquel Lubac, unfortunately, was not able to be here, so I will present the work. And this was done together with the European Environment Agency and the Commission, DG Regio. So it's important to keep in mind this is, let's say, at European level, and what we could extract, what we could say about green areas, green infrastructure in European cities. So just to put in context, all we know the conflicts, competing demand for users in the city. For certain elements may be very efficient, but mainly for natural or greens, there are these competing users. And an outcome of that, there has been a call for action. We have been at global level the SDGs, but then at European level we have the EU biodiversity strategy, and more recently the nature restoration law. It's important also to highlight the biodiversity aspect because, we have seen this morning how green is good for health, but also the EU biodiversity highlights the need to recover the cities to be an important player recovering biodiversity. I don't know if animals crossing the city. So what are the requirements at the European level? So we need to assess the evolution of green spaces, but it's not only to say how much green we have, also to characterize. So is this green public, is private, so still has a role, but then is not as a park that everybody could use it. The composition is not the same, a tree, a shrub, a grass, and how big or how small it is, how is it distributed in the city. Also, it's important to evaluate the impact of actions with all this legislation that is coming and more requirements or also more will the cities to increase the green. What is this, the impact? Is really increasing? What is it increasing? And one important element is that the use and reuse of existing data, that the coherence, comparability, continuity across Europe. So, okay, if you are looking at that, Copernicus is very handy. We have Urban Atlas, probably most of you know. It has 788 cities, above 50,000 inhabitants, and it provides a land use land cover for 17 classes. It includes a specific class called Green Urban Area that we could assimilate a public park. The minimum mapping unit is a quarter of hectare, and it has additional attributes, and we have data from 2012, 18, and 21 that it's coming. Of course, if you want to go more in depth to green and green infrastructure, this information is very valuable, but is not enough. So again, Copernicus provides high-resolution layers, more thematic because are high resolution, but are very complementary. We have the imperviousness, we have seen this morning, how to harmonize a time series. We have the tree cover density that has full European coverage. So all these are at 10 meters with similar time frame. And also the street tree layer that is complementary information or attributes to the urban atlas. In addition to that, we have also the high nature value farmland. This is a European data set out to 1 kilometer developed by GRC together with the European Environment Agency. So agricultural rural areas, there's some areas that have a high nature value, high biodiversity, because the practice, because the location, because the type of crop. And all these areas are very valuable, and very often they are also used for recreation by people. So it's also important to consider that. And also we have taken OpenStreetMap. Why we have taken all these data sets to reach what? So here on the left, on the column, we see the data sets that I just presented. We see the ones that are coming from the Copernicus, so it's reproducible, regularly updated. And below we see the high nature value farmland and OpenStreetMap. And then on top, we see the classes that we have defined. We start from the left for green urban areas that we could simulate to parks. The next column are smaller green urban areas or smaller parks coming from OpenStreetMap and extracting what is impervious. Then we have trees on the street that are not that coming from the street tree layer and combining with the tree cover density. Then natural and semi-natural areas that are more on the urban to peri-urban, that forest and semi-natural areas. Then are classes that, let's say, are more human intensive or intervention. One is sport and leisure, like would be golf courses, etc. Urban Atlas provides the land use, but then we can identify how much of this is green, because there may be other infrastructure that is not green. Similar for private gardens. We know low density areas, and from this low density, we extract what is built up, and then we get that establishing certain conditions. Then we have allotments, moving more to what we consider agriculture that still may have a value, this high nature value farmland, and we end with the blue element. So all in all, here you can browse the results. We have maps for these 788 cities that are publicly available. Yeah, on the right. So here is just an example. On the left, we have Urban Atlas, and green is more or less some green elements, but on the right side, we see more the detail filling on this. But also we can produce analytical tools. So for example, yeah, we can compare the cities, and then we can compare, so this is the percentage of the different elements that we see on the GI component, the green infrastructure component in the different cities, and at the end we have the blue component. We can also see what is the value of what we call this high nature value farmland and how it could contribute, or we can extract and see what is remaining. So with that we can play and we can see the relevance of the different elements, also the importance of private gardens. So this is showing the city and peri-urban areas, but then we can differentiate. We can also identify the percentage of green areas that are protected under Natura 2000 common designated areas. So red means that is below 50% in different categories. Okay, so this is a basis. What I presented is for 2018. Now we have 2012, and we can analyze changes, but this is the starting point. So we can go beyond that and not only saying where is the green and what is the percentage and what type of green, but for example, we can analyze the accessibility. So accessibility to this green area, public, it's important, within 400 meters walking distance. It means that this is a standard that will allow kids and elderly people to reach these areas. And then it's taking into account the street network, the percentage of population that have this green readily accessible within a walking distance. This is a methodology developed by Ugo Pohlmann from the Regio, but now we want to extend to not only the parks as defined in Urban Atlas, to also including small areas, how it would change. But then we have another policy about noise, environmental noise. So here on the right side is Copenhagen. And Copenhagen, yeah, we also have seen this morning that is lacking some green spaces, more spaces in the outskirts. But what is highlighted here are those green spaces that have certain noise quality, so are below the requirements of the noise directive. And also a buffer indicates the accessibility. So people living in the blue area could easily reach walking distance this green. We add another attribute, and quiet. And finally, another important element is when we talk about green infrastructure, green in the city, nature by solutions, okay, we know how it is today. But what would happen in 5–10 years? Particularly, and coming from Barcelona, we know the problems with drought. So it's analyzing, because also Copernicus provides a nice data set, vegetation phenology and productivity. So we could see the impact of past current droughts and also impact on the productivity, and also this could be a tool for assessing the future, what is viable and what could be more vulnerable. So that's all from my side. Thank you very much.
Yes, thank you. I have a question related with the last sentences that you said. If you would like to compare or see what will happen, or if you want to redesign the streets that we already have, and we are using in Tallinn one AI tool for generating just a visualized picture of this. Is it maybe possible? Maybe you have to answer me. I don't know, is it yes or no, and maybe it's impossible to answer today, but is it possible to use this data and connect it with the AI tool that we are using today, so it can show us maybe even better solutions, how the greenery or the green area should look like?
Mm-hmm. Yeah, what I'm presenting here is not providing solutions, but is providing the basis to identify where are problems, because it's not enough, it's not accessible, or maybe problems in the future. And then it comes, okay, which solutions do we have is not considering only green. So it's and I think another important aspect is that we need to say in the multifunctionality in the different elements. So, and connecting with information, because this is pixel-based, we can also connect with local information. And in fact, we have done a test in Go Green cities, and embedding local data with European data. And then European data provides the context, and the local data provides better information that sometimes is not highlighted. But then we know the context, and context is similar in different cities.
Thank you. Do we have questions from you, guys?
Audience is very silent today. We know each other by now, huh? Thomas.
Not so much of a question, but really, I think congratulations for this example, because it really shows what we really need to get to if we want to have a buy-in of the Earth observation data by policy. And of course, Copernicus is really guiding the way. So we have harmonized data, we have regular updates, and it's full coverage of Europe. So then you can come up with this analysis, and that's, I think, really something that we should keep in mind, even if we're starting with very cool analysis in a single city, that we always keep in mind that we need to make sure that the approaches can be applied also somewhere else, and only then we can get out of this research corner where we are often stuck now.
Yes, I completely agree also, because one of the, let's say, advantages of Earth observation is also the comparability through cities. So it's not only relying on local data that might be specialized, but let's say has a wider view. But I do want to stress a question for you. You were talking of local data that can give more precision to a layer, such as the ones that you've been showing. Throughout these 788 cities, did you collect all local data? How does this process work?
No. This was in the context of another project. And in that project, there were few, so we envisage a system that will allow to combine. And then I think it was 2 or 3 cities. Sorry, I don't remember now which one. We tried to put together, so just overlay the local information with the European from Copernicus. And in most cases, it was very nice because, I mean, it's a combination, because when sometimes you have very detailed information, sometimes you miss a bit the context, or you have only the trees, but it was very nice because it helped to understand the context, and not only in the city and around. But on the other side, we got more specific information there. And in one case, it was locating different nature-based solutions that they implemented. And then on the results, we could ask, okay, is this increasing the accessibility, or is increasing the quality, because there were already some green, but now it has more quality, or so it helped to answer these questions and to analyze.
Okay. Thank you, Jean, once more.
Thank you.
Yeah. So it's a pleasure to introduce the next speaker, Ilias Agatangelidis. Thank you. From the National and Kapodistrian University of Athens, Greece. He will be talking about the thermal behavior of large-scale urban parks in global megacities during compound heat and drought events. Thank you, Ilias. The floor is yours.
Thank you. I'm Ilias Agatangelidis from the University of Athens, and in this talk I will try to show you how cooler are parks than the surrounding built-up area. As probably we all know here in this room, cities are some of the most vulnerable places in Earth, because there is the combined effect of the urban heat island and of the climate change, of course. Climate change doesn't mean only an increase in the average temperature, but also more heat and drought extremes. Green infrastructure has been proven to be a very effective solution, with also other positive side effects, not only in combating urban overheating. But most previous satellite-based studies have focused only in few cities, in single case studies. So we wanted to extend this analysis to multiple cities, to multi-year observations, and also to focus in extremes. Just a quick reminder, why are parks cooler than the surrounding built-up area? First of all, the incoming energy, the solar energy, is partitioning more into latent heat flux. that is evapotranspiration, rather than sensible heat flux that is the case in the built-up areas. Of course, there is shading if there are trees. Typically, vegetation has a higher albedo than the urban materials. And also, there is, of course, no or minimal anthropogenic heat sources or radiation trapping. And if we put this in the context of local climate zones, green spaces and parks more specifically create local climates within the city that are cooler than the surrounding urban area. But how much cooler? In parallel to the urban heat island effect, we can define, and is defined, the park cool island. There are many definitions also for the urban heat island and for the park cool island. And we have analyzed in our work some of them, but for simplicity, I'll stick here with the PCI, the park cool island, that is defined as the difference between the temperature of the urban public in the buffer zone of 500 meters minus the average temperature inside the park. Our study has two phases. The first one is a study that covers about 2,000 parks that are systematically collected. More on this in a bit. And in phase 2, we focus only on large-scale parks in 14 global megacities. Okay, the boundaries of the parks in both cases are coming from the OpenStreetMap platform after rigorous filtering and many checks. And as I said, in the first phase, we focus on multiple parks, over 2,000 parks. But what is the special case in this first step? In phase 1, we focus on isolated parks. That means parks that have no other parkland or other extended green space in their vicinity. I think also in the previous presentation, we saw some maps, and the reality is that parks are not in general isolated. They are usually clustered together. So we ended up with about 2,000 parks, but we had started with over, I would say, hundreds of thousands. With automatic filtering, we ended up with around 5,000, and then we manually checked all of them and ended up with the final 2,000 parks. In phase 2, and I should say that because we had very strict rules for phase 1, one problem was that we ended up with very few large parks. So we extended this study also with a special focus on large parks. In both cases, the surface temperature comes from Landsat 8 product, and we computed the extremes of the city using reanalysis data from ERA 5 land. At the right side of the slide, you can see also the classification in 5 major categories that were also manually applied to the parks using aerial photographs. Okay, let's go to the results. On average, we find that during daytime, during the overpass of Landsat, the park cool island effect has a value of 1.5 degrees. This is the average value for all the 10 years that we assessed. An interesting point is that we found that parks in Europe and in North America, especially in the United States and Canada, have a greater cooling intensity than other continents. And this is not because of the climate or because of the park type. Even when we controlled for these factors, for all major confounding factors, parks in these areas had a higher cooling intensity. Maybe that is because of how the parks are managed, maybe because of irrigation, but that is only hypothesis. Also, another interesting point that it came up with our studies, that you can see that in the right side, that parks in arid areas have a strong cooling effect during summer. That was a bit different from other previous studies that focused on single cases in arid areas that had shown that maybe the parks there are not so, have not so much benefits in regards of cooling. But on average, using all these parks and using the systematic selection that we followed, parks in all different climates have strong cooling effect during summer when it is needed. Okay, but what was the major factor that had the greater influence on the cooling effect? That was the park type. During daytime, parks with dense tree canopy were statistically significantly higher in PCI than in comparison to the other parks. Of course, we must always have in mind that satellites see the upper part of the trees, and grass is also in direct contact with the air in pedestrian level rather than the top of the tree. But using satellites, we find that parks with dense trees are much cooler than the other cases. If we focus then on the size of the park, as you can see, and I must note that this graph ends in 20 hectares. As I said before, you had a small sample size for larger parks, so that's the reason why they are not included in this graph. But what we can see that with increasing area, the cooling effect increases like a log-like function. Previous studies and also the smaller samples that we have show that this line continues to be logarithmic, but as I noted, the sample size in our study was smaller, so that's why we end at 20 hectares. Okay, let's move now to the larger parks. The first result was that on average, they have a strong cooling effect, much stronger than the global average that is shown on the left side of the slide. Regarding compound heat and drought events, there are two results that are important. The bad news are that they are increasing, both in intensity and frequency and duration. The good news is that large-scale parks remain largely unaffected by these heat and drought events. We found no significant difference between the typical conditions during summer and the conditions during extremes. This is again possible because of the irrigation of the parks. Parks are not a completely natural environment. There is the influence of humans, so they can, in general, be resilient in extremes. But when we go back to the larger sample of 2,000 parks, if we focus on the arid and the Mediterranean climates, we see that the distribution of the cooling effect during heat and drought events is about 1 degree lower than the typical conditions. So remember in a previous slide, we saw that in arid regions, parks have in general a strong cooling effect, but during heat and drought extremes, the cooling is smaller.
Sorry, just to tell you, you have to conclude. Thank you.
Yeah, I'm in the last slide. So, to be quick, parks with trees have the greater cooling intensity. We found that for small to medium-sized parks, they follow with a high certainty the logarithmic function. We also to extend this work using nighttime data from Aster, EcoStress, MODIS. Each one of these solutions has its problems, but that's the direction we are going to follow. Thank you.
Thank you very much. I have one question. Does the shape also affect the cooling effect?
The shape of the park?
Yeah, probably. Maybe we just should build big, long stripes, or some in some else shape that we should consider.
Okay. Well, we also checked the shape, and we didn't find a very significant difference. But in part, this is because of satellite data, because if we have very narrow strips of park, there is much mixture between the park and the surrounding urban area. So one problem with this is because of the data. So not much difference, but with a bit of uncertainty.
All right. Any questions from the audience?
I have one more question, Elias. You were showing this logarithmic function of the cooling effect of parks depending on the area. So it's very interesting to understand that it's not a linear thing. The more it's big, the bigger effect it has. I have a question also putting myself in the shoes of municipalities. What about having a lot of small parks? Not too far one from the other. Does it have a major impact compared to one big park and that's it? What's your finding, and can you elaborate on it?
Yeah. Well, first of all, large parks also play another role in the city. So they are for recreational uses, as a shelter during heat waves. So the answer is not so simple. Staying only on the cooling effect, we saw that with increasing area, there is a logarithmic, not linear, but there is an increase in the cooling effect. Also, previous studies have shown that a few isolated trees don't have such a good cooling. So to give an answer and not to go around the issue.
It's not an easy question, sorry.
I think many small to medium-sized parks are the better solution for cooling purposes.
I have one more question as well about the water bodies, or I mean, does they affect as well the way that these parks are cooling down the city? If I don't know, we have some ponds or lakes inside the park.
Okay. In the larger sample size, on purpose, we didn't include parks with water inside, so as to have 5 more concrete categories. But one of the reasons why the large parks had the substantial cooling was that the majority of them included water surfaces, so water plays a significant role in cooling. Thank you.
Thank you again.
Thanks. The next topic is enhancing urban green space through Earth observation, integration of super resolution in sustainable urban planning. Theodora Selea, please.
Hello, I'm Theodora from DMV, and today I'm going to present our work regarding the enhancement of urban green spacing using Earth observation with super resolution. In the next few minutes, I'm going to present the Space for Urban Green project that founded this work, followed by the motivation behind it and the challenges that we identified in monitoring urban green spaces. Then we are going to talk about the method and technologies that we have applied and a showcase of our main results, and finally the conclusions and a few future directions for us. The Space for Urban Green project is founded by ESA. It was a project led by GMV in collaboration with CO Space Tech and Cardiff. Now, why are urban green spaces important for a sustainable urban planning? Well, because they play a vital role in improving air quality, thus reducing the urban heat island effect and enhancing the well-being of city inhabitants. In order to do this, we made use of Earth observation data because it allows us to have a large-scale monitoring of urban events, and in addition to this, we managed to overcome the limitations of traditional Earth observation data, offering a higher resolution by applying super resolution techniques. Therefore, in the Space for Urban Green project, we aim to showcase how this Earth observation data can be effectively used for urban planning. To ensure that the proposed solution met the real-world demands, during this project we actually had a user consultation with respondents from 11 cities, 9 from Europe, and 1 other East Tunisia, and finally from Turkey. By doing this consultation, we managed to identify the current needs and ensure that our work during the Space for Urban Green project had actually practical requirements for the urban planners. So the motivation behind this is given the urban challenges that come across given the growing population numbers. As previously said, we have air pollution, heat islands, and climate change. However, managing these green spaces in a traditional way is costly and time-consuming because it's a manual labor task. In addition to this, the city managers actually need accurate data, which needs to be obtained at a larger scale. So, in order to mitigate this, we proposed the solution that we are going to present today by combining the Earth observation and super resolution based on AI method. We came across a few challenges when designing our solution. First, it was the limited resolution of Earth observation data, because, for example, Sentinel-2 offers a 10-meter resolution, which is not enough to detect smaller green spaces in dense urban environments. Second, there was the high cost of the traditional methods. Here we include field surveys or even, let's say, drone campaigns. And we also came across some inconsistent data because sometimes the urban planners need to access municipality databases, which might be in different formats and difficult to use. And they also need to integrate these different types of data. In addition to all of this, there is also a lack of historical context, meaning that it's more difficult to see the changes that were made in a city regarding the urban green spaces changes and how different urban development were made. So in the Space for Urban Green project, we proposed 4 services, some of which are applicable to the design of planning of urban green spaces, and the others to the management and monitoring of urban green spaces, and a few of them are going to be presented on the next slides. If you have a look here, this is an example of how we actually did this. So we used a super resolution applied across sensor using Sentinel-2 and spot data. Sentinel-2 was enhanced by a factor of 4 up to a resolution of 2.5 meters, which was enough for us to detect the particularities in urban green spaces. Afterwards, the super resolved image was used in other AI-based algorithms to perform land use and land cover classifications. If you have a look at this image, for example, the one from the left is an actual urban vegetation mapping obtained from a super resolved satellite imagery, and the two images from the right actually show the difference between performing a land use and land cover or urban mapping on a satellite to image and on a super resolved image. It is visible that the one from the outmost right has more granularity, meaning that we can detect better patches of vegetations and smaller ones, which is of use especially in particular for urban planning. Now, given the previously obtained images, we developed, as I said, a series of services. One of them is the design and planning of urban green spaces, and this is actually the land use and land cover map generated from the synthetic image. We can actually see here that we have, from a total area in the image of 120 hectares, we have a vegetation area of around, let's say, 80 hectares. So this is what the service allows us to do, to see, for example, the green space in relation to other types of data. Another service integrated by us was the combination of other in situ data, like the one from air quality and temperature. And for example, as we can see it here, this allows us to see where other green spaces are needed to be installed given the particularities of air quality. Another example would be the one related to the population and the vegetation area concerning a population zone. So for example, here we can see that we have, let's say, in the first area, the one from above, we have a low vegetation zone for each inhabitant for around 15 square meters. And in the second one, we have more vegetation per inhabitant, like 31 square meters. The services regarding the management and monitoring of urban green spaces allow, for example, to identify vegetation health status, and by monitoring the service, the urban planner can prioritize interventions to help the vegetation. Another one would be using the historical data from a particular area, which actually enables us to see how some specific areas have changed. For example, how urban area was developed, how many tall buildings appeared, how the industrial area, and what changes were appeared in a particular area. So in conclusion, during the Space for Urban Green project, we managed to demonstrate the value of integrated Earth observation data in the design, planning, and management for urban green spaces. We managed to show that super resolution techniques applied even on Sentinel-2 can actually lead to good results for finally obtaining a good product for urban green spaces. And we showed a few practical applications, like the ones you saw before, like vegetation health monitoring, population accessibility, or land use change detection. Our future plans include to expand the demonstration pilot cities so that we can have more diverse geographic settings, We plan to develop a long-term commercial strategy and, of course, work on enhancing the AI models to obtain better results. Thank you.
Thank you very much. I have one question. It's based on the user needs. If I would like to use this application or this technology that you were working on, have been working on, do I need a lot of experts, or is it so intuitive that everybody can do this? I imagine that you are putting on some filters and layers, and then you can see the difference, and maybe there is even some kind of description how to read these changes from the pictures.
Yes, so the final product is intended for general use, so that the expert knowledge should be reduced and needed as personnel.
Thank you. Yes, I can see there is a question. One moment, the microphone is on the way.
Thank you for the presentation. I'd like to ask you if you have quantified the added value for going from 10 meters to 2.5.
In what way do you mean quantified value? Like the super resolution algorithm, or as the final end product?
You know, the added value in terms of planning. I mean, if you have quantified how better the 2.5 product serves the need for urban planning.
Unfortunately for this, we didn't manage to find an actual score as it is for super resolution. So this was only visually identified by our remote sensing expert, as in the picture shown there. So we had a visual technical comparison, let's say.
Great, thanks.
Other questions from the room? Okay, I have one last question. It's always about going from only the mapping to instead some information that can help actions, as it was said already this morning from our keynotes. So this goes a bit in this direction, your management and monitoring service. I was wondering, you were talking about the health status of some vegetation. Do you come up with some statistics that municipalities can use, or is it just one by one? What's the kind of information that you provide to municipalities?
Yes, it's more like a statistic, like a map with the level of, let's say, health of the vegetation. Yeah.
So statistics on the health based on an area?
Yeah.
Okay. Thank you again. So it's a pleasure to introduce the next speaker, Gabriele Oneto from University of Genoa, Italy. He will be telling us about unveiling living urban cohabitats, looking at cities through a species-agnostic classification. Welcome, Gabriele. The floor is yours.
Thank you for the introduction. And oh boy, it's crazy to be talking here. But anyway, yeah. Good evening. I'm Gabriele, and let's talk about landscape ecology for a second, with just a pinch of urban planning. But unfortunately, these results are yet to be published. Unfortunately, my consortium is quite a tyrant, and also time is a tyrant. But unfortunately, everything is going to be out in a couple of months. Anyway, this is where I live. This is Genoa. Let's get familiar with it. It's quite a large city, but there are things living in it, like this cute animal, and also these cute animals. Cute plants, not so cute animals, and animals that people really don't like. Unfortunately, there are also people who like to work with animals, like my friend Francesca, who is a parametric designer who works to develop green nature-based solution to try to cope biodiversity and urban planners. And on the other side of the Alp, there's my second home, Munich, where there's my friend Brandon, who is working with birds and all other kind of animals, like hedgehogs, bats, and local plants. And while we talk with one another, we always say, yeah, we have so many great ideas, plants biodiversity, green nature-based solution, but how can we actually make things connect with one another? Yeah, let's talk about that. Because in green urbanism, confronting different site conditions is quite hard. For instance, which spatial module should we use? And which aspects of cities should we consider, like buildings, cars, or temperature? And from whose perspective? We are always talking about the human perspective. Yeah, we are the ones who are making the discussion and taking the solutions, but there's also birds and plants in there. So we have a lot of research and results. These guys were saying this almost 10 years ago. But still, we lack the will and capacity to act on it. So frameworks. Frameworks are great. We have so many of them, and I'm going to present one of course. And we have frameworks on green infrastructure, on nature conservation, and so on and so on. And they are good at describing a lot of things, especially if they are generic frameworks. But they tend to prefer one single perspective. And while dealing in cities, such perspective matters. Let's take a look at phrasing, for instance, in Germany. In urban landscapes, from an architectural perspective, the first thing I think when I think of landscapes is identity, this cultural thing that just makes a place that for so many people, and also legibility. Looking at the landscapes, I'm perceiving it for what it is. I'm seeing here clearly there's a church. It's a rich history behind it. But for an ecologist, that is just a group of environmental conditions. I don't care about anything else. And also, multiple dimensions are around in cities. Physical conditions, social economic inclinations, abiotic conditions, like the SETS system that is gathering more and more knowledge each day. So what's the idea? We want to build up knowledge about urban landscape diversity and compare different sites in cities and between cities, and work with multiple things in mind, not just ecology, also urban planners, and describe the urban habitats as a whole. And so, in doing so, we want to keep 4 properties. The main one is a meaningful agnostic perspective. So one that envelops basically most of the things that are living inside of the city. And in doing so, it also helps addressing rare species, so the ones who are not that much data about them, and lost species, so the one that nobody cares about. And in doing so, let's talk about multiple dimensions, so multiple layers, and keep the architecture flexible so we can expand without having to redo everything else by working at 10-meter resolution. Start about methodology. We are working on 3 cities under the umbrella of this Horizon project, the ECOLOPS project, where me, Francesca, and Brandon are working in computationally designing nature-based solution with specific multi-species target in mind for these ecological envelopes for building. And our methodology is based on 5 steps, but it's quite late, so I'm going to just skip through them. But one of the things that I really like about our approach is that our idea of cities is not just, let's get the municipality, because the municipality is an anthropic construct. And the global human settlement layer, I don't know if this was by design, but it's doing a perfect job in just considering a broader area that is marvelous for connectivity's sake. And let's do everything at 10 meters, yes. And for the layers, let's talk about the 2 different focus. One, it's at the local scale. So let's focus on what's there, the local urban form, local cell diversity, while focusing on the surroundings, so using a 100-meter moving window, we are addressing landscape urban form, so patch distribution. Also anthropic imprint, both the active and passive action of human in the landscapes, and finally, biophysical conditions. We have selected more than 60 variables and scraped everything, mostly everything, automatically from only open datasets. So in this way, we can expand and just gather all updated version of all of these amazing products, like the high-resolution suite layers, global human settlement, OpenStreetMaps data, and so on. We compute everything on multiple pipelines that are designed to be run on Linux clusters, so to help us to expand by working with rasters and vectorial pipelines. And everything is written in Python, and then we save everything into rasters files. Then we simplify, because from 60 variables they are too much, and we run into the problem of having not such a clear-cut behavior. So we select the best feature reduction algorithm by choosing the one that can get the more information without adding too much complexity. Finally, we classify everything, and we actually found out that K-mean, of all things, did a good enough job into getting everything back together. So, results. And here the results are taken in two different ways if you are an ecologist or if you are an architect, because architects really like categorical maps. They are like that single omniscient class, while ecologists don't like maps. They like gradients, they like PC values. And that's why when we started dealing with applications in the future, we have both, so we can approach the problem from the two different sides. But let's talk results. This is 39 distinct classes with more than 1,200 combinations, divided into the 4 layers. Some of them I'm pretty happy about, like anthropic imprint, the one on the top right, that is showing how the landscapes is being confronted by the different presence of humans, and also like the nighttime light emissions, heat emission, the distance to land users' particular characteristics, and so on, and also presence of particular overarching policies regarding park or big natural conservation area. And we confronted the city center of each city with the surrounding satellites, because morphology and the other aspects quite differs between the red zones and the blue zones. And between all of the metrics, I just selected a couple of them. So let's see anthropic imprint confronting with local urban form. And some of these things quite make sense. So this is not a laser pointer, I think. But I don't know. OK, it's fine either way. So for instance, in the city center, we have a lot of regulated natural areas. So what are they? They are green parks. They have green infrastructure that they are lacking in the satellites because they don't really afford that kind of infrastructure. But what they have are really big natural areas with overarching directives, national parks, for instance. Another difference that we highlighted is that in satellites, there is a lot more commercial and industrial areas that have a bigger impact on local biodiversity. This is not really present in city centers because there's not space for that. But in city centers, we have more core human living areas, very busy, dense urban areas. And let's show a couple of parks here and there. Here is the Munich English Garden, and looking again at the top 2 layers, you can see how this constellation of local diversity correlates with the classes of anthropic imprint. And so from the actual park to get to the city center, you're passing through very dense area of human activity where probably animals will have a very tough time getting through that. But if you take a look at the similar results in Genoa, again, the park is much smaller with that tiny, tiny bean of yellow. But before getting to the purple, very heavy thingy, we're going to get through more edge human patches, in a way, a smoother gradient. But just to wrap up things, what are the main takeaways of these things? So the application is, of course, we're not trying to explain everything. This is not to be confused with an omniscient knowledge base. This is not our idea. We just want to bridge different domains of urban studies together. Landscape ecology, urban planners, and probably other disciplines that deals into urban analysis for nature-based solutions, for greenery, species mitigation, and climate change adaptation. The limitation are data availability, of course. I'm always looking forward to new layers, and I have to thank all of the people that yesterday already gave me some suggestion of improvement. If the OECD really can deliver a new resolution at the functional urban area of social economic data, oh please, I want that. And regarding the computational requirements, everything is going to be scaled up using the architecture of the Leibniz Research Center. And the next step is to expand to more cities. If you have really big cities in Europe, please reach out to me. I want to include your city. Decide if we really want to keep the functional urban areas or go back to the city center, because sometimes people forget that all of this expansion is going on around the border of the city, and so is the data that is lacking. And start to apply on some things. I'm going to tackle urbanity island and plant biodiversity. I have friends and colleagues that are going to tackle plant management and social interaction. And finally, a really warm shout out to everyone who helped me, all of my supervisors, cool people who helped me, and all of the Ecolabs consortium. And thank you to you all.
Wonderful, thank you. I have one question. You asked the cities to turn to you, so I have a question. Did you find something interesting during the research that every city should take in mind when planning new areas? Something that was so interesting that maybe it's, you can burst it out here.
It's quite difficult to generalize one thing that every city must have, right? Especially if you just go by the everything just need to be greener. Well, one thing that actually, I think I have an answer. So from a humanist point of view, everything needs to be greener. It's difficult because we have so many regulations that deals into heritage conservation that are just a straight barrier. And that is coming from a straight anthropic point of view. And if you don't start tackling that, then we can't really green cities, right? We're thinking of putting green solar panels and green roofs on cities, but if you try to do that, at least in Italy, they will say, oh no, you can't.
Yeah, that's a good point of things, because definitely there is when we want to plant the trees, but we cannot plant it on top of gas pipes because they has to be, this area has to be clean and yearly maintained. So there's no point of thinking about making cities greener. So totally, it's a good idea. But I saw a hand from the audience. Yeah.
Hi. Hi, Gabriela. Thank you so much for this presentation. It was very interesting, very funny at the beginning, so you got the attention of everyone, mine too, as well. So I wanted to ask you two questions, basically. The first one is, well, for this study to be as generalized as possible, you must have used, of course, the open data set you've mentioned. I was wondering if you found some data that many cities were it was shared, or common data used by every city that you used, or just European data sets. And also, how was this study validated? On like what data do you use to validate the maps you showed at the end? Thank you so much.
Thank you for your question. I'm going to be super honest. I'm going to start with the second question. We're working on that, and as of now, the validation is using internal methods. So we are actually looking for external. Then we'll have a second version of with external validation to actually work with this kind of maps. For some of them, it's going to be easier, especially the one that are basically land covers plus diversity on top. For some of them, it's not quite easy, so much easy, so probably the validation will just be one map that's trying to explain the other, like the social economic one. There's not that many maps that are doing that kind of work. So yeah, that's quite an open topic. But regarding the first one, I try to use as much as global data as possible. But some of them it's quite easier to just get it for Europe, like all of the global high resolution layers of Copernicus. There are also quite a lot of cool vectorial layers, like unharmonized data sets of world protected areas that could be accessed worldwide. So vectorial data is not just park from OpenStreetMaps, but it's just every kind of area with our overarching national protected policy of any kind. And that is quite cool. And it's not that much taught. Sure.
No? Okay. Did you process yourself satellite data, or just used maps deriving from satellite data?
So where the products were available, we just used the product. Some of them, I think something regarding temperature we actually processed. And we're actually looking forward for the OpenEO environment of Copernicus to get all of the Landsat data, because at that point we can just process things for temperature data at 10-meter resolution. So yeah, we're actually kind of doing both.
Thank you. Other questions from the audience? Gabriele, let me thank you for your very enthusiastic talk. I do have one more question. By the way, I really like your point of view of not seeing human at the center all the time. We have this attitude sometimes to claim that we are the most important species out there, but actually we are not, and also pigeons might have a role, you know. And so you've been classifying a lot of urban areas, urban types. I was wondering, what do you see as the next step? What is the kind of information? I mean, putting together architects and natural scientists is a big thing. So how do you see your products evolving towards, let's say, some decision support system?
I think that kind of depends on which application starts from here. Because while we were developing such a classification together with architects, I mean, the two poles just wanted things done differently. But that's the same thing that is going on in the Ecolabs projects. We are developing nature-based solution, and people just want to do things separately. So I think that at one is just doing a nice job at bridging two very different subjects together. And then in the future, as more application is going to play around this, maybe it's not going to be my work, maybe it's going to be the work of somebody else, but as many people is going to really start working around a multidisciplinary tool, then maybe the surrounding cultural scene could start thinking in a more broader term. Or maybe it's just my optimism talking.
Thank you, Gabriele, again.
Pierre from France, Pierre Scardi, will talk about species-specific air pollution removal by individual trees and shrubs at city scale.
Okay, thank you. Okay, so now I can present you some information and a project about the quantification of air pollution, air pollutants removal capacity by urban trees at city scale. So as you know, urban trees can improve or not the air quality through two processes. So the first one is the deposition of gaseous and particulate air pollutants on leaves, trunks, and branches surface. And the second process is about the stomatal uptake of gaseous air pollutants through stomata on leaves surface. So in order to quantify the air pollution removal capacity by urban trees, we have developed a model, floor tree model, in order to propose and to select the best tree species, plant species for urban planning. So the database gathers more than 200 plant species with some physiological and environmental parameters like stomatal conductance, emission rates of biogenic VOX, volatile organic compound, and some morphogeometric parameters like leaf area index. So in order to run the floor tree model, we need at least 1 year of early data for the air pollutants concentration, but also meteorological data like solar radiation, air temperature, wind speed and direction, and relative humidity. For each tree, we need also, we estimate some parameters like the size at maturity for the crowd dimension, and parameters are all considered for healthy and isolated trees. So we need to estimate the gaseous air pollutants uptake through stomata. So for that, we use the phytotoxic ozone dose, for instance, based on species-specific stomata conductance, velocity of deposition, and the stomatal conductance depends on some environmental parameters like the soil water content, the air temperature, the solar radiation, etc. This allows us to quantify the quantity of ozone or NO2, for instance, uptake by each tree. In parallel, we are able to estimate and to quantify the quantity of ozone formed based on isoprene and monoterpene emission rates and reactivity factors. At the end, we can calculate the net ozone uptake, the difference between the quantity of ozone removed and the quantity of ozone formed. And some tree species can form more ozone than removed. So such tree species are not recommended for urban planning and for reforestation, for instance, and greening activities. For the deposition of PM, particulate matter, so we use the velocity of deposition based on some parameters and empirical equation using star, so the shoot silhouette to total leaf area ratio, and the phyllotaxis in order to estimate the species-specific PM removal capacity. We estimate also the CO2 storage and CO2 sequestration from allometric equation in order to estimate the dry weight tree biomass to quantify the equivalent CO2 based on the diameter at breast 8 and the tree 8. So we apply the 4-tree model to different frontrunner cities, so Aix-en-Provence, Florence, Valencia, Vilnius, and Bucharest, in order to map the capacity of urban trees to remove or not air pollution, to mitigate or not air pollution. So I will present you one use case in Valencia in Spain. So we have detected more than almost 150,000 trees with 300 species. So most common tree species are citrus, platanus, and phoenix, palm trees, Washingtonia and phoenix. So at the end, we are able to map for each tree, individual tree, the impact on air pollution. I mean, on this figure, you can see the quantity of PM10 removed every year by each tree. For NO2, for CO2 sequestration, and for ozone. And for instance, you can see for some tree species, many trees in Valencia, the trees form more ozone compared to the quantity removed. And we can see with a focus on different species. So for instance, in Valencia, so we can estimate the quantity of ozone formed by the trees, public and private, so more than 225 tons, because the ozone formation potential is higher compared to the ozone removal capacity. For NO2, almost 200 tons per year, 40 tons for PM10, and more than 5,000 tons for CO2 every year. Thank you for your attention. I'm fast. Very fast.
Thank you, and I especially thank you for saving our time, because what I want to say, yesterday I had many questions when after my presentation, that if I have had mapped every tree in the city, how I estimate what is the not value, but what is the what is the air pollution effect to them. But I now see that you have done the work, so probably we will contact with you and take those formulas and have a chat with you about making these same calculations of Tallinn as well. That's why I mean. But I was started thinking, aren't you afraid that someone will take these formulas and start saying, oh, look at this tree, it's so like, it's doing so less work that we can cut it down. It was a joke.
No, okay. So maybe dangerous. No, because you have different cofactors. So not only air quality. For me, all trees are good for humans, but not all trees are good for air quality. But now we know. So when you want to plant, so we need to communicate to city planner and urban planners and manager, because if you want to plant, you need to know your existing tree inventory. You know the impact on air quality, and from this information you can adapt and you can adjust. For instance, in Valencia, avoid to plant palm trees. You can plant different acer species, for instance, in order to balance. But you need to have a global vision, not at city scale, but at metropolis scale, for instance, or conurbation scale.
Another question came up. Did you take any aspects about the building ecosystem? Like, if we think about only reducing the air pollution, but what about that we want to have like a lot of pieces living together peacefully, so we definitely have to take the aspect of different trees, gives a living space for different animals or different living beings.
So, okay, we can estimate different regulating ecosystem services for air pollution mitigation, but also cooling effect, so for the urban heat island mitigation. So now we have all information. So yes, you can estimate and quantify different ecosystem services, not only air quality.
We have a question from the audience. The microphone is coming to you.
Thank you for the presentation. I want to ask if those values are relevant for the transport emissions, how big percentage of the transport emissions the trees can collect, because I don't have this intuition about figures.
About the transport of emission?
Yeah, how those values correspond to the pollution of the city?
I don't understand.
You mean the pollution from transport?
Yes.
Okay. So
okay. So no, for this estimation, I use local data for air pollutants concentration from air quality monitoring station. So I cannot dissociate the percentage for transport, for industrial activities, etc. Because I use just the air, the concentration, ambient air concentration.
Yeah, but if we now go from absolute values to percentage to relative change of the air quality, what is the change?
So every year you have different value, because we need at least 1 year of data, because the most important parameter for trees are the soil water content. So if you have droughts, so you don't have exchanges of gases from air to the inside the trees, because to save water, the trees close the stomata, so you don't have uptake of air pollutant. So you need 1 year of data to quantify, so you need a lot of environmental parameters, not only air pollution data. So from here to another year, the estimation will be different. So you cannot estimate the percentage of changes. I don't know if I answer. No?
Okay, yeah, then maybe you can chat next, yeah. Okay, one very quick question. You've been looking at the tree species, the different tree species. Is there, let's say, a correspondence between the tree and the type of pollutant that it removes, or are there some specific species that are good for removing whatever pollutant?
Well, the capacity depends on trees. Some tree species are more efficient to remove, for instance, particulate matter. Conifers are the best. And deciduous species are the best for gaseous air pollutants. So depends if you want to plant some trees along the road to reduce PM in particular, it's better to plant some conifers.
Okay.
So we can dissociate for each air pollutant.
Thank you, Pierre, again. So let me thank all the speakers today and Marcus. That has been we've been co-chairing greatly this session on green infrastructures. I want to just a few communications in terms of organization. Tomorrow morning we are starting here in the big hall at 9:15. We will have reflections on this first day from our urban practitioners. So you must have noticed that today we had 4 sessions on different topics, all co-chaired with users. So we will have their reflections after this longish day. And then we will go towards the other sessions, the other technical sessions that will happen here and in Magellan. So we will be a bit on both rooms. So who has not done it and has a presentation tomorrow, please go to the colleagues at the end of the room to upload your presentation. And we will be sharing presentations at the end of the conference online. So if for any reason you do not want it to be shared, please always let our colleagues know in advance. And last, we have now the lovely poster session. I've seen that you've been already interacting. You will have a nice aperitivo to interact even better. So please, just enjoy. Thank you.